From the moment human beings became aware of themselves as thinking creatures, the sky has loomed overhead as both a presence and a provocation. Long before it was an object of measurement, the heavens were an experience, vast, patterned, and unreachable. Day after day, the sun traced a dependable arc. Night after night, stars emerged, arranged in configurations that seemed at once stable and alive. The moon waxed and waned with a rhythm that insinuated itself into human biology, ritual, and memory. To look upward was not simply to observe nature, it was to confront mystery. Why did the lights above move as they did? What governed their order? And perhaps most unsettling of all, what was humanity's place beneath them? These were not questions born of leisure or abstraction. For early humans, the sky was bound to survival. Seasonal changes governed the availability of food, the migration of animals, and the cycles of planting and harvest. The rising and setting of particular stars became signals, cosmic markers that anchored time itself. Before writing, before mathematics, and before cities, the heavens served as humanity's first clock and calendar. Yet utility alone cannot explain the depth of meaning early cultures assigned to the sky. Even in the most practical observations, wonder was present. The regularity of celestial motion suggested intention. The enormity of the firmament suggested power far beyond the human scale. Archaeological evidence indicates that humans were marking celestial events tens of thousands of years ago. Cave paintings, standing stones, and carefully aligned burial sites reveal an attentiveness to solstices, equinoxes, and lunar cycles that exceeds mere coincidence. These early sky watchers lacked a formal language for astronomy, but they possessed an acute awareness of pattern. Repetition bred expectation, and expectation gave rise to interpretation. The heavens became a story written in light, one that demanded explanation, even if none could be verified. Myth was humanity's first answer to the sky. Faced with phenomena that could not be controlled or fully understood, early societies framed the cosmos in narrative terms. The sun became a deity or a chariot, the moon a watchful guardian or a wandering god, the stars ancestors, spirits, or heroes frozen in time. These stories were not naive attempts at science but sophisticated frameworks for meaning. They integrated cosmology with ethics, social order, and identity. To know the sky was to know who you were and how you ought to live. Yet even within myth, there was curiosity. Many ancient stories are not content merely to personify the heavens. They grapple with questions of origin and structure. Why is the sky above and the earth below? Why do some stars wander while others remain fixed? Why does the moon change its shape? These narratives often encode observational insights, preserving generations of accumulated knowledge beneath layers of symbolism. The boundary between myth and early cosmology was porous, and within it lay the seeds of more systematic inquiry. As human societies grew more complex, so too did their engagement with the sky. Agriculture intensified the need for reliable calendars, and centralized power demanded predictive authority. Priests, shamans, and early astronomers emerged as specialists whose role was to read the heavens on behalf of the community. Their observations were often entwined with ritual, but they were nonetheless empirical in character. Eclipses, planetary motions, and stellar risings were recorded, compared, and anticipated. The sky became a domain where careful watching conferred both prestige and power. At the same time, the heavens provoked philosophical unease. The apparent perfection of celestial motion contrasted sharply with the disorder and mortality of life on Earth. This contrast raised uncomfortable questions. Were humans the center of creation, or merely inhabitants of a small and fragile world beneath an indifferent sky? Did the lights above exist for humanity's benefit, or did they obey laws entirely separate from human concerns? Such questions did not yield easy answers, but they marked an important shift. The cosmos was no longer just a backdrop for human drama, but a subject worthy of contemplation in its own right. The act of looking up also cultivated humility. The sheer scale of the night sky challenged any simple sense of human dominance. Even without modern measurements, the intuition of vastness was unavoidable. The stars were numerous beyond counting, their distances unfathomable. To stand beneath them was to sense one's own smallness. Yet paradoxically, It was also to feel connected to something larger. This tension between insignificance and belonging has never left the human relationship with the cosmos. Crucially, early cosmic questions were not limited to what the sky was, but whether it was inhabited. If the lights above were realms rather than decorations, then it was natural to wonder who or what might dwell there. Many ancient cultures imagined the heavens as populated spaces, home to gods, spirits, or ancestors. These were not idle fantasies, but logical extensions of a worldview in which Earth itself teemed with unseen forces. If rivers and forests had inhabitants, why not the sky? This intuition, that other realms might exist beyond the Earth, represents one of humanity's most enduring ideas. Long before telescopes or spacecraft, people entertained the possibility of other worlds. These worlds were not necessarily physical in the modern sense, but they were real within the cosmological imagination. They shaped rituals, moral systems, and expectations about life and death. The sky was not empty. It was occupied, layered, and alive. Over time, this imaginative richness laid the groundwork for more abstract thinking. Once the heavens were conceived as a system rather than a mere canopy, questions of structure and causation became unavoidable. Why do celestial motions repeat with such precision? What governs their paths? Are the patterns eternal, or did they have a beginning? These questions mark the transition from mythic interpretation to proto-scientific inquiry. They do not reject wonder, they refine it. Looking up thus became an intellectual act. Observation turned into reflection, and reflection into speculation. The sky invited hypotheses long before it allowed tests. Even incorrect ideas contributed to progress by sharpening questions and revealing inconsistencies. Each attempt to explain the cosmos, however flawed, represented a step away from passive awe and toward active understanding. It is important to recognize that this process was neither linear nor uniform. Different cultures emphasized different aspects of the sky, shaped by geography, environment, and social structure. Desert skies invited different interpretations than forested ones. Nomadic peoples engaged the heavens differently from settled agricultural societies. Yet across these variations, a common thread persists. The sky mattered. It demanded attention, interpretation, and respect. In this sense, humanity's first cosmic questions were not scientific in the modern sense, but they were foundational. They established the habit of inquiry, the willingness to look beyond immediate experience and ask larger questions about existence. They trained human minds to search for order in apparent chaos, and to accept that some truths might lie beyond reach. The story of cosmic exploration does not begin with instruments or equations. It begins with eyes lifted toward the night, minds unsettled by what they saw, and voices attempting to give shape to the unknown. The earliest humans could not have imagined spacecraft, galaxies, or expanding universes. Yet the impulse that drives those discoveries, the refusal to accept the sky as mere scenery, was already present. In looking up, humanity took its first step toward understanding worlds beyond its own, even if those worlds existed only as questions waiting for future answers. Before the emergence of science as a formal method, humanity's understanding of the cosmos was shaped by a complex interplay of myth, philosophy, and careful observation. These were not separate domains, but overlapping ways of making sense of the same sky. Myth supplied meaning, philosophy supplied structure, and early astronomy supplied continuity. Together they formed a pre-scientific worldview that was neither arbitrary nor ignorant, but internally coherent and deeply responsive to lived experience. Mythological cosmologies were humanity's first comprehensive models of the universe. They explained origins, order, and destiny through narrative, often grounding cosmic processes in human-like motives and actions. Creation stories across cultures frequently begin with chaos or darkness, followed by an act of separation. Sky from earth, light from darkness, order from disorder. This recurring pattern reflects a universal intuition that the cosmos is structured rather than accidental. The sky, vast and seemingly eternal, was rarely treated as inert. It was dynamic, intentional, and often sacred. In many traditions, the heavens were imagined as layered realms. The sky above was not a single space, but a stratified structure through which gods, souls, or celestial forces moved. Stars might be holes in a cosmic roof, campfires of ancestors, or divine eyes watching the earth below. The Milky Way, with its luminous band across the night, was especially potent as a symbol, a celestial river, a road of spirits, or the boundary between worlds. These interpretations did not arise from fantasy alone, but from repeated, careful observation married to symbolic thinking. At the same time, mythologies often encoded surprisingly precise astronomical knowledge. Seasonal star risings, planetary cycles, and eclipses were woven into stories that preserved their timing and significance. Oral cultures lacking written records relied on narrative as a mnemonic device. Myths became data storage systems, transmitting astronomical information across generations with remarkable fidelity. In this way, story and sky were mutually reinforcing. Observation informed myth, and myth preserved observation. Philosophy emerged when thinkers began to interrogate these inherited narratives. Rather than rejecting myth outright, early philosophers asked what lay beneath it. If the sky followed patterns, perhaps those patterns reflected underlying principles rather than divine whim. This shift did not eliminate gods from the cosmos, but it reframed their role. The universe could be intelligible, governed by order that human reason might partially grasp. This philosophical turn is especially evident in ancient attempts to describe the cosmos as a system. The heavens were no longer merely a stage for divine drama, but a structured whole with parts that interacted according to discernible rules. Questions arose about substance and motion. What were the stars made of? Why did some celestial bodies wander while others remained fixed? Was the sky fundamentally different from the earth, or were they composed of the same stuff? Such questions marked a decisive change in human self-understanding. To ask whether the heavens obeyed laws was to imply that humans, through reason, could access truths beyond immediate experience. Knowledge was no longer solely revealed or inherited. It could be pursued. This pursuit was tentative and often speculative, but it represented a profound intellectual leap. Early astronomy developed within this philosophical context. It was not yet experimental science, but it was systematic. Observers tracked the movements of the sun, moon, and planets with increasing precision. They noticed regularities and anomalies, cycles and deviations. Over time, these observations accumulated into predictive frameworks. Calendars improved. Eclipses could be anticipated. The sky became a domain where future events could be known in advance, lending an aura of inevitability to celestial order. This predictability reinforced the idea that the cosmos was governed by reason rather than caprice. Even when celestial bodies were still considered divine, their behavior appeared constrained by rules. This tension between divinity and regularity is one of the defining features of early cosmological thought. The heavens were sacred, but they were also lawful. To study them was not to diminish their sanctity, but to participate in it. Different cultures resolved this tension in different ways. Some emphasized harmony, seeing the cosmos as a perfectly balanced whole in which every part had its place. Others emphasized struggle or renewal, imagining the heavens as arenas of cyclical conflict and rebirth. Yet across these variations, a shared assumption persists. The universe is meaningful, and its structure can be understood, at least in part, by the human mind. Crucially, early cosmologies were often anthropocentric, but not trivially so. Humanity was frequently placed at the center of the cosmos, not because of physical measurement, but because of existential significance. The Earth was central because it was the realm of experience, meaning, and moral action. This centrality was symbolic rather than spatial, though the two are often conflated. The idea that the Earth might not be physically central was difficult to accept because it seemed to undermine humanity's cosmic importance. Yet even within geocentric frameworks, there were hints of a broader universe. The notion that stars were distant suns, or that other realms might exist beyond the visible sky, appears repeatedly in ancient thought. These ideas were speculative and rarely dominant, but they demonstrate that the human imagination was not confined to a single closed cosmos. The sky invited expansion, even when philosophical systems resisted it. Early astronomical models often relied on geometry and idealized motion. Circles and spheres were favoured not because of empirical necessity, but because they symbolised perfection. The heavens, unlike the corruptible earth, were thought to embody eternal forms. This distinction between celestial and terrestrial realms shaped cosmology for centuries. The sky was perfect and unchanging, the earth imperfect and mutable. Yet the very act of tracking planetary irregularities challenged this dichotomy. Retrograde motion, variations in brightness, and other anomalies strained ideal models and demanded explanation. In responding to these challenges, early thinkers developed increasingly elaborate systems. These systems were not mere intellectual exercises, they were attempts to reconcile observation with deeply held metaphysical commitments. When data conflicted with expectation, interpretation was adjusted, often in creative ways. This process illustrates an important point. Pre-scientific cosmology was dynamic. It evolved in response to new observations, even if its foundational assumptions remained intact. The question of other worlds also surfaced within this milieu. If the cosmos was vast and ordered, was it reasonable to assume that Earth was unique? Some philosophical traditions entertained the possibility of multiple worlds, each governed by similar principles. Others rejected this idea, arguing that the cosmos was a single finite whole. These debates were not settled by evidence, but by metaphysical preference. Yet the very fact that they occurred indicates that the concept of plurality was thinkable long before it became testable. Myth, philosophy, and early astronomy thus formed a continuum rather than a sequence. Myth provided the initial framework, philosophy questioned and refined it, and astronomy anchored it in observation. None of these domains operated in isolation. Together, they sustained a worldview in which the cosmos was intelligible, inhabited, and significant. The sky was not an empty expanse, but a structured reality that invited interpretation. From a modern perspective, it is tempting to view these early systems as stepping stones towards science, valuable only insofar as they approximated later truths. This view misses their deeper significance. They represent humanity's first sustained engagement with cosmic scale and order. They trained minds to think beyond the immediate and to tolerate uncertainty. They fostered a sense of continuity between human life and the larger universe. In this pre-scientific era, the cosmos was not yet measured in distances or masses, but it was measured in meaning. The sky shaped calendars, rituals, and philosophies. It informed ideas of time, fate, and destiny. Even as later science would strip away many of these symbolic layers, the foundational questions they addressed would remain. What is the universe made of? How is it ordered? And what, if anything, lies beyond our world? These questions did not begin with instruments or experiments. They began with stories told beneath the stars, arguments held in shaded courtyards, and careful watching of the sky's slow, relentless motions. Long before science, humanity had already entered into a dialogue with the cosmos, a dialogue that would eventually transform both our understanding of the universe and our place within it. The transition from a sacred sky to a physical universe did not occur suddenly, nor did it involve a clean break with earlier ways of thinking. Instead, it unfolded gradually, through a long process in which symbolic meanings were reinterpreted, metaphysical assumptions were tested, and observation began to take precedence over authority. What changed was not humanity's fascination with the heavens, but the framework through which that fascination was expressed. The sky remained awe-inspiring, but it increasingly became something that could be analysed, modelled, and ultimately explained without recourse to divine intention. In early cosmologies, the sky's sacredness was inseparable from its mystery. Celestial motions were not merely regular, they were purposeful. Eclipses were omens, comets portents, and planetary conjunctions messages encoded in light. The heavens were not distant, they were engaged with human affairs. This intimacy made sense in a world where natural phenomena were understood relationally rather than mechanically. Events occurred because someone or something willed them to occur. To ask why was to ask who. Yet as records accumulated and comparisons became possible, patterns emerged that strained purely mythic interpretation. Eclipses, once feared as unpredictable intrusions, were found to recur according to cycles. Planetary motions, though complex, exhibited consistency over long periods. The same stars rose and set in the same seasonal rhythms year after year. These regularities suggested that the heavens were not responding to human actions or divine moods, but following their own internal logic. This realization did not immediately dissolve the sacred view of the sky. Instead, it transformed it. Order itself became sacred. The idea took hold that the cosmos was governed by principles that were stable, intelligible, and universal. Divinity, where it remained, was increasingly associated with these principles rather than with arbitrary intervention. The heavens were holy not because they were capricious, but because they were lawful. One of the most significant shifts in this process was the gradual separation of cosmology from theology. Early thinkers began to argue that understanding the structure of the universe did not require insight into divine motives. The question, how does the sky move, could be asked independently of, why does it exist? This distinction was subtle but revolutionary. It opened the door to explanations based on geometry, motion, and material properties rather than narrative intention. As this perspective gained ground, the sky began to be conceptualized as a space rather than a ceiling. Instead of a dome enclosing the Earth, the heavens became an expanse extending outward, populated by objects whose positions and movements could be charted. Stars were no longer fixed decorations embedded in a crystalline shell. They were points in a larger three-dimensional arrangement. This conceptual expansion did not require new instruments, only a willingness to reinterpret what was already seen. The idea that celestial bodies were physical entities similar in some respects to Earth marked another critical step. The moon, once a symbol or deity, began to be understood as a solid body with surface features. Its phases were explained not as transformations but as changes in illumination. Shadows, angles, and relative positions replaced mythic metamorphosis. The moon was still beautiful and mysterious, but it was no longer unknowable. This reimagining of the moon had profound implications. If the nearest celestial object was a physical world, perhaps the same was true of the planets. The wandering stars, long associated with gods and fate, could be reclassified as bodies moving through space according to consistent rules. Their apparent irregularities could be explained by relative motion rather than divine intent. What appeared chaotic from one perspective might be orderly from another. Such insights challenged deeply held assumptions about humanity's place in the cosmos. If the heavens were governed by the same principles everywhere, then Earth might not be unique. If celestial bodies were made of the same substance as terrestrial ones, then the boundary between sky and Earth was not absolute. The universe became continuous, rather than divided into fundamentally different realms. This continuity eroded the moral and metaphysical hierarchy that had long placed humanity at the center of creation. The Earth could still be significant, but its significance was no longer guaranteed by cosmic architecture. Instead, it had to be argued, defended, or redefined. This was unsettling, and resistance was inevitable. Sacred traditions were not easily abandoned, nor were they meant to be. They provided meaning that mechanical explanations could not replace. The tension between sacred interpretation and physical explanation shaped much of early cosmological thought. Rather than choosing one over the other, many thinkers attempted synthesis. The universe could be physical and still meaningful, lawful and still purposeful. Geometry could be divine. Motion could be sacred. In this view, studying the heavens was not an act of reduction, but of reverence. However, as explanatory models grew more precise, the balance shifted. Predictions based on physical principles proved reliable in ways that mythic interpretations could not match. When a model could anticipate an eclipse or explain a planetary anomaly without invoking supernatural causes, it gained authority. Over time, this authority accumulated, slowly displacing older frameworks not through confrontation, but through success. The emergence of a physical universe also altered the nature of cosmic questions. Instead of asking what the heavens signified, thinkers began to ask what they were made of. Substance replaced symbolism as the primary object of inquiry. Were the stars fiery, solid, or something else entirely? Did celestial bodies move because they were pushed, pulled, or carried? These questions demanded new concepts and new forms of reasoning. Importantly, the move toward physical explanation did not eliminate wonder. If anything, it intensified it. Understanding that the same principles governed both falling stones and moving planets revealed a unity that was intellectually exhilarating. The cosmos became a single system rather than a patchwork of domains. This unity suggested that the universe could, in principle, be understood as a whole. Yet this understanding came at a cost. As the sky became a physical universe, it also became more distant. Gods withdrew. Omens lost their immediacy. The heavens no longer spoke directly to human affairs. Meaning had to be sought elsewhere or reconstructed on new terms. For some, this was liberating. For others, it was disorienting. The shift also reframed humanity's relationship to knowledge. If the universe operated according to discoverable principles, then ignorance was no longer a permanent condition. It was a temporary state, to be remedied through observation, reasoning, and debate. This optimism was fragile, often interrupted by error and conflict, but it proved resilient. Crucially, the transformation from sacred sky to physical universe did not complete itself in antiquity. It remained incomplete, contested, and evolving. Sacred interpretations persisted alongside physical models for centuries, sometimes in harmony, sometimes in tension. Even today, traces of the sacred linger in the language of astronomy and cosmology. We still speak of heavens, of cosmic order, of awe inspired by the stars. What changed irreversibly was the assumption that the sky was beyond explanation. Once the heavens were admitted into the realm of physical inquiry, they could not be returned to pure mystery. The universe became something humanity could interrogate rather than merely endure. This change did not diminish the sky's power, it transformed it. In moving toward a physical universe, humanity did not abandon its ancient dream of other worlds. It reinterpreted it. Worlds were no longer realms of gods or spirits alone. They could be places governed by laws, potentially accessible in thought if not in practice. The question of what lay beyond Earth did not disappear with the sacred sky. It became sharper, more demanding, and ultimately more consequential. The heavens, once a divine canopy, had become an open expanse. The path from myth to mechanism was neither smooth nor final, but it marked a decisive reorientation of the human mind. Looking up was no longer only an act of reverence. It was an invitation to understand. Few ideas in human history have been as destabilizing as the realization that Earth is not the center of the universe. This was not merely a technical correction to astronomical models. It was a profound psychological and philosophical rupture. For millennia, humanity had understood its place in the cosmos through a framework that placed the Earth at the center of all motion and meaning. To remove that center was to unsettle assumptions about order, purpose, and human significance. The shock was not in the mathematics alone, but in what those mathematics implied. Before this turning point, the geocentric worldview felt intuitively correct. The Earth appeared still, solid, and immovable. The sky, by contrast, seemed to move around it in vast, graceful arcs. The sun rose and set. The stars wheeled overhead. The planets wandered against the stellar background. Everything visible to the senses reinforced the impression that Earth was the natural anchor of the cosmos. This view aligned seamlessly with philosophical and theological traditions that placed humanity at the focal point of creation. Centrality was not only physical, it was moral and metaphysical. When the heliocentric model was proposed, it challenged these assumptions at their root. The suggestion that Earth was in motion, spinning on its axis and circling the sun, contradicted direct experience. People did not feel the Earth move. Objects did not fly off its surface. The sky did not appear distorted by such motion. To accept this model required a radical act of trust in abstract reasoning over sensory intuition. It asked humanity to believe that appearances could be deceptive on a cosmic scale. This demand alone would have been unsettling, but the implications ran deeper. If Earth was not the center, then it was one planet among others. Its position was not privileged, but contingent. The sun itself, once thought to circle the Earth, became the gravitational anchor of a planetary system in which Earth was merely a participant. The cosmos expanded outward, and humanity's home shrank in relative importance. The resistance to this idea was therefore not simply conservative stubbornness. It reflected a genuine crisis of meaning. If Earth was not central, what guaranteed humanity's importance? If the heavens did not revolve around us, did they care about us at all? The Copernican shift threatened to transform the universe from a human-centered stage into an indifferent arena governed by impersonal laws. This crisis unfolded gradually. Early heliocentric ideas did not immediately overthrow older models. Instead, they competed with them, often coexisting uneasily. For a time, heliocentrism could be treated as a mathematical convenience rather than a literal description of reality. Calculations might be easier if the sun were placed at the center, but that did not mean it truly was. This compromise allowed thinkers to benefit from the new model without fully confronting its implications. Yet, as evidence accumulated and explanatory power grew, this compromise became harder to maintain. The heliocentric model explained planetary motions with a coherence that geocentrism increasingly lacked. Retrograde motion, long a puzzle, emerged naturally from relative movement rather than requiring elaborate geometrical constructions. Simplicity became an argument in itself. The universe, it seemed, made more sense when Earth was not its anchor. Accepting this new arrangement required a redefinition of motion and rest. Earth was no longer the fixed reference point. It was a moving body subject to the same principles as other planets. This realization eroded the sharp boundary between the heavens and the Earth. The same forces that governed celestial motion applied to terrestrial objects. The universe was unified not only in structure, but in behavior. The psychological impact of this unification was profound. Humanity lost its cosmic pedestal. The Earth became one world among many, orbiting an ordinary star in a vast expanse. This was not merely a loss of status, it was a loss of certainty. The cosmos was no longer arranged around human needs or narratives. It existed on scales of space and time that dwarfed human experience. This displacement triggered what might be called a cosmic humility. The universe no longer appeared tailored to human presence. Instead, humanity appeared as a latecomer, inhabiting a small planet in a system that had existed long before humans and would persist long after. For some, this realization was liberating, freeing thought from parochial constraints. For others, it was deeply unsettling, stripping the cosmos of its apparent concern for human affairs. Importantly, losing the center did not mean losing all meaning. It forced a re-evaluation of where meaning resides. If humanity was not central by default, perhaps significance had to be constructed rather than assumed. The universe might not confer purpose, but it did not forbid it either. This shift placed greater responsibility on human thought and culture to define values in a cosmos that no longer revolved around them. The Copernican shock also reshaped the question of other worlds. If Earth was not unique in its position, might it not be unique in other respects as well? The idea that other planets could be worlds, places rather than mere lights, became increasingly plausible. Once Earth was recognized as a planet, the category expanded. Planets were no longer abstract points of light, they were potential landscapes. This expansion had far-reaching consequences. The universe became populated with possibilities. Other planets might have their own histories, their own conditions, perhaps even their own forms of life. The question of other worlds shifted from mythic speculation to philosophical conjecture, grounded in physical analogy. If the same laws applied everywhere, why should Earth alone host complexity? At the same time, the loss of centrality intensified the desire to understand. If humanity occupied no privileged position, then knowledge itself became a way to reclaim significance. Understanding the cosmos was no longer a passive reception of meaning, but an active pursuit. The human mind, though small in scale, proved capable of grasping structures vastly larger than itself. This capacity became a new source of pride, replacing the older comfort of central placement. The Copernican shift also introduced a new kind of uncertainty. If Earth was not central, then there was no obvious frame of reference from which to define absolute position. Motion became relative. Perspective mattered. The universe no longer had a single, obvious orientation. This relativization of viewpoint would echo through later developments in science and philosophy, reinforcing the idea that knowledge is shaped by the observer's position as well as by the observed reality. Despite its revolutionary nature, the Copernican model did not immediately banish older intuitions. Cultural and religious traditions adapted, reinterpreting centrality in symbolic rather than spatial terms. Humanity could still be central in moral or spiritual significance, even if it was not physically central. This adaptation softened the shock but did not erase it. The universe had been irreversibly decentered. Over time, the initial trauma gave way to a new sense of scale. The cosmos expanded in imagination as well as in measurement. The sky was no longer a nearby shell, but a vast arena of motion extending far beyond immediate perception. Earth became a traveller rather than a throne, a participant rather than a pivot. This reorientation did not end humanity's ancient dream of other worlds, it intensified it. By losing the centre, Earth gained company. The cosmos became a place where multiple worlds could exist, each following its own path around a star. The question was no longer whether Earth was unique by design, but whether it was unique at all. The Copernican shock thus marked a turning point not only in astronomy, but in human self-understanding. It forced humanity to confront the possibility that it was not the focal point of creation, and to find meaning in that realization rather than in spite of it. The loss of the center was painful, but it was also productive. It opened the universe, inviting inquiry, comparison, and humility. In decentering Earth, the cosmos became larger, colder, and more indifferent, but also richer in possibility. The sky no longer revolved around humanity, but humanity could now move, intellectually and imaginatively, through the sky. That movement would define the next chapters of cosmic exploration. Once the Earth lost its privileged position at the center of the cosmos, a new question emerged with unexpected force. If our world is not central, then what makes it matter? This question is not trivial, nor is it merely academic. It reaches into the foundations of how humanity understands itself, its future, and its responsibilities. The idea of other worlds, real physical places beyond Earth, forces a reassessment of uniqueness, value, and meaning in a universe that no longer appears designed around human presence. At first glance, the existence of other worlds might seem to diminish Earth's importance. If planets are common, if stars are innumerable, then our home could appear replaceable, even insignificant. This fear has accompanied every major expansion of cosmic scale. Each time humanity has discovered that it occupies a smaller portion of reality than previously believed, anxiety has followed. Yet history suggests that expansion does not erase meaning, it relocates it. Other worlds matter because they provide context. Without comparison, Earth appears singular by default. With comparison, its properties become intelligible. The presence of other planets transforms Earth from a cosmic exception into a case study. We begin to see which features of our world are common outcomes of physical processes and which are rare accidents. Atmospheres, oceans, magnetic fields, climates, these are no longer givens but variables. Earth's habitability becomes something to be explained rather than assumed. This shift has profound consequences. Consider water. On Earth, liquid water feels inevitable, woven into every aspect of life. But the search for other worlds reveals how fragile and conditional this presence is. Water requires precise balances of temperature, pressure, and chemistry. On some worlds it freezes permanently. On others it boils away. On still others it may exist only beneath ice or within rock. Understanding these variations reframes Earth's oceans not as background scenery, but as remarkable achievements of circumstance. In this sense, other worlds sharpen appreciation rather than dull it. They reveal how many ways a planet can fail to become Earth-like. Barren surfaces, toxic atmospheres, runaway climates, these outcomes appear to be common. Against this backdrop, Earth's stability stands out. Life's persistence here no longer seems guaranteed by cosmic benevolence, but sustained by a delicate interplay of conditions that could easily have unfolded differently. Other worlds also matter because they test the universality of natural laws. If the same physical principles operate everywhere, then planets beyond Earth become laboratories where those principles play out under different initial conditions. Studying them allows humanity to distinguish what is fundamental from what is contingent. Gravity, chemistry, and thermodynamics are constant. landscapes and climates are not. This distinction deepens scientific understanding while reinforcing the unity of the universe. At a deeper level, the existence of other worlds reshapes the question of life itself. For most of human history, life was assumed to be a local phenomenon, confined to Earth by default. The recognition that planets are physical worlds governed by shared laws makes this assumption increasingly untenable. If life emerged here through natural processes, then it may emerge elsewhere under similar conditions. The question shifts from, is life unique, to how common is it? This shift carries philosophical weight. If life exists elsewhere, then humanity is not the sole expression of biological complexity in the universe. Intelligence, culture, and consciousness may not be cosmic anomalies. Even if life elsewhere is simple or rare, the mere possibility expands the narrative of existence beyond a single planet. Earth becomes part of a larger story rather than the entire story. Yet even if Earth were the only inhabited world, other worlds would still matter. They would define the boundaries of life's rarity and resilience. A universe filled with sterile planets would make Earth extraordinary in a different way. Not as the center of creation, but as an improbable oasis. Either outcome carries significance. Other worlds are not competitors for meaning. They are mirrors in which Earth's significance is clarified. There is also a temporal dimension to why other worlds matter. Earth is not static. Its climate, geology, and biosphere have changed dramatically over time, and they will continue to change. Studying other planets reveals possible futures as well as alternate presents. Worlds that lost their atmospheres or suffered climatic collapse serve as cautionary examples. They show that planetary environments can degrade irreversibly, and that stability is not guaranteed by inertia alone. In this context, other worlds become warnings as much as wonders. They demonstrate that planets can cross thresholds beyond which recovery is impossible. This perspective reframes Earth not as a permanent home, but as a temporary condition, one that requires stewardship if it is to persist. The value of Earth is heightened, not diminished, by the recognition that many planets do not share its resilience. Other worlds also expand humanity's sense of possibility. For much of history, the sky was a boundary, a limit beyond which imagination could roam, but bodies could not. As worlds became understood as physical places, that boundary softened. The idea that planets are destinations rather than abstractions alters the long-term horizon of human ambition. Even if interplanetary travel remains difficult or distant, the conceptual shift matters. Humanity is no longer confined in principle to a single world. This expansion of horizon influences culture as much as science. Art, literature, and philosophy absorb the idea of other worlds and reflect it back in new forms. Narratives of exploration, encounter, and comparison proliferate. The human story extends outward, no longer bound exclusively to terrestrial concerns. Other worlds become canvases on which hopes, fears, and questions about identity are projected and examined. At the same time, the existence of other worlds tempers anthropocentrism. It challenges the assumption that human experience defines the norm. Conditions that seem essential from a terrestrial perspective, day-night cycles, familiar gravity, breathable air, are revealed as local adaptations rather than universal standards. This relativization fosters intellectual humility. Humanity becomes one expression of cosmic possibility rather than its measure. Importantly, other worlds matter even before they are visited or fully understood. Their significance does not depend on immediate utility. They matter because they alter perspective. They stretch imagination beyond inherited limits. They force humanity to confront scales of space and time that resist intuitive comprehension. In doing so, they cultivate a kind of maturity, a willingness to accept that meaning must coexist with vastness. There is also an ethical dimension to this awareness. Recognizing that Earth is one world among many does not license neglect. It intensifies responsibility. If life is rare, Earth is precious. If life is common, Earth is still our only known home. Other worlds may offer insight or inspiration, but they do not absolve humanity of care for its own planet. On the contrary, they underscore how difficult it is for a world to sustain life at all. Other worlds matter because they anchor humanity's cosmic curiosity in reality. They transform ancient speculation into testable inquiry. They bridge mythic longing and scientific investigation. The dream of other worlds is no longer confined to imagination. It is grounded in observation and theory. This grounding does not end wonder. It gives it direction. Ultimately, the importance of other worlds lies in what they reveal about Earth and about ourselves. They expose assumptions, refine questions, and broaden perspective. They remind humanity that meaning is not bestowed by central placement, but constructed through understanding, care, and curiosity. Earth matters not because it is the only world, but because it is our world, understood more deeply in light of all the worlds that are not like it. In recognizing other worlds, humanity does not lose itself. It finds a larger context in which to situate its story. The universe becomes more complex, more demanding, and more honest. And within that expanded universe, Earth's value is not erased. It is illuminated. Once the universe was understood as vast, physical, and governed by laws rather than intentions, humanity faced a new limitation. The senses that had carried us from myth to philosophy were no longer sufficient. Eyes that could track stars and planets across the naked sky could not resolve distant worlds. Hands that could shape tools and monuments could not reach beyond Earth. If other worlds were to be known as more than abstractions, humanity would need new ways of seeing, hearing, and measuring. Extensions of perception capable of operating far beyond the limits of biology. Machines became those extensions. They did not replace human curiosity, they amplified it. Telescopes, detectors, and later spacecraft functioned as prosthetic senses, allowing humanity to experience parts of the universe that would otherwise remain forever inaccessible. Through them, the cosmos ceased to be a distant spectacle and became an environment that could be interrogated, mapped, and compared. This transformation was not merely technical, it altered the nature of knowledge itself. For most of human history, understanding the sky meant interpreting what could be directly observed. Patterns were inferred from repeated visual experience. Even philosophical speculation remained tethered to what the unaided senses could plausibly imagine. Machines severed that tether. They allowed information to be gathered in forms no human sense could directly register. Radiation invisible to the eye, particles too small to feel, distances too vast to intuit. The first mechanical aids to perception were simple in concept but profound in consequence. Optical instruments gathered light over larger areas and focused it more precisely than the human eye could manage. Suddenly, faint objects became visible. Details once blurred into insignificance emerged with clarity. The sky, previously experienced as a smooth dome, fractured into layers and depths. Stars multiplied. Nebulous patches resolved into structured forms. The universe grew larger and more complex with every improvement in instrumentation. Crucially, these machines did not merely show more, they showed differently. The human eye evolved to operate within a narrow band of conditions optimized for survival on Earth. It sees a limited range of light and interprets it according to neurological shortcuts shaped by evolution. Instruments, by contrast, are indifferent to comfort and familiarity. They register what is there, not what is convenient to perceive. This indifference is their power. As new detectors came into use, humanity discovered that most of the universe is invisible to natural vision. Vast amounts of information arrive at Earth in forms that pass through us unnoticed. Machines revealed these hidden dimensions, exposing processes that would otherwise remain theoretical. The cosmos turned out to be far more active, violent, and dynamic than the serene night sky suggested. Stars were born and died in obscured regions. Energetic events reshaped entire systems. The universe was not a static backdrop, but a restless arena. These revelations forced a re-evaluation of what it meant to see. Observation was no longer synonymous with looking. It became an act of interpretation mediated by instruments, calibration, and models. Data replaced direct sensation. The human role shifted from observer to analyst, from witness to interpreter. Understanding now required trust, not in authority or tradition, but in chains of reasoning that linked machine output to physical reality. This shift introduced new challenges. Machines do not speak in images or narratives, they produce signals. Raw data must be processed, filtered, and translated into forms the human mind can grasp. Every step introduces assumptions. Every instrument has limits and biases. Knowing the universe through machines requires not only technical skill, but epistemological caution. What we see is shaped by how we choose to look. Yet despite these challenges, machine-mediated perception proved remarkably reliable. Predictions based on instrument data consistently matched future observations. Models built from indirect measurements yielded accurate forecasts. Confidence grew not because machines were infallible, but because their errors were detectable and correctable. Unlike myth or intuition, instrumental knowledge could be tested against itself. As machines extended humanity's reach outward, they also extended it inward. Instruments capable of measuring minute variations revealed subtleties previously overlooked. Planetary motions were tracked with extraordinary precision. Atmospheric compositions could be inferred from faint signatures. Surfaces could be analysed from afar. Other worlds ceased to be mere points of light and became environments with histories and properties. The emergence of robotic exploration marked a further evolution in perception. Machines were no longer confined to observing from afar. They could travel. Sensors were carried to distant places, gathering data in situ. Temperature, pressure, chemistry, and texture could be measured directly on other worlds. Humanity's senses were no longer limited to Earth's surface. They were distributed across space. This distribution had profound psychological effects. Images returned from distant environments created a sense of presence. Landscapes light years away or millions of kilometers distant felt tangible. The emotional impact of seeing another world's surface cannot be overstated. It transformed abstract possibility into lived experience, mediated though it was by machinery. Humanity could now say, with justification, that it had touched other worlds through its instruments. At the same time, machines imposed a new kind of humility. They revealed how little could be known without assistance. They exposed the narrowness of natural perception. They reminded humanity that intuition is a poor guide at extreme scales. The universe does not conform to human expectations. It must be met on its own terms. Machines make that meeting possible. Importantly, these instruments did not eliminate the role of imagination. On the contrary, they demanded it. Interpreting data requires conceptual frameworks that often precede direct confirmation. Machines deliver measurements, not meaning. Humans must supply the latter. Hypotheses, models, and analogies remain essential. The difference is that imagination is now constrained by evidence rather than freed from it. Machines also democratized cosmic knowledge in unexpected ways. Data gathered by instruments could be shared, replicated, and reanalyzed. Observations were no longer tied to individual observers or isolated traditions. Knowledge became collective, cumulative, and self-correcting. The cosmos became a shared object of inquiry rather than a private vision. Yet reliance on machines also introduced dependence. As instruments grew more complex, fewer individuals could fully understand their inner workings. Trust shifted from personal experience to institutional processes. This shift raised questions about authority and interpretation. Who speaks for the machines? How are uncertainties communicated? These questions remain unresolved, but they reflect a deeper truth. Extending perception changes not only what is known, but how knowledge is organized. Despite these complexities, machines remain humanity's most powerful allies in cosmic exploration. They allow us to transcend biological constraints without abandoning human judgment. They make the invisible visible and the distant immediate. Through them, other worlds move from speculation to comparison, from myth to measurement. In a deeper sense, machines embody the continuation of humanity's oldest impulse, to look beyond the immediate horizon. Stone circles aligned to the sky were early instruments. Calendars carved into bone were early data records. Modern detectors and probes are heirs to that same tradition. The tools have changed, but the desire has not. Machines are not neutral intermediaries. They shape the questions we ask and the answers we accept. They privilege certain kinds of information over others. Yet this shaping is not a flaw, it is a feature of all inquiry. Awareness of mediation does not invalidate knowledge, it refines it. As humanity's senses extend farther into space, the universe becomes both more alien and more familiar. Other worlds are revealed as governed by the same laws that shape Earth, yet expressed in unfamiliar forms. Machines allow us to hold both truths at once. They show continuity without erasing difference. In the end, machines do not diminish the human role in cosmic understanding. They redefine it. The universe is no longer something humanity merely looks at. It is something humanity engages with through tools, models, and shared interpretation. Our senses have become distributed, our perspective expanded. Through machines, the ancient act of looking up has become an act of reaching out. The sky is no longer only overhead, it is within reach of our instruments and our minds. Other worlds, once imagined, now enter human experience through streams of data and images. The cosmos has not grown smaller, but humanity's capacity to know it has grown larger. The limits of earthbound vision. For all the power of human curiosity and ingenuity, the sky as seen from Earth imposes strict and often invisible limits. Long before the first spacecraft left the planet, astronomers confronted a paradox. The universe invited study, yet persistently resisted clarity. The problem was not intelligence or effort, but location. Earthbound vision is constrained by the very environment that makes life possible. Air, water, gravity, and light, conditions that sustain human existence, also distort, absorb, and conceal much of the cosmos. To the naked eye, the night sky appears crisp and serene. Stars seem fixed, their light steady and reliable. This apparent stability is an illusion born of scale and distance. In reality, the atmosphere through which starlight passes is in constant motion. Layers of air with different temperatures and densities bend light unpredictably, causing stars to shimmer and blur. This effect, familiar as twinkling, is a subtle reminder that Earth's atmosphere is not a passive window, but an active medium that reshapes what we see. Early observers learned to live with these distortions. They trained their eyes, waited patiently for moments of stillness, and recorded what they could. Over centuries, this discipline produced remarkable achievements. Planetary motions were charted, eclipses predicted, and celestial cycles mapped with impressive accuracy. Yet there were boundaries that no amount of patience could overcome. Certain details remained forever out of reach, smeared by turbulence or drowned in background glow. The atmosphere does more than blur images. It blocks entire categories of information. Most of the radiation emitted by celestial objects never reaches the ground. Invisible wavelengths are absorbed high above the surface, filtered out by layers of gas that protect life from harmful exposure. What reaches the human eye is a narrow slice of a much broader spectrum. For millennia, humanity studied the universe through a keyhole, unaware of how much lay beyond. This limitation shaped cosmological understanding in subtle ways. The universe appeared quieter, cooler, and more orderly than it truly is. Violent events unfolding in distant regions left little trace in visible light. Processes hidden within clouds of gas and dust remained unseen. Whole classes of objects escaped detection entirely. Earthbound vision favoured surfaces over interiors, brightness over energy, and proximity over power. Light pollution added another layer of constraint. As human settlements grew, artificial illumination spilled upward, washing out faint celestial features. The Milky Way, once a dominant presence in the night sky, faded from view for much of the world's population. Urban observers inherited a diminished cosmos, stripped of depth and nuance. This loss was not merely aesthetic, it narrowed awareness of the universe's richness and scale. Even in ideal conditions, high mountains, dry air, dark skies, earthbound observation faced fundamental obstacles. Distance weakens signals. Light spreads out as it travels, growing fainter with every passing unit of space. Objects of immense size and energy can appear as dim points when viewed from afar. Telescopes can gather more light, but they cannot change the basic geometry of radiation. At some point, faintness overwhelms resolution. Resolution itself presents another constraint. The ability to distinguish fine detail depends not only on instrument size, but on environmental stability. On Earth, atmospheric turbulence imposes a ceiling on clarity. No matter how perfect the optics, moving air smears incoming light. Adaptive techniques can compensate to some degree, but they are complex and imperfect. For generations, astronomers were forced to accept that certain scales were simply inaccessible from the ground. These constraints influenced the kinds of questions that could be asked. Early astronomy focused on motion, position, and timing, properties that could be measured despite blurring and absorption. Questions about composition, structure, and internal processes were harder to pursue. The universe became a geometry of points and paths rather than a chemistry of substances. This emphasis shaped theories, privileging kinematics over physics. The limits of earthbound vision also encouraged speculative excess. When details could not be resolved, imagination filled the gaps. Blurred features were interpreted according to expectation and desire. Linear patterns appeared where none existed. Surface markings took on meanings they could not support. The boundary between observation and interpretation blurred alongside the images themselves. Some of the most enduring misconceptions about other worlds arose from this interplay between inadequate data and powerful imagination. At the same time, these limits fostered humility and discipline. Astronomers learned to doubt first impressions and to value consistency over drama. Repeated observation became a safeguard against illusion. Careful comparison across time and location helped separate real features from transient artifacts. The difficulty of earthbound vision cultivated methodological rigor, laying the groundwork for later advances. Yet no amount of rigor could overcome certain barriers. The atmosphere remained an obstacle, not an ally. Gravity anchored instruments to the ground, restricting vantage points. Day and night cycles interrupted observation. Weather intervened unpredictably. Entire regions of the sky were inaccessible from any given location. Earth itself imposed a partial, uneven view of the cosmos. These constraints gradually shifted expectations. Astronomers came to recognize that some questions could not be answered from Earth alone. Understanding the universe would require new perspectives, literally. This recognition did not arise from failure, but from success. As knowledge deepened, its boundaries became more apparent. Each improvement in earthbound observation revealed not only new details but new absences. The realization that most cosmic information never reaches the ground was particularly transformative. The universe emits across a vast range of energies, from gentle waves to violent bursts. Earth's atmosphere, while life-saving, is opaque to much of this radiation. To remain on the surface was to remain partially blind. The sky seen from Earth was not the universe as it is, but the universe as filtered for biological survival. This insight reframed the relationship between astronomy and technology. Instruments were no longer mere enhancements of sight. They were compensations for environmental loss. To see more of the universe, humanity would need to escape its protective cocoon. The atmosphere, once regarded as a neutral backdrop, became a barrier to be circumvented rather than endured. Importantly, this shift did not imply dissatisfaction with Earth or its conditions. The atmosphere's opacity is a feature, not a flaw, from a biological perspective. It shields life from radiation that would otherwise be lethal. The very invisibility of much of the cosmos is a consequence of Earth's habitability. Recognizing this connection deepened appreciation for the planet, even as it motivated exploration beyond it. The limits of earthbound vision also underscored the contingency of human knowledge. What we know depends on where we stand. Perspective shapes discovery. Had humanity evolved under different conditions, on a thinner atmosphere or none at all, cosmic understanding might have followed a different path. Knowledge is not only cumulative, it is situated. This realization carries philosophical weight. It suggests that ignorance is not always a failure of intellect, but a function of position. To know more, one must sometimes move. In this sense, astronomy became a science of displacement. Understanding the universe required leaving the surface that nurtured human life. The desire to transcend earthbound limits was not escapism, it was epistemological necessity. The recognition of these limits did not diminish the achievements of ground-based astronomy. On the contrary, it highlighted their ingenuity. Working within constraints sharpened technique and theory. Earthbound observation achieved extraordinary precision despite its handicaps. Yet its ultimate contribution may have been to reveal what it could not do. By exposing the boundaries of vision, astronomers clarified the next step. The universe could not be fully known from below. To see clearly, humanity would need to rise above the distortions, beyond the absorptions, and outside the gravitational well that anchored instruments to a single vantage point. The sky, long observed from the ground, would have to be approached from within. The limits of earthbound vision thus became a catalyst rather than a conclusion. They marked the end of one era of cosmic observation and the beginning of another. The question was no longer whether the universe could be understood, but how far humanity was willing to go to understand it. The answer would come not from sharper eyes alone, but from leaving the ground entirely. The moment humanity learned to record light rather than merely observe it, the universe began to change. Photography transformed astronomy from an art of trained perception into a science of accumulated evidence. Where the eye was fleeting and subjective, photographic plates were patient and impartial. They gathered light over minutes, hours, even nights, revealing objects and details no human observer could ever hope to see unaided. In doing so, they quietly ended an era dominated by visual impression and ushered in a new age of remote worlds made real through data. The earliest astronomical photographs were crude by modern standards, yet revolutionary in effect. For the first time, the sky could be frozen in time. Subtle features no longer depended on momentary clarity or individual skill. A plate could be examined, re-examined, and shared. Disagreements could be settled not by authority or reputation, but by reference to a physical record. Astronomy became cumulative in a new way, building a permanent archive of the heavens. Photography also introduced a new kind of patience into observation. Long exposures allowed faint objects to emerge gradually from darkness. Light that arrived one photon at a time could be gathered until it became visible. This capacity dramatically expanded the observable universe. Nebulous patches resolved into structured forms. Star fields multiplied. Objects once thought to be empty regions revealed unexpected complexity. The sky, long perceived as sparse, proved to be crowded. This expansion altered humanity's conception of other worlds. Planets and stars were no longer isolated curiosities, but members of vast populations. Photography revealed that the Milky Way was not a smooth glow, but a dense assembly of individual stars. What had seemed like background texture was, in fact, structure on an immense scale. The universe grew not only larger, but richer. Yet photography alone could not answer the most pressing questions about these distant objects. Recording light captured appearance, not composition. Knowing how bright or extended something was did not explain what it was made of or how it worked. To move beyond surface impressions, astronomers needed a way to analyze light itself. That method came through spectroscopy. When light is spread out into its component wavelengths, it carries a detailed record of its origin. Different elements absorb and emit light in characteristic patterns. By studying these patterns, astronomers could determine the composition of objects far beyond physical reach. This was a conceptual leap of enormous consequence. For the first time, humanity could know the chemistry of distant worlds without touching them. Spectroscopy revealed a startling continuity between Earth and sky. The same elements found in terrestrial laboratories appeared in the spectra of stars and planets. Iron, hydrogen, calcium, substances familiar from daily life, were present across the cosmos. This discovery collapsed the ancient division between celestial and terrestrial matter. The heavens were no longer composed of a unique, divine substance. They were made of the same ingredients as Earth. This realization fundamentally reframed the idea of other worlds. If distant bodies shared Earth's chemistry, then they were not symbolic realms but physical places. They obeyed the same laws and were subject to the same processes. The universe became a coherent system rather than a collection of disconnected domains. Worlds elsewhere were no longer merely conceivable, they were relatable. Spectroscopy also revealed motion in a new way. Subtle shifts in spectral lines indicated movement toward or away from the observer. These shifts could be measured with extraordinary precision, far exceeding what visual tracking allowed. The universe became dynamic on scales previously invisible. Stars moved. Systems evolved. Motion was no longer inferred indirectly, it was measured directly through light. Through this combination of photography and spectroscopy, the first truly remote worlds came into focus, not as imagined landscapes, but as characterized objects. Planets could be distinguished from stars, not only by position, but by physical properties. Atmospheres could be inferred, temperatures estimated, surfaces hinted at through reflected light. Even without leaving Earth, humanity began to assemble portraits of places it could never visit directly. Importantly, these techniques also disciplined imagination. Where earlier observers had filled blurred details with expectation, photographic and spectral evidence constrained interpretation. Features either appeared on plates or they did not. Chemical signatures either matched known patterns or they did not. Speculation increasingly had to answer to data. This did not eliminate error, but it changed its nature. Mistakes became technical rather than mythic, corrigible rather than entrenched. Photography further introduced a new relationship to time. Plates could be compared across years or decades, revealing change where none was expected. Variable stars brightened and dimmed. Explosive events flared and faded. The sky, once assumed to be largely static, proved to be alive with transformation. Worlds were not frozen in perfection. They evolved, aged, and sometimes died. This temporal dimension reinforced the sense that other worlds had histories. They were not eternal symbols, but participants in cosmic processes. Planets cooled. Stars burned fuel. Systems formed and dispersed. Time entered astronomy, not merely as a measure of cycles, but as an agent of change. The universe became a story rather than a tableau. At the same time, spectroscopy introduced an unsettling distance. Knowing the composition of a star did not bring it closer in any physical sense. Remote knowledge expanded, but physical separation remained absolute. This tension, between intimacy of understanding and remoteness of location, became a defining feature of modern astronomy. Humanity could know much about distant worlds without ever approaching them. This paradox reshaped expectations. It demonstrated that exploration did not require presence, at least not initially. Information could precede contact. Worlds could be mapped in principle before they were ever visited in fact. This insight laid the conceptual groundwork for later space exploration. Machines would go where bodies could not, guided by knowledge gathered from afar. Photography and spectroscopy also democratized astronomy in unexpected ways. Data could be shared widely. Observations made in one place could be analyzed elsewhere. Knowledge became less dependent on individual observers and more on collective interpretation. Astronomy began to resemble a global enterprise, united by common datasets and methods rather than local tradition. Yet these methods had limits. They depended on light reaching Earth, and light could be blocked, distorted, or overwhelmed. Dust obscured regions of space. Bright objects drowned out faint companions. Atmospheric absorption still filtered signals. Despite dramatic progress, Earthbound remote sensing remained incomplete. Some worlds hinted at their existence only indirectly, leaving tantalizing gaps in understanding. These gaps, however, were productive. They sharpened questions and exposed the inadequacy of existing tools. Photography and spectroscopy revealed just enough to make their own limitations apparent. Knowing that a planet existed was not the same as knowing its surface. Detecting an atmosphere did not reveal its dynamics. The desire to move from inference to direct measurement grew steadily. Crucially, the success of these techniques validated a radical idea. Physical knowledge could be obtained without physical contact. This principle would become foundational for space exploration. Spacecraft would later carry instruments that extended these same methods outward, performing photography and spectroscopy not from Earth, but from orbit and beyond. The techniques that first revealed remote worlds would become the backbone of their direct exploration. In hindsight, photography and spectroscopy occupy a pivotal place in the story of cosmic discovery. They represent the bridge between seeing and understanding, between speculation and measurement. They transformed other worlds from points of light into objects of study, endowed with properties that could be catalogued and compared. Through them, the universe became both more distant and more familiar. More distant because its scale and complexity exceeded previous imagination. More familiar because its constituents obeyed the same rules everywhere. The cosmos was no longer a mystery to be contemplated from below, but a system that could be investigated, piece by piece, through disciplined use of light. These techniques did not end humanity's longing to reach other worlds. They intensified it. By revealing what could be known from afar, they made clear what remained unknown. The gap between observation and presence became visible, and with it arose a new ambition, to move beyond remote sensing and into direct encounter. Photography and spectra opened the door. What lay beyond it would require a more radical step, leaving Earth entirely. The leap from observing distant worlds to reaching toward them did not arise from pure curiosity. It emerged from a convergence of ambition, conflict, and technological necessity. Spaceflight was born not in the quiet halls of observatories, but in an era defined by global tension and unprecedented mobilization of scientific talent. The same forces that drove humanity to develop weapons of immense destructive power also provided the means to escape Earth's gravitational grip. This paradox lies at the heart of modern space exploration. Rockets, in their simplest form, are ancient devices. The principle of propulsion by reaction was understood long before it was refined. Early rockets were used for signaling, ceremony, and warfare, valued more for spectacle than precision. For centuries, they remained curiosities, impressive but unreliable, incapable of sustained control or significant payloads. The dream of using rockets to reach beyond Earth existed largely in imagination, detached from practical possibility. What changed was not the basic idea, but the scale and rigor applied to it. Industrialization provided new materials, more precise manufacturing, and a growing understanding of physics. Rockets began to be treated not as novelties, but as engineering systems. Their behavior could be predicted, refined, and improved. Still, without compelling motivation, progress remained incremental. It was war that supplied both urgency and resources. Global conflict transformed rocketry from a speculative pursuit into a strategic priority. Nations invested heavily in technologies that promised range, speed, and deterrence. Rockets offered something unprecedented: the ability to deliver payloads across vast distances without reliance on traditional transport. This military imperative accelerated research at a pace no peaceful program could have matched. Problems that might have taken decades to solve were addressed in years. In this environment, rocketry matured rapidly. Propulsion systems became more powerful and reliable. Guidance mechanisms improved, allowing for controlled trajectories rather than blind arcs. Structures were optimized to withstand stress while minimizing weight. Each improvement was driven by practical demands, yet each also brought spaceflight closer to feasibility. The boundary between weapon and vehicle grew thinner. The end of major global conflict did not end this momentum. Instead, it redirected it. Technologies developed for warfare were repurposed for exploration. Engineers and scientists who had worked under military pressure found themselves with tools capable of unprecedented reach. The question shifted from how far a rocket could carry a weapon to how far it could carry an instrument. This transition was not automatic or inevitable. It required a reimagining of purpose. Rockets, once symbols of destruction, were reframed as instruments of discovery. This reframing was facilitated by a broader cultural shift. After years of devastation, there was a desire to channel technological power toward constructive ends. Space offered a domain where competition could be sublimated into achievement and where national pride could be expressed without immediate harm. The physics that made rockets effective weapons also made them ideal for leaving Earth. To reach orbit or escape the planet's gravitational influence, a vehicle must achieve extraordinary speed. This requirement is unforgiving. There is no gradual ascent to space. There is only the threshold beyond which gravity loses its hold. Rockets are uniquely suited to this task because they carry both fuel and oxidizer, allowing them to operate where air cannot. Understanding this requirement clarified why earlier dreams of spaceflight had remained unrealized. Balloons and aircraft, dependent on atmosphere, could not reach the necessary velocities. Only a device capable of sustained acceleration in vacuum could succeed. War-driven rocketry provided exactly that capability, albeit developed for different ends. As rockets grew more powerful, the idea of placing objects into orbit moved from speculation to calculation. The mathematics of orbital motion had long been understood in principle. What was missing was the means to achieve it. Once rockets could deliver sufficient speed, orbit became an engineering problem rather than a conceptual one. The sky was no longer an unreachable ceiling. It was a region that could be entered and occupied. The first ventures into space were modest by later standards. Instruments were simple, lifetimes brief, and control limited. Yet their significance was enormous. For the first time, machines left Earth entirely, carrying sensors beyond the atmosphere and returning data unfiltered by air or gravity. The universe, previously observed through layers of distortion, could now be sampled directly. These early flights revealed just how transformative space access would be. Measurements taken above the atmosphere differed markedly from those taken below. Radiation levels were higher. The sky was darker. Signals were clearer. Phenomena invisible from the ground became obvious. The decision to leave Earth's surface was vindicated almost immediately. Space was not merely an extension of terrestrial observation, it was a fundamentally different vantage point. At the same time, these achievements underscored the risks and costs involved. Rockets are unforgiving machines. They operate at the edge of material limits, balancing immense forces within narrow tolerances. Failures were frequent and often catastrophic. Progress came through trial, error, and loss. Each success rested on a foundation of previous mistakes. Spaceflight demanded a tolerance for risk that few other scientific endeavors required. This reality reinforced the initial reliance on machines rather than people. Human life was too fragile, too valuable to be placed atop unproven systems. Instruments could fail without tragedy. Data could be lost without mourning. The early era of spaceflight was necessarily robotic, not out of philosophical preference, but out of pragmatic caution. The militarized origins of spaceflight also shaped its early culture. Programs were hierarchical, secretive, and driven by competition. Space became a new arena in which geopolitical rivalries played out. Achievements were measured not only in scientific return, but in symbolic value. Being first mattered. Reaching farther mattered. Visibility and prestige were intertwined with discovery. Yet within this competitive framework, a more universal perspective began to emerge. Images and data returned from space did not respect national boundaries. The view of Earth from above, fragile and unified, challenged the narratives that had driven conflict. Spaceflight, born of war, began to offer a perspective that transcended it. This irony is central to its legacy. Technically, the development of spaceflight marked a decisive break from all previous exploration. Unlike ships or caravans, rockets could not be recalled once launched. They followed trajectories determined at ignition. This irreversibility demanded unprecedented precision and planning. Exploration became an exercise in foresight rather than adaptation. Every decision had to be made in advance, every contingency anticipated. This requirement transformed the nature of exploration itself. It shifted emphasis from improvisation to simulation, from experience to modeling. Space missions were planned in abstract spaces of equations and diagrams long before hardware was built. The journey occurred first in thought, then in metal and flame. This inversion would define space exploration for decades to come. The birth of spaceflight also redefined humanity's relationship with distance. For the first time, reaching another world was not a metaphor, but a technical possibility. The gap between Earth and sky, once conceptual, became measurable in fuel, velocity, and time. Space was no longer an infinite beyond, it was a domain with entry conditions. Yet even as rockets made space accessible, they emphasized how difficult access truly was. The energy required to escape Earth is enormous. Every kilogram launched represents vast expenditure. Spaceflight is not a natural extension of human movement. It is an exception carved out through extreme effort. This difficulty tempered early optimism and imposed realism on long-term ambitions. In retrospect, the role of war in birthing spaceflight is deeply ambivalent. Without conflict, progress would almost certainly have been slower. Without urgency, resources might never have been concentrated so intensely. Yet the cost was high and the motivations conflicted. Space exploration carries this inheritance with it, a reminder that technological capability does not arise in moral isolation. What matters is not origin alone, but direction. The same rockets that once embodied destructive potential became tools for expanding knowledge. The same propulsion that carried weapons could carry cameras, sensors, and messages. Spaceflight transformed instruments of division into vehicles of shared discovery. In leaving Earth for the first time, humanity crossed more than a physical boundary. It crossed a psychological threshold. The sky ceased to be unreachable. Other worlds, once glimpsed only through light and inference, became destinations in principle. Spaceflight did not answer the question of what those worlds were like, but it made answering that question possible. The birth of spaceflight was not the fulfillment of an ancient dream. It was the opening of a door. What lay beyond it would depend on how humanity chose to step through. When humanity finally acquired the ability to leave Earth, the most immediate question was not where to go, but who or what should go first. The popular imagination, shaped by centuries of myth and decades of speculative fiction, expected human explorers to take the lead. Yet the reality of spaceflight dictated a different order. The first emissaries to other worlds were not people, but machines, and this choice was neither timid nor temporary. It was a recognition of the profound mismatch between human biology and the environments beyond Earth. Space is fundamentally hostile to life. Outside the narrow envelope of Earth's atmosphere, conditions shift abruptly from tolerable to lethal. Vacuum strips heat from unprotected bodies, radiation damages cells and DNA, and microgravity disrupts physiological systems evolved for constant weight. Even short exposures carry risk. Long durations amplify it. To send humans into space safely requires layers of protection, redundancy, and support systems that multiply complexity and cost. Early spaceflight, already operating at the edge of engineering capability, could not bear that burden. Robots, by contrast, thrive in indifference. They do not require air, food, or sleep. They do not suffer from radiation sickness or bone loss. Temperature extremes that would kill a human in seconds can be tolerated or engineered around by machines. A robot can be shut down, rebooted, or abandoned without moral consequence. In an environment where failure is likely and margins are thin, this resilience is decisive. The decision to send robots first was also shaped by uncertainty. When space exploration began in earnest, almost nothing was known about conditions beyond Earth. Even the space between planets was poorly characterized. Radiation levels, micrometeoroid density, and the behavior of spacecraft systems in prolonged microgravity were matters of speculation. Sending humans into such ignorance would have been reckless. Robots provided a way to probe the unknown without risking lives. There was also a deeper epistemological reason for robotic primacy. Early exploration was not about settlement or presence, it was about information. The primary goals were measurement, characterization, and reconnaissance. What mattered most was not endurance or adaptability, but the ability to gather data reliably under alien conditions. Machines excel at this task. They can be optimized for specific measurements, calibrated precisely, and operated continuously without fatigue or distraction. Robotic missions also allowed for iteration. A failed mission, while disappointing, did not end a program. Lessons could be learned, designs improved, and new attempts launched. Human missions, by contrast, impose an emotional and political finality. Failure involving loss of life can halt exploration entirely. Robots permitted a learning curve steep enough to be productive without being catastrophic. This pragmatism extended to distance. Many of the most intriguing targets in the solar system lie far beyond the reach of human travel, at least with current technology. Travel times measured in years or decades are acceptable for machines, but impractical for people. A robotic probe can cruise silently for years, awaken on arrival, and perform its tasks without complaint. Human explorers would require continuous life support, psychological resilience, and return plans that dramatically exceed feasible limits. The choice of robots also reshaped the philosophy of exploration itself. Traditionally, exploration had been defined by presence. To explore was to go somewhere in person. Space demanded a redefinition. Exploration became an act of extension rather than displacement. Human intention, curiosity, and judgment were projected outward through machines. The explorer's body remained on Earth, but the explorer's senses and agency did not. This projection was not passive. Robots were not autonomous wanderers acting independently of human thought. They were carefully designed embodiments of scientific questions. Every instrument carried by a spacecraft reflected a decision about what mattered to know. Cameras asked one set of questions, spectrometers asked another. Drills, scoops, and sensors extended human inquiry into environments where direct presence was impossible. The human role thus shifted from traveler to architect. Exploration became an exercise in anticipation. Missions had to be planned in exquisite detail long before launch. Paths, targets, contingencies, all were decided in advance. Once a spacecraft left Earth, real-time control was often impossible. Signals took minutes or hours to cross the void. Commands were delayed, responses arrived long after circumstances had changed. Robots had to operate with a degree of autonomy, carrying out human intent without immediate oversight. This delay introduced a new temporal rhythm to exploration. Unlike terrestrial expeditions, where decisions could be made on the fly, space missions unfolded according to pre-written scripts punctuated by moments of uncertainty. Patience became a scientific virtue. Waiting for data, interpreting sparse signals, and adjusting plans remotely required a different kind of engagement with discovery. Critics sometimes argue that robotic exploration lacks the authenticity of human presence. A machine, they contend, cannot truly experience a place. It does not feel terrain underfoot or react intuitively to the unexpected. Yet this critique misunderstands the purpose of early exploration. The goal was not experience for its own sake, but understanding. Robots were not sent to marvel, they were sent to measure. Moreover, machines enabled forms of perception unavailable to humans. Instruments can detect wavelengths the eye cannot see, sense chemical compositions imperceptible to touch, and operate in environments utterly inaccessible to biology. In many respects, robots are not lesser explorers but different ones, capable of gathering kinds of information no human could obtain directly. Their perspective is alien, but precisely for that reason it is powerful. There is also an ethical dimension to robotic primacy. Sending humans into poorly understood environments raises questions of consent, risk, and responsibility. Robots sidestep these issues. They absorb danger on humanity's behalf. This ethical buffer allowed exploration to proceed without forcing premature choices about acceptable loss. It bought time to learn, to refine technology, and to decide when, if ever, human presence would be justified. Robots also served as pathfinders. They mapped terrain, identified hazards, and tested technologies that would later support human missions. In this sense, robotic exploration was not a substitute for human exploration, but a prerequisite for it. Machines went first, not because humans were absent, but because humans were preparing. As robotic missions multiplied, their successes began to alter perception. Other worlds, once abstract targets, became places with recognizable features. Landscapes appeared. Patterns emerged. These images and data forged an emotional connection that challenged the assumption that only human presence could make a place real. A rocky plain photographed by a robot millions of kilometers away could feel immediate and compelling. Distance shrank in imagination, even as it remained vast in fact. This emotional resonance highlighted another strength of robotic exploration: accessibility. Data returned from machines could be shared widely, allowing millions to participate vicariously in discovery. Images could be broadcast, measurements published, and findings debated globally. Exploration became a collective experience rather than a privilege of a few. Robots did not exclude humanity from space. They invited it in. The success of robotic missions also revealed an unexpected continuity with earlier scientific methods. Telescopes and detectors had already accustomed humanity to knowing distant objects without physical contact. Spacecraft extended this tradition rather than overturning it. They were telescopes that moved, laboratories that travelled. The logic of remote sensing reached its natural conclusion in mobile instruments operating on other worlds. Over time, robots grew more capable. They moved from flybys to orbiters, from orbiters to landers, from landers to rovers. Each step represented an increase in interaction, not a leap in presence. Exploration deepened incrementally, guided by caution and evidence. This gradualism reflected an understanding of space not as a frontier to be conquered, but as an environment to be studied. The primacy of robots also shaped expectations about intelligence and agency. Machines demonstrated that purposeful action did not require consciousness. A rover navigating terrain according to programmed constraints could achieve goals without awareness. This realization subtly influenced how humanity thought about itself in the universe. Intelligence, it seemed, could be distributed, mediated, and embodied in forms other than flesh. Yet robots never replaced human curiosity. They served it. Every robotic mission was conceived, interpreted, and contextualized by human minds. The machines extended reach, but meaning flowed back to Earth. Exploration remained a human enterprise, even when humans stayed behind. In choosing robots to go first, humanity acknowledged both its limitations and its ingenuity. It recognized that survival beyond Earth would require humility as much as ambition. The universe would not accommodate human fragility. Humanity would have to adapt its methods to the universe as it is. Robots were the first step in that adaptation. They carried questions outward, gathered answers, and returned them across the void. They did not claim territory or plant flags. They observed, measured, and listened. In doing so, they transformed other worlds from unknown destinations into known places. Humanity did not delay exploration by sending robots first. It made exploration possible at all. When exploration moved beyond Earth, it carried with it a fundamental contradiction. For all of human history, to explore had meant to be physically present, to walk terrain, feel surfaces, and respond instinctively to the unexpected. Space exploration stripped away this immediacy. Other worlds were reached not by bodies, but by signals. Contact was replaced by communication. Presence gave way to proxy. Humanity was forced to learn how to explore without touch. This was not a simple substitution. Touch is not merely one sense among others. It is foundational to how humans understand space, texture, and reality itself. It provides resistance, feedback, and certainty. To remove it is to remove a primary source of trust. Early space exploration therefore faced a profound epistemic challenge: how to know a place without ever being there. The solution emerged gradually through the careful design of instruments that could substitute for physical interaction. Cameras became stand-ins for eyes, spectrometers for chemical intuition, and mechanical arms for hands. Each instrument translated a specific aspect of the environment into data that could be transmitted across immense distances. Exploration became an act of translation rather than immersion. This translation required new habits of interpretation. On Earth, a rock can be picked up, turned over, and examined from multiple angles in seconds. On another world, a similar action might take days or weeks of planning, command transmission, and execution. Decisions had to be made based on incomplete information, with limited opportunity for correction. The pace of exploration slowed dramatically, demanding patience and foresight. The loss of touch also altered the emotional texture of discovery. The thrill of immediate encounter was replaced by anticipation and delay. Images arrived long after they were captured. Data was passed far from its source. This distance could feel frustrating, yet it also intensified engagement. Each new signal carried weight. Each image was examined with care. Exploration became a collective act of interpretation rather than an individual experience. Learning to explore without touch also required redefining what counted as evidence. On Earth, direct manipulation provides confirmation. In space, confirmation comes through convergence. Multiple instruments must agree. Independent measurements must align. Confidence is built not through immediacy, but through redundancy. The reliability of knowledge depends on systems rather than sensations. This systemic approach fostered a new kind of rigor. Instruments were calibrated obsessively. Error margins were scrutinized. Assumptions were made explicit. Because direct verification was impossible, uncertainty had to be acknowledged rather than ignored. Space exploration became, by necessity, a discipline comfortable with provisional conclusions. The challenge extended beyond instruments to communication itself. Signals traveling across space are delayed, degraded, and sometimes lost. Commands sent to distant machines must anticipate conditions that cannot be directly observed at the moment of execution. Exploration thus became an exercise in prediction. Human operators had to imagine future states of environments they could not touch or see in real time. This predictive aspect transformed planning into a form of exploration in its own right. Before a mission ever launched, engineers and scientists simulated scenarios in painstaking detail. Virtual landscapes were constructed. Hypothetical failures were rehearsed. The journey occurred first in models and diagrams, long before it unfolded in reality. Exploration became front-loaded, with understanding pursued in advance rather than discovered on the fly. At the same time, this approach cultivated a new relationship with uncertainty. Despite exhaustive planning, surprises were inevitable. Environments behaved differently than expected. Surfaces proved softer or harder. Dust clung where it was not anticipated. Machines responded in unplanned ways. Each surprise had to be interpreted remotely, without tactile confirmation. Learning occurred through inference rather than sensation. These moments revealed the limits of remote exploration, but they also demonstrated its resilience. When a human explorer encounters the unexpected, instinct guides response. When a machine encounters it, human teams must reason their way forward collectively. This distributed problem-solving, though slower, can be remarkably creative. Solutions emerge through dialogue, debate, and iteration. Exploration becomes a shared cognitive endeavor. Exploring without touch also reshaped notions of risk. Human explorers accept personal danger as part of discovery. Machines do not experience risk, but missions do. A failed maneuver can end years of effort. Because replacement is costly and slow, caution becomes paramount. Every action is weighed against potential loss. This conservatism can frustrate the desire for boldness, yet it preserves continuity of investigation. Importantly, the absence of touch does not imply absence of interaction. Instruments can drill, scoop, heat, and analyze. They can alter environments in controlled ways. These interactions are indirect, mediated through commands and feedback, but they are nonetheless real. Other worlds are not merely observed, they are engaged, albeit carefully. The reliance on indirect interaction also forced a re-evaluation of scale. Human senses evolved to operate at human dimensions. Space exploration operates across extremes, microscopic chemistry and planetary landscapes alike. Instruments bridge these scales, translating phenomena into forms humans can comprehend. Touch, replaced by data, becomes abstracted. Texture becomes measurement. Resistance becomes force readings. Contact becomes signal. This abstraction has philosophical consequences. It distances the explorer from the explored, raising questions about authenticity and presence. Can a place truly be known without being felt? Does data capture essence or only surface properties? These questions echo older debates about perception and reality, now reframed by technology. Yet history suggests that touch is not the sole arbiter of knowledge. Much of modern science already operates beyond direct sensation. Atoms are known through traces. Forces are inferred through effects. Space exploration extends this epistemology to geography itself. Places are known through patterns of information rather than bodily immersion. Learning to explore without touch also democratized participation. Because exploration occurred through data, anyone with access to that data could engage with discovery. Scientists across the world could analyze findings simultaneously. Images could be shared with the public. Interpretation was no longer confined to those physically present. Exploration became inclusive, distributed across communities, rather than concentrated in individuals. This inclusivity changed the cultural meaning of exploration. Instead of heroic individuals venturing into the unknown, exploration became a collective project sustained by collaboration. Achievement was measured not by endurance or bravery alone, but by insight, coordination, and persistence. The romance of presence gave way to the satisfaction of understanding. At the same time, the absence of touch sharpened longing. Images of distant landscapes provoked a desire to feel them directly. Rocks seen but not held, horizons viewed but not walked. These absences became motivators. Robotic exploration both satisfied curiosity and intensified it. It revealed enough to make the lack of presence palpable. This tension has driven ongoing debate about the future of exploration. Some argue that robots suffice, that knowledge does not require embodiment. Others insist that human presence brings irreplaceable intuition and adaptability. Learning to explore without touch does not resolve this debate. It reframes it. It demonstrates what can be achieved remotely, clarifying what remains uniquely human. The discipline developed through remote exploration also influences how humanity thinks about its own planet. Satellite observation, remote sensing, and global monitoring apply the same principles to Earth itself. Touch is no longer required to know climate patterns, geological processes, or ecological change. The perspective gained through space exploration feeds back into terrestrial understanding. In this way, exploring without touch becomes a broader mode of knowing. It trains humanity to attend to signals, patterns, and systems rather than immediate sensation. It encourages patience over impulse, synthesis over reaction. These habits extend beyond space, shaping how complex problems are approached more generally. Yet it would be a mistake to interpret this mode as disembodied or detached. Human values, questions, and interpretations remain central. Machines do not decide what matters. People do. Touch is absent at the point of contact, but presence persists at the level of intention. Exploration remains grounded in human curiosity, even when mediated through circuits and code. As humanity learned to explore without touch, it also learned to trust forms of knowledge that feel counterintuitive. Certainty no longer arrived with physical confirmation. It emerged through coherence, consistency, and convergence. This trust was earned through repeated success. Remote methods proved capable not only of discovery, but of deep understanding. The result was a new kind of exploration, slower, more deliberate, but also more expansive. Worlds could be studied that would never host human footsteps. Environments too extreme for life could still be known. The reach of inquiry extended beyond the reach of bodies. Exploring without touch did not diminish the meaning of exploration. It transformed it. Presence became informational rather than physical. Contact became analytical rather than sensory. The universe, once approached through myth and later through observation, was now engaged through mediation. In mastering this mode, humanity gained access to places it could never otherwise know. Other worlds became legible, not through footprints, but through patterns of light, chemistry, and motion. Touch was absent, but understanding was not. This new way of exploring prepared humanity for a deeper question, not about how to explore, but about why. If worlds can be known without being visited, what does exploration ultimately mean? By the time humanity had learned to explore without touch, a deeper question could no longer be avoided. If machines could gather data, traverse hostile environments, and return knowledge across vast distances, what did exploration actually mean? The rise of unmanned exploration did more than extend reach. It challenged long-held assumptions about presence, purpose, and the human role in discovery. Space exploration ceased to be merely a technical endeavor and became a philosophical one. For most of history, exploration had been inseparable from embodiment. To explore was to go somewhere oneself, to endure risk, to encounter the unknown directly. Heroism, hardship, and narrative were tightly bound to physical presence. Unmanned exploration disrupted this tradition. Discovery no longer required the explorer's body to be at the site of discovery. Instead, intention and agency were projected outward through machines. The explorer remained on Earth, yet exploration still occurred. This separation forced a redefinition of presence. If a robotic instrument operates on another world according to human-designed goals, is that not a form of human presence by proxy? The machine does not choose its mission, but it enacts human curiosity with remarkable fidelity. In this sense, unmanned exploration is not absence but delegation. The explorer's body stays behind, but the explorer's questions, priorities, and methods travel onward. This delegation alters responsibility as well. In traditional exploration, the explorer bears the consequences of decisions directly. In unmanned exploration, consequences are displaced. A failed maneuver results in lost hardware and lost data, not lost life. This displacement lowers the ethical threshold for risk, enabling bolder inquiry. At the same time, it imposes a different kind of accountability. Missions are judged by return on investment, scientific yield, and long-term value rather than survival or endurance. Exploration becomes outcome-oriented rather than experiential. The philosophical shift also reframes courage. Courage in unmanned exploration does not reside in physical bravery, but in intellectual commitment. It is expressed through patience, long-term planning, and acceptance of uncertainty. Teams devote years, sometimes decades, to missions whose success is never guaranteed. The risk is not bodily harm, but irrelevance, failure, or silence. This quieter courage rarely fits heroic narratives, yet it sustains exploration just as surely. Unmanned exploration also challenges romantic notions of discovery. There is no first step taken by a person, no breath drawn in alien air. Instead, discovery unfolds through images arriving as data packets, through graphs and spectra interpreted far from their source. Critics sometimes see this as impoverished, a pale substitute for human encounter. Yet this view assumes that meaning derives primarily from sensation rather than understanding. In practice, unmanned exploration often produces a different, more reflective form of meaning. Distance encourages deliberation. Data must be contextualized, debated, and integrated. Discovery becomes less about momentary awe and more about cumulative insight. The emotional payoff may be delayed, but it is often deeper, rooted in comprehension rather than spectacle. There is also a democratizing effect. Human exploration concentrates experience in a few individuals. Unmanned exploration distributes it widely. Images and data can be shared globally, allowing millions to participate in interpretation and wonder. Discovery becomes collective rather than exclusive. The universe is no longer encountered by a select few on behalf of many. It is examined by many through shared evidence. This collectivization reshapes authority. In unmanned exploration, no single observer can claim privileged insight based on presence alone. Interpretation depends on reproducibility, transparency, and peer scrutiny. Knowledge is earned through consensus rather than testimony. This epistemic shift aligns space exploration more closely with modern scientific values, reinforcing skepticism and accountability. At a deeper level, unmanned exploration reflects a changed relationship between humanity and nature. It abandons the assumption that to know is to conquer. Machines do not impose themselves in the same way human explorers historically have. They move cautiously, sample sparingly, and leave minimal footprints. Exploration becomes observational rather than extractive. Other worlds are approached as subjects of study, not resources to be claimed. This restraint has ethical implications. As awareness grows that some environments may be scientifically pristine or potentially habitable, the choice to explore remotely takes on moral weight. Unmanned missions minimize contamination and irreversible impact. They allow humanity to learn without prematurely altering what is studied. In this sense, unmanned exploration embodies a principle of stewardship extended beyond Earth. The philosophy of unmanned exploration also intersects with questions of identity. If humanity can understand worlds it never visits, does presence matter at all? Does exploration require embodiment to be authentic? These questions resist simple answers. Human presence brings intuition, adaptability, and emotional resonance that machines cannot replicate. Yet unmanned exploration demonstrates that understanding does not depend solely on those qualities. Rather than replacing human exploration, unmanned exploration reframes it. It clarifies what humans uniquely contribute. Where machines excel at endurance, precision, and survival, humans excel at synthesis, improvisation, and meaning-making. The philosophy that emerges is not one of exclusion, but of complementarity. Robots extend reach, humans extend interpretation. This complementarity also influences long-term visions of spacefaring futures. Before humans venture widely beyond Earth, unmanned exploration maps paths, identifies hazards, and establishes knowledge. It creates the conditions under which human presence might one day be justified and sustainable. In this way, unmanned exploration is preparatory rather than substitutive. It is exploration in advance of arrival. Yet even if humans never set foot on many of the world's machines explore, those missions remain meaningful. The value of exploration lies not in possession, but in understanding. A world does not need to host human life to matter. Its history, structure, and processes enrich the story of the universe. Unmanned exploration affirms this broader conception of value. There is also a humbling aspect to this philosophy. By relying on machines, humanity acknowledges its own fragility. The universe is not built to accommodate human bodies. Survival beyond Earth is difficult, conditional, and uncertain. Unmanned exploration accepts this reality without surrender. It adapts method rather than insisting on dominance. This humility extends to expectations. Unmanned missions often operate at the edge of communication and control. Silence is a real possibility. Not every question will be answered. Not every target will yield insight. The philosophy that sustains these missions is one of patience rather than entitlement. Exploration is undertaken without guarantees. In this patience lies a quiet maturity. Humanity no longer assumes the universe owes it access or meaning. Instead, it approaches with tools designed to listen rather than demand. Data is accepted as it comes, incomplete and contextual. Understanding grows incrementally, not triumphantly. The rise of unmanned exploration also blurs boundaries between observer and instrument. Machines become extensions of human cognition, embodying decisions made years earlier. They act out intentions long after their creators may have moved on. Exploration acquires a temporal depth that transcends individual lifetimes. It becomes a cultural project rather than a personal one. This continuity reinforces the idea that exploration is not a single act, but an ongoing relationship with the unknown. Unmanned missions do not conclude stories. They open them. Each discovery raises further questions. Each answer reframes what remains to be known. The universe reveals itself gradually, through sustained engagement rather than dramatic conquest. Ultimately, the philosophy of unmanned exploration rests on a simple but profound recognition. Understanding does not require domination. To know a world is not to claim it. To explore is not to possess. Machines allow humanity to practice this distinction at a cosmic scale. By sending robots instead of people, humanity chose a path of inquiry over assertion. It accepted delay over immediacy, understanding over spectacle, patience over triumph. This choice does not diminish human aspiration. It refines it. It aligns exploration with responsibility and curiosity with care. Unmanned exploration is not a retreat from the universe. It is an approach shaped by realism, humility, and respect for complexity. It acknowledges both the power and the limits of human presence. Through machines, humanity reaches outward without pretending the universe is made for it. In doing so, exploration becomes less about where humans can go and more about what humans can learn. The universe is engaged not as a stage for heroism, but as a reality to be understood. That understanding, built slowly and collectively, will shape whatever future steps humanity chooses to take among the worlds it has come to know from afar. Mars in the human imagination. Long before Mars became an object of scientific scrutiny, it occupied a distinctive place in the human imagination. Unlike the distant stars, which appeared fixed and impersonal, Mars moved. Night after night, it wandered against the stellar background, sometimes brightening dramatically, sometimes retreating into obscurity. Its reddish hue set it apart from the other planets, giving it an identity that felt immediate and expressive. Among the wandering lights of the sky, Mars seemed almost alive. This sense of animation was crucial. Human imagination responds most strongly to what appears to change. Mars did not merely exist, it behaved. It looped backward in the sky, lingered near certain stars, and flared unexpectedly in brightness. These behaviors invited interpretation. To early observers, Mars was not just another celestial body, but a character, temperamental, unpredictable, and charged with meaning. Across cultures, the planet's color exerted a powerful influence on its symbolism. Red is the color of blood, fire, and danger, and Mars inherited these associations almost universally. It became linked with conflict, aggression, and upheaval. Yet this symbolism did not necessarily imply fear alone. War gods were often protectors as well as destroyers, embodiments of vitality and force. Mars, in this sense, represented raw energy, dangerous but essential. These associations endured because Mars remained visible to the naked eye in a way that preserved mystery. Its disk could not be resolved. Its surface features, if they existed, were hidden. Observers could track its motion with precision, yet its nature remained elusive. This combination of familiarity and concealment made Mars a perfect canvas for projection. It was close enough to feel relevant, distant enough to remain unknowable. As cosmological ideas evolved, Mars retained this imaginative charge. When the Earth-centered universe gave way to a planetary system in which Mars was recognized as a world like Earth, the nature of speculation changed, but its intensity did not. Mars ceased to be merely a sign or omen and became a place, a possible environment with its own conditions and history. The red planet was no longer just about war, it was potentially a world. This shift had profound consequences. Once Mars was conceived as a physical world, questions followed naturally. Did it have land and water? Did it have seasons? Could it support life? These questions were not idle. They reflected a growing willingness to imagine Earth as one example among many, rather than a unique stage set apart from the rest of the cosmos. Mars became the nearest test case for this new worldview. Mars also benefited from proximity in another sense. Its orbit brings it relatively close to Earth at regular intervals, causing it to loom large and bright in the sky. During these oppositions, Mars demands attention. It outshines most stars and rivals even Jupiter in brilliance. For ancient observers, these events would have reinforced the planet's perceived importance. Mars did not fade into the background, it asserted itself. With the rise of telescopic observation, this assertion intensified. Even crude instruments revealed that Mars had a disk rather than a point-like appearance. Dark and light regions became visible, hinting at surface diversity. The planet appeared to have polar caps that waxed and waned with the seasons, suggesting a climate. These observations were tantalizing precisely because they seemed so Earth-like. Mars began to look not just like a world, but like a familiar one. The human imagination seized on these similarities. If Mars had seasons, perhaps it had weather. If it had polar caps, perhaps it had water. If it had land and dark regions, perhaps it had vegetation. Each inference built upon the last, forming a narrative of a neighboring planet that was older, colder, and possibly more evolved than Earth. Mars became a mirror in which humanity contemplated its own past and future. This imaginative momentum was reinforced by cultural context. As industrialization reshaped Earth, people became accustomed to large-scale engineering, global communication, and rapid technological change. It no longer seemed absurd to imagine advanced societies altering entire landscapes. The idea that intelligent beings on Mars might build vast structures to manage dwindling resources resonated with terrestrial anxieties. Mars became a stage for reflecting human fears and ambitions back at themselves. Importantly, Mars was imagined not only as inhabited, but as narrative. It was given history. Speculation often portrayed it as a dying world, a planet that had once been vibrant but was now fading. This narrative carried moral weight. It suggested that civilizations like planets could decline if they failed to adapt. Mars became a cautionary tale projected onto the sky. At the same time, Mars retained its sense of otherness. Even in the most optimistic imaginings, it was rarely portrayed as a paradise. Its redness, its coldness, and its distance preserved an aura of danger. Mars was not a second Earth waiting to be claimed. It was a challenging environment that demanded ingenuity to survive. This tension between familiarity and hostility made it endlessly compelling. The imaginative power of Mars also stemmed from its silence. Unlike Earth, it offered no direct evidence of life. There were no signals, no obvious signs of activity, no definitive answers. This absence was fertile ground for speculation. Where evidence is lacking, imagination rushes in to fill the void. Mars became whatever the observer needed it to be: a rival, a warning, a hope. As scientific tools improved, this imaginative tradition did not vanish. It adapted. Even as skepticism grew and interpretations became more cautious, Mars continued to occupy a privileged position in the search for life beyond Earth. It was close enough to study in detail, yet alien enough to remain intriguing. Other planets were either too inhospitable or too distant to compete for attention. Mars stood at the threshold between the familiar and the unknown. This threshold status is crucial. Mars is neither clearly alive nor clearly dead. It shows evidence of past activity, yet appears inert today. It invites questions without answering them outright. In this ambiguity lies its enduring power. A planet that clearly hosts life would shift attention to biology. A planet that clearly never could would fade into geological interest. Mars occupies the uncomfortable middle ground. Human imagination is drawn to unresolved stories. Mars is unresolved. It hints at rivers without oceans, climates without warmth, and histories without witnesses. Each new observation reframes the mystery without closing it. This openness sustains fascination across generations, even as specific ideas rise and fall. Mars also serves as a psychological bridge between Earth and the wider universe. It is close enough to imagine visiting, settling, or transforming, yet distant enough to resist casual appropriation. It forces humanity to confront the limits of its power. Dreams of Mars are therefore always tinged with humility. The planet does not yield easily to fantasy. It pushes back with harsh realities. Over time, Mars has become more than a planet in the sky. It has become a symbol of persistence, of questions that refuse to disappear. Every era projects its concerns onto Mars, and every era finds something different reflected back. For ancient observers, it was a god of conflict. For early modern thinkers, a possible twin world. For industrial societies, a dying planet. For modern science, a record of planetary change and potential habitability. Yet beneath all these layers of interpretation lies a simple fact. Mars has always been visible. It has always been there, red and wandering, resisting easy classification. Unlike distant galaxies or invisible forces, Mars can be pointed to. It can be watched over a lifetime. This continuity anchors imagination in observation, preventing it from drifting entirely into abstraction. Mars matters not because it has confirmed humanity's hopes, but because it has consistently challenged them. It has invited speculation and then demanded correction. It has inspired stories and then resisted them. In doing so, it has trained human imagination to operate at the boundary between desire and evidence. The planet that refused to die in the human mind did so by remaining ambiguous. Mars never allowed itself to be fully explained, only more deeply questioned. This quality would shape every phase of its exploration, from illusion to shock, from hope to reassessment. Before spacecraft ever approached it, Mars had already been visited countless times in thought. Those visits left traces, not on its surface, but in human culture. Understanding Mars requires understanding those projections as much as the planet itself. The story of Mars exploration therefore begins not with rockets or instruments, but with imagination, persistent, restless, and never quite satisfied. Few episodes in the history of planetary science reveal more about the power of human perception than the saga of Martian canals. What began as cautious observation evolved into elaborate narratives of alien engineering, only to collapse under the weight of better evidence. This was not a simple case of error corrected by progress. It was a demonstration of how expectation, limitation, and imagination can conspire to create convincing illusions, especially when a world already carries deep symbolic weight. The roots of the canal controversy lay in the inherent difficulty of observing Mars from Earth. Even at its closest approaches, the planet remains distant enough that surface details blur at the edge of resolution. Early telescopes improved clarity, but not enough to deliver certainty. Observers strained to interpret faint contrasts and fleeting alignments through turbulent air. Under these conditions, the mind became an active participant in observation, assembling incomplete impressions into coherent forms. Lines began to appear. Thin, linear features seemed to connect darker regions across the Martian disk. At first, these were described cautiously, as markings or streaks whose nature was uncertain. But once the idea of linear structures entered discussion, it gained momentum. Human perception is exquisitely sensitive to lines and patterns. We are predisposed to connect dots, to impose order on ambiguity. What might have been irregular shading began to look like networks. Language played a crucial role in this transformation. The term used to describe these features carried implications beyond its technical meaning. A word that could signify natural channels was easily reinterpreted as artificial constructions. Once that interpretive door opened, the features were no longer neutral observations. They became signs of intention. The idea that Mars might host intelligent life was already circulating. The planet's apparent seasonal changes and polar caps suggested dynamic processes. Its smaller size and greater age invited speculation that it might be further along an evolutionary trajectory than Earth. Against this backdrop, canals seemed plausible, not as random features, but as deliberate responses to environmental decline. The narrative assembled itself with remarkable coherence. According to this vision, Mars was a drying world. Its inhabitants, facing dwindling water supplies, had constructed vast networks to distribute meltwater from the poles to arid regions. These canals were planetary-scale infrastructure, evidence of a civilization capable of global coordination. The starkness of the Martian environment reinforced the drama of the story. Survival on such a world would demand ingenuity, discipline, and cooperation, qualities admired and feared in equal measure. This narrative resonated powerfully with contemporary concerns on Earth. Rapid industrialization had demonstrated humanity's ability to reshape landscapes. Massive engineering projects were becoming symbols of progress and control. At the same time, anxieties about resource depletion and environmental stress were beginning to surface. Mars became a projection screen for these tensions, a distant reflection of terrestrial hopes and warnings. Importantly, the canal hypothesis was not fringe speculation. It was discussed seriously by respected observers and disseminated widely. Illustrations of Mars featuring intricate grids of straight lines captured public imagination. The image of a living, engineered planet took hold, reinforced by repetition and authority. Once embedded in popular culture, it became self-sustaining. Skepticism struggled to compete with the allure of an inhabited neighboring world. Yet from the beginning, there were dissenting voices. Some astronomers failed to see the canals at all. Others saw them intermittently or inconsistently. Observations varied with atmospheric conditions, instrumentation, and expectation. Attempts to photograph the canals produced ambiguous results. The lines seemed to resist objective capture, appearing most clearly in drawings rather than images. This inconsistency should have raised alarms, but it was often explained away. Differences in perception were attributed to observer skill or equipment quality. The absence of photographic confirmation was blamed on technical limitations. The narrative was resilient, capable of absorbing contradictions without collapsing. This resilience reveals a critical feature of illusion. Once an idea satisfies psychological and cultural needs, it becomes resistant to disconfirmation. The illusion was reinforced by the structure of early scientific communication. Observations were often shared through sketches and descriptions rather than raw data. Interpretation and representation were inseparable. A drawing was not merely a record, it was an argument. Each new depiction subtly guided how others looked, priming perception to align with expectation. The canals were not only seen, they were taught to be seen. As telescopic technology improved, however, the tension between expectation and evidence grew harder to ignore. Larger instruments and better optics revealed more detail, not less. The surface of Mars appeared increasingly complex and irregular. The crisp straight lines of canal maps dissolved into patchy shading and natural features. Where precision increased, canals retreated. This retreat did not occur all at once. Belief lingered, adapted and narrowed. Some proposed that canals were seasonal or transient, appearing only under certain conditions. Others suggested they were optical effects enhanced by contrast. Gradually, the idea of vast artificial networks gave way to more cautious interpretations. The narrative lost coherence as evidence accumulated against it. The final blow came not from argument, but from clarity. Improved observation showed that Mars was not crisscrossed by straight lines, but textured with craters, valleys, and irregular formations. What had once seemed like deliberate geometry was revealed as the brain's attempt to simplify complexity under poor resolution. The canals were not discovered to be something else, they were discovered not to exist. This realization forced a reckoning, not only with a specific hypothesis, but with the process that had produced it. The canal episode exposed the vulnerability of observation to bias, especially when data is sparse and stakes are high. It demonstrated how easily the desire for meaning can shape perception, turning ambiguity into apparent structure. The disillusionment was profound. Mars, once imagined as a world of dying but noble civilizations, appeared increasingly barren. The collapse of the canal narrative marked a turning point in planetary science. Speculation would no longer be allowed to outrun evidence so freely. Caution replaced confidence. Mars shifted from a mirror of human ambition to a problem of planetary physics. Yet the canal episode should not be dismissed as mere folly. It played a crucial role in sustaining interest in Mars. It motivated observation, debate, and technological improvement. Without the imaginative momentum generated by the idea of Martian civilizations, the drive to study the planet might have waned. Illusion, in this case, propelled inquiry even as it misdirected it. There is also a deeper lesson embedded in the episode. The canals revealed the human tendency to anthropomorphize the unknown. Faced with an alien world, observers interpreted it through familiar frameworks: cities, infrastructure, intention. This tendency is not easily erased. It reflects how human cognition operates, seeking agency and purpose even where none exists. Modern science did not eliminate this impulse, it learned to manage it. The canal controversy contributed to the development of stricter standards of evidence and greater awareness of cognitive bias. It underscored the importance of independent verification and objective recording. Photography, spectroscopy, and eventually spacecraft would provide these tools, reducing reliance on subjective interpretation. The emotional arc of the canal story also left a lasting imprint on how Mars would be approached thereafter. Enthusiasm was tempered by humility. Claims were framed more cautiously. Extraordinary interpretations demanded extraordinary support. Mars had taught science a painful but valuable lesson about restraint. Yet even as the canals vanished from serious discussion, their legacy endured in culture. The idea of Mars as inhabited lingered in fiction, art, and public imagination long after scientists had abandoned it. This persistence reflects the emotional power of the original vision. A barren Mars was harder to love than a struggling, intelligent one. In a sense, the canals never truly disappeared. They transformed. What had once been imagined as artificial structures became, in later exploration, genuine channels carved by natural processes. Mars did have valleys and river-like features, just not the ones imagined. The planet retained its connection to water and change, even as the narrative shifted from engineering to geology. This transformation highlights the complex relationship between illusion and discovery. The canals were wrong, but they pointed in a direction that was not entirely misplaced. Mars was not a static desert. It had a dynamic past. The error lay not in imagining activity, but in assigning it prematurely to intelligence. The canal episode thus stands as a cautionary tale and a catalyst. It warns against the seductions of overinterpretation, especially when evidence is limited. At the same time, it illustrates how imagination can drive scientific progress by focusing attention and effort. Mars demanded better answers, and science eventually delivered them, not by confirming fantasy, but by replacing it with deeper understanding. In relinquishing the canals, humanity did not lose Mars. It gained a more honest relationship with it. The planet emerged not as a stage for alien civilizations, but as a record of planetary processes that could illuminate Earth's own history and fate. Illusion gave way to shock. The next encounters with Mars would be far less forgiving and far more revealing. The first spacecraft to pass close to Mars did more than return data. They shattered an entire era of expectation. For generations, Mars had been imagined from afar, filtered through telescopes, drawings, and theories shaped as much by hope as by evidence. When machines finally crossed the gap and looked directly upon the planet, the shock was immediate and profound. Mars did not merely disappoint old fantasies. It replaced them with something far stranger and more sobering. Until those first flybys, Mars had remained an abstraction constrained by distance. Even after the canal illusion faded, many scientists still expected a world that resembled a colder, drier Earth. Seasonal changes, polar caps, and surface markings suggested at least a measure of familiarity. The prevailing question was not whether Mars had once been Earth-like, but how far along its decline it had progressed. The assumption of kinship persisted. Flyby missions ended that assumption in a matter of hours. As the first close images streamed back, Mars revealed a surface that was brutally alien. Craters dominated the landscape, overlapping and ancient, more reminiscent of the Moon than of Earth. Vast, seemingly lifeless plains stretched without vegetation, without rivers, without signs of recent geological activity. The sky appeared thin and hazy, offering little protection from space. The sense of a dying but once flourishing world was replaced by the image of a planet that had been cold, battered, and exposed for immense spans of time. The emotional impact of these images cannot be overstated. Mars had long been the most promising candidate for a living neighbour. It was the planet closest to Earth in imagination, as well as distance. When it failed to meet expectations, the disappointment was not merely scientific. It was cultural. Mars had carried humanity's projections of otherworldly life more than any other body in the solar system. Its apparent desolation forced a reckoning. The shock was sharpened by contrast. The Moon's barrenness had been expected. It was small, airless, and clearly geologically inactive. Mars, by contrast, had teased observers with hints of complexity. To see it rendered as a cratered wasteland felt like a betrayal of accumulated hope. The flybys did not simply reveal Mars, they exposed how much observers had wanted it to be something else. This moment marked a turning point in planetary science. Distance had allowed ambiguity, proximity did not. The flybys stripped away interpretive comfort. Mars was no longer a canvas for speculation. It was a place with measurable properties, and those properties were unforgiving. The atmosphere was far thinner than anticipated. Surface pressures were low. Radiation exposure was high. Liquid water, if it existed at all, could not persist on the surface under current conditions. Yet within this disappointment lay a more subtle surprise. Mars was not uniformly dead. Even in the earliest images, signs of complexity emerged. Enormous volcanoes towered over the plains, dwarfing anything on Earth. A canyon system cut across the planet on a scale unmatched in the solar system. These features hinted at a violent and dynamic past. Mars might be barren now, but it had not always been quiet. This dual revelation, present desolation paired with past grandeur, reframed the planet entirely. Mars was not a failed Earth. It was a different kind of world, one that had followed its own evolutionary path. The absence of life as imagined did not equate to absence of history. On the contrary, Mars appeared to preserve its history in stark relief, unsoftened by erosion or biological overprinting. The flybys also exposed the limits of remote interpretation. Features once interpreted as vegetation cycles or artificial constructs dissolved under higher resolution. What remained were geological patterns that demanded new explanations. Scientists were forced to confront how much they had inferred from minimal data. The shock was epistemological as much as observational. Mars had not misled humanity. Humanity had misread Mars. There was also a temporal shock. The cratered surface suggested immense age. Mars appeared to have ceased much of its geological activity early in its history, leaving scars that persisted for billions of years. Earth, by contrast, renews itself constantly through plate tectonics, erosion, and life. The comparison underscored how different planetary destinies can be, even among neighbours formed from similar materials. The atmosphere revealed by the flybys deepened this contrast. Mars possessed only a tenuous envelope of gas, insufficient to trap heat or shield the surface effectively. The idea of a warm, wet present collapsed. Any habitability Mars might have enjoyed had to belong to the distant past. This realization redirected scientific inquiry. The question was no longer whether Mars currently hosted life, but whether it ever could have. This shift was not universally welcomed. Some resisted the bleakness of the new image, searching for signs that might preserve older hopes. Others embraced the clarity, seeing in it an opportunity to study planetary failure and divergence. Mars became valuable not because it resembled Earth, but because it did not. Its differences promised insight into what makes worlds livable, and what causes them to lose that capacity. The flybys also demonstrated the power of proximity in planetary exploration. Images taken from afar had allowed imagination to dominate. Images taken close imposed discipline. They forced theory to respond to reality rather than the reverse. This lesson would echo throughout the exploration of the solar system. Close encounters do not merely add detail, they reorder understanding. Emotionally, the flybys marked the end of innocence. Mars could no longer be dreamed into friendliness. It had to be confronted on its own terms. The planet's harshness demanded respect rather than romanticism. This shift matured the scientific relationship with Mars, replacing speculative exuberance with measured curiosity. Yet the shock did not extinguish fascination. It transformed it. Mars became compelling for new reasons. Its vast volcanoes raised questions about internal heat and planetary size. Its canyons hinted at processes unlike those on Earth. Its cratered plains offered a window into early solar system history. The absence of life became a puzzle rather than a verdict. There was also an unexpected aesthetic dimension to the flyby images. The starkness of the Martian surface carried its own beauty, desolate, monumental, and ancient. Mars emerged as a world of extremes, sculpted by forces that operated on scales difficult to imagine. This aesthetic impact helped sustain public interest, even as old narratives collapsed. The shock of the flybys also altered expectations for future missions. If Mars had confounded assumptions so completely, what else might be misunderstood? Caution became a guiding principle. Hypotheses were framed tentatively. Data was prioritized over narrative. The planet had earned skepticism. At the same time, the flybys underscored the necessity of continued exploration. One encounter was not enough to tell a planet's story. The surface revealed by brief passes could not capture regional diversity or subsurface complexity. Mars, stripped of illusion, demanded deeper investigation. Its mysteries had changed, but they had not diminished. The psychological transition from imagined Mars to observed Mars was not instantaneous. Cultural representations lagged behind scientific understanding. Stories of Martian civilizations persisted even as evidence faded. This lag highlights the different tempos of science and imagination. Data can overturn ideas quickly. Culture absorbs change slowly. Nevertheless, the flybys marked an irreversible shift. Mars was no longer an idea first, and a planet second. It was a planet first, and ideas would have to follow. This reordering defined the next phase of exploration. Orbiters, landers, and rovers would build on the flybys' revelations, moving from shock to synthesis. The first close encounters taught humanity a difficult but necessary lesson. Proximity does not confirm hope. It tests it. The universe is not obliged to fulfill expectation. Other worlds exist on their own terms, indifferent to human longing. To explore them is to accept that indifference without surrendering curiosity. Mars, revealed at last, did not offer the comfort of familiarity. It offered something more demanding, the challenge of understanding a world that refused to align with imagination. In that refusal lay the beginning of a more honest exploration, one grounded in evidence, tempered by humility, and open to surprise. The flybys ended the era of illusion. What followed would require landing, touching, and measuring, one careful step at a time. If the flybys had stripped Mars of illusion, landing on it forced humanity into a new relationship with the planet, one defined by intimacy, vulnerability, and irreversible commitment. A flyby is a glance, however close. A landing is an encounter that cannot be undone. To land on Mars was to accept its gravity, its atmosphere, and its surface as they were, not as imagined. It was a declaration that Mars was no longer merely to be observed, but to be engaged. The technical challenge alone was unprecedented. Mars occupies an unforgiving middle ground between worlds. Its atmosphere is thick enough to complicate entry, yet too thin to provide easy braking. Spacecraft arriving at Mars must shed enormous velocity in minutes, relying on a precarious sequence of heat shields, parachutes, and controlled descent. There is no margin for improvisation. By the time a signal reaches Earth, the outcome is already decided. Landing on Mars is not piloting. It is choreography executed in silence. This constraint reshaped the psychology of exploration. Engineers and scientists had to relinquish control at the most critical moment. Human decision-making gave way to pre-programmed action. Trust shifted from people to systems. A landing, once initiated, unfolded beyond intervention. Success or failure would be known only after the fact, announced by a delayed signal crossing millions of kilometers of space. The first successful landings therefore carried a tension unlike any previous exploration milestone. They were not triumphant arrivals marked by human presence, but anxious waits punctuated by data. When confirmation finally came, relief replaced suspense. Humanity had not merely reached Mars, it had touched it, however indirectly. Touch, even mediated through machines, changed everything. Orbiters could suggest, landers could confirm. Soil composition could be measured directly. Atmospheric conditions could be sampled at the surface. Temperatures could be recorded through day and night. Mars ceased to be a surface inferred from afar and became an environment characterized from within. The initial impressions were stark. The ground appeared rocky, dry and barren. The sky was thin, tinted by dust rather than clouds. There were no signs of vegetation, no obvious indicators of biological activity. The dream of a living Mars, already weakened by flybys, seemed to fade further. Yet landing did not simply confirm desolation. It revealed complexity at a finer scale. Soils told stories. Chemical analyses indicated interactions with water in the past. Minerals formed in environments that could not be explained by dry processes alone. The ground bore witness to conditions different from those observed today. Mars, it seemed, was not merely barren, it was transformed. The surface preserved traces of a world that had changed profoundly. This realization reframed disappointment into curiosity. The absence of life was no longer the end of the story. It became the beginning of a deeper question. What happened here? Landing on Mars turned the planet into a forensic site. Every rock became evidence. Every layer hinted at processes long ceased. Exploration shifted from searching for present vitality to reconstructing ancient environments. The act of landing also humanized Mars in an unexpected way. Images returned from the surface were no longer abstract views of a distant sphere. They were horizons, shadows, textures. The planet acquired scale. Slopes could be judged. Distances estimated. Mars became a place that could be stood upon, even if only by machines. This sense of place altered public perception. Mars was no longer an unreachable point of light. It was a landscape. Yet this intimacy carried restraint. Landers were confined to single locations. Their perspective was fixed. What they revealed was detailed but local. Mars, vast and varied, could not be understood from one point alone. Each landing answered some questions while raising many others. The need for mobility became clear. Before that mobility could be realized, however, landers had to survive. Mars tested machinery relentlessly. Dust coated instruments. Temperature swings stressed materials. Communication was intermittent. Power was finite. Every operation required careful planning to conserve resources. The environment imposed discipline, forcing exploration to proceed deliberately. These constraints shaped scientific priorities. Measurements had to justify their cost in energy and risk. Redundancy became essential. Instruments were designed to serve multiple purposes. Each action was weighed against the possibility of mission-ending failure. Mars was not a forgiving place for experimentation. Yet within these limits, landers accomplished something profound. They validated the entire premise of unmanned planetary exploration. Machines could survive on another world long enough to conduct meaningful science. Data returned from the surface was richer and more nuanced than anything obtained remotely. The investment was justified not by spectacle, but by understanding. Landing also deepened philosophical questions raised by unmanned exploration. If machines could land, analyze, and transmit knowledge from Mars, what role remained for human presence? The surface data did not feel incomplete. In many respects, it exceeded what humans could have gathered in short visits. The notion that embodiment was essential to exploration weakened further. At the same time, landing intensified the desire for human presence. Seeing Mars up close made it feel tantalizingly accessible. The obstacles were technical rather than conceptual. The planet was no longer an abstraction. It was a place where machines already stood. The question shifted from whether humans could go to when and why they should. Scientifically, landing marked the transition from reconnaissance to investigation. Mars was no longer surveyed broadly. It was studied deeply. Hypotheses generated by orbital data could be tested directly. Interpretations could be refined or rejected. The planet's story began to cohere, not as a tale of alien civilization, but as a narrative of planetary evolution. This evolution appeared harsh. Mars had lost much of what made Earth hospitable. Its atmosphere thinned. Its magnetic field weakened or vanished. Surface water disappeared. Whatever processes once sustained a warmer, wetter environment had ceased. Landing confronted humanity with a planetary cautionary tale written in stone. Yet Mars was not simply a warning. It was also an archive. Earth's active geology and biology erase much of its early history. Mars, quieter and colder, preserved its past. Landing on Mars allowed humanity to read chapters of planetary history no longer legible at home. In this sense, Mars became valuable not despite its barrenness, but because of it. Emotionally, landing represented a moment of reconciliation. The disappointment of earlier shocks gave way to a more mature appreciation. Mars did not need to host life to matter. It mattered because it revealed how planets change, how environments collapse, and how habitability can be lost. These lessons were not abstract. They were written across the Martian surface. The act of landing also reinforced the collaborative nature of modern exploration. No single individual could claim credit for standing on Mars. Success belonged to teams, institutions, and generations of accumulated knowledge. Exploration was no longer heroic in the classical sense. It was collective, procedural, and cumulative. This collectivism changed the narrative of achievement. The milestone was not a footprint, but a data set. The triumph was not endurance, but insight. Mars, once the province of myth and imagination, became a laboratory for planetary science. Its significance shifted from romance to relevance. Yet even as Mars was domesticated scientifically, it retained its power to inspire. The images returned from the surface did not dispel wonder. They redirected it. The stark beauty of Martian landscapes spoke of timescales and forces beyond human experience. Standing on Mars, even by proxy, expanded perspective. Landing on another world also redefined the relationship between risk and reward. The risk was enormous, but it was borne by machines. The reward was knowledge shared widely. This asymmetry reinforced the logic of unmanned exploration while leaving open the possibility of future human involvement. Ultimately, landing on Mars closed one chapter of exploration and opened another. It ended the era in which Mars could be imagined freely. The planet had spoken for itself, through rocks, soil, and silence. What it said was complex, sobering, and compelling. Mars had not offered the life humanity once hoped to find. Instead, it offered understanding about planets, about change, and about fragility. Landing transformed Mars from a symbol into a subject. And having landed, humanity could no longer look away. Water has always been the silent protagonist of the Martian story. Long before spacecraft touched the surface, speculation about Mars revolved around the possibility of flowing water, channels imagined, polar caps observed, seasonal changes debated. With landings and orbiters providing concrete data, the question of water did not disappear. It sharpened. Mars revealed a paradox: abundant signs of water's influence, yet no oceans to be found. The first indications came from the land itself. From orbit, Mars displayed networks of valleys and channels etched into its surface, some branching and sinuous, others wide and scoured. These features bore an unmistakable resemblance to river systems on Earth. They curved, converged, and cut through terrain in ways difficult to explain without flowing liquid. The implication was unavoidable. Water had once moved across Mars on a planetary scale. Yet this implication collided with present reality. The surface was dry beyond dispute. The atmosphere was too thin to support stable liquid water. Temperatures rarely rose above freezing. There were no seas, no lakes, no rivers. Mars had water written into its geography, but not into its present. The planet seemed to remember water even as it no longer possessed it. This contradiction forced a temporal shift in thinking. Water on Mars was not a contemporary phenomenon, it was a historical one. The channels did not speak of current flow, but of ancient conditions radically different from those observed today. Mars, it became clear, had undergone a transformation profound enough to erase oceans while preserving their traces. Geological evidence supported this view. Layered sedimentary rocks suggested deposition in standing bodies of water. Minerals formed in aqueous environments were detected, their chemistry incompatible with dry processes. Some formations hinted at long-lasting interactions between rock and liquid, not brief or catastrophic events. Mars, at some point, had sustained water for extended periods. Yet the absence of shorelines complicated the picture. On Earth, oceans leave unmistakable signatures: coastal features, wave-cut terraces, sediment distribution. On Mars, such features were ambiguous or absent. If oceans had existed, where were their boundaries? The planet offered rivers without seas, deltas without basins. Water seemed to have flowed, pooled, and vanished without leaving behind a clear final resting place. This puzzle prompted competing interpretations. Some suggested that Mars never had large oceans, only regional bodies of water that formed and evaporated or froze over time. Others proposed that oceans did exist, but their evidence was obscured by later geological processes or buried beneath dust and volcanic deposits. Still others argued that water flowed episodically, released by melting ice or subsurface reservoirs rather than sustained climate. Each interpretation carried implications for Mars's climate history. Sustained oceans would require a thicker atmosphere and warmer temperatures over long periods. Episodic flows could occur under colder conditions, driven by transient heating events. The debate was not merely academic. It touched on the central question of habitability. Long-lived water environments are more favourable for life than brief, catastrophic floods. What complicated matters further was Mars's apparent inability to retain water. The planet's low gravity and lack of a strong magnetic field left its atmosphere vulnerable to erosion. Over time, solar radiation could strip away gases, thinning the atmosphere and destabilizing surface water. Water molecules themselves could be broken apart, with hydrogen escaping into space. Mars's water did not simply disappear, it was slowly dismantled. This process reframed Mars as a cautionary example of planetary vulnerability. Earth retains its oceans in part because of its size, magnetic field, and active geology. Mars, smaller and quieter, lost the protections that sustained habitability. Its water history became a story of loss rather than absence. Yet not all water vanished. Evidence accumulated that significant amounts remained locked away. Polar caps contained vast reserves of ice. Subsurface ice appeared widespread, particularly at higher latitudes. Radar data suggested buried glaciers and ice-rich deposits hidden beneath layers of dust and rock. Mars was not dry in an absolute sense, it was dry at the surface. This realization added complexity to the narrative. Mars had not simply lost its water, it had redistributed it. Liquid water gave way to ice. Oceans may have fragmented into reservoirs isolated from one another. The hydrological cycle, once active, became frozen in place. Water remained present, but inaccessible. The distinction between liquid and solid water matters profoundly for life. Liquid water is a solvent, a medium for chemistry, and a facilitator of biological processes. Ice is a storage state. Mars' water story, therefore, is not just about quantity, but about phase. The planet crossed a threshold beyond which water could no longer perform its life-enabling role on the surface. This threshold likely marked a turning point in Mars's biological potential. If life ever arose, it would have done so under conditions very different from those observed today. As the planet cooled and dried, any life would have been forced to adapt, retreat, or perish. The surface became hostile, while subsurface niches might have offered refuge. The absence of oceans also affected how Mars was studied. Without large bodies of water, sediment transport and erosion operated differently. Landscapes preserved ancient features rather than constantly renewing them. This preservation turned Mars into a geological time capsule. The same processes that made it inhospitable also made it readable. For scientists, this readability was invaluable. Earth's dynamic systems erase evidence of early environments. Mars's stillness preserved them. Channels, deltas, and mineral deposits became clues in a planetary detective story. Water without oceans became a paradox that demanded explanation rather than dismissal. This paradox also influenced exploration strategy. If Mars once had water, where was it most likely to have pooled? Where might it have lingered longest? These questions guided the selection of landing sites. Exploration targeted regions with signs of ancient lakes, river deltas, and mineral alteration. Mars was no longer searched indiscriminately. It was interrogated methodically. Emotionally, the water story carried a quiet melancholy. The idea of rivers flowing across Mars, of rain falling under a thicker sky, evoked a lost world. Mars became not just barren, but bereaved. Its dry plains were not primordial deserts, but remnants of something richer that had faded away. This sense of loss resonated with broader human concerns. On a planet grappling with environmental change, Mars offered a stark reminder that habitability is not guaranteed. Worlds can cross thresholds from which there is no easy return. The red planet became a silent witness to planetary fragility. Yet the absence of oceans did not render Mars irrelevant. On the contrary, it made it more important. Understanding how and why Mars lost its water could illuminate Earth's own long-term stability. It could reveal the conditions necessary to sustain oceans and the risks that threaten them. Mars' dryness became a lesson written at planetary scale. Water without oceans also challenged assumptions about life elsewhere. It suggested that habitability might be transient rather than permanent. Worlds could host life for a time and then become sterile. The search for life beyond Earth would need to account for this impermanence, looking not only for current water, but for histories of water. In this way, Mars expanded the concept of habitability from a static condition to a dynamic process. It taught that being habitable is something a planet does, not something it is. Mars had done it once, and then stopped. The channels, deltas, and mineral traces scattered across its surface are not remnants of failure alone. They are records of possibility. They show that Mars crossed thresholds Earth has not yet crossed, and in doing so, they provide perspective. Mars's water story is not about oceans that never existed. It is about oceans that may have existed and then vanished, leaving behind a planet caught between memory and absence. To explore Mars is to read that memory in stone. And in doing so, humanity learns as much about its own world as about the red one. Mars should have lost its hold on the human imagination long ago. It offered no canals, no civilizations, no living surface. Its air was thin, its ground barren, its silence complete. And yet, despite the collapse of its most seductive myths, Mars continues to haunt humanity in a way no other planet does. This persistence is not an accident of tradition or proximity. It arises from something deeper. Mars occupies a unique psychological, scientific, and symbolic space that no amount of data has been able to erase. At the most basic level, Mars haunts us because it is almost Earth. Not enough to be familiar, not enough to be alien. It shares a day length similar to our own. It has seasons. It has mountains, valleys, dust storms, and polar ice. It obeys the same physical laws and formed from the same primordial material. Yet it diverged. Somewhere along its history, Mars became what Earth did not. That divergence invites comparison, and comparison invites unease. Mars is the closest example of a world that might have succeeded, and didn't. This is not the cold inevitability of a gas giant or the sterile finality of an airless moon. Mars looks like a planet that once had options. It had water. It had energy. It had time. The fact that it lost these advantages transforms it into a planetary cautionary tale rather than a simple curiosity. Mars is not irrelevant. It is instructive. This sense of instruction is what makes Mars linger in thought. Every discovery on Mars raises a parallel question about Earth. Why does Earth still have oceans? Why does it retain a thick atmosphere? Why does it support life so robustly while Mars does not? The answers point to contingencies rather than certainties. Size, magnetic fields, internal heat, geological activity. These are not guaranteed features of rocky planets. Earth's stability appears less inevitable when seen alongside Mars' collapse. Mars haunts us because it demonstrates that planetary habitability is fragile. It is not a permanent state bestowed by formation alone. It must be maintained by a delicate balance of forces. When that balance is lost, the consequences are irreversible on human timescales. Mars does not merely show a different outcome, it shows how easily outcomes can diverge. There is also a psychological intimacy to Mars that cannot be replicated by more exotic worlds. We can imagine standing on Mars. We can picture its horizon, its sky, its dust underfoot. Even without human presence, Mars feels inhabitable in concept, if not in practice. This imagined accessibility creates emotional proximity. Mars feels like a place we could reach, not a realm forever beyond us. This imagined reachability intensifies both hope and anxiety. Mars becomes the nearest destination for humanity's outward ambitions, yet it also confronts those ambitions with stark limits. It is close enough to tempt, harsh enough to resist. This tension keeps Mars perpetually unresolved in human thought. Mars also haunts us because it preserves memory. Earth is a world of erasure. Tectonics, erosion, and life itself overwrite the past continuously. Mars, by contrast, is a world of accumulation. Its surface holds scars billions of years old. Its landscapes are not just places, but records. To study Mars is to study deep time in a form rarely accessible elsewhere. This temporal depth lends Mars a gravitas that transcends its present barrenness. It is not empty, it is archived. Each crater, channel, and layer of sediment is a sentence in a long planetary autobiography. Mars does not speak through activity, but through stillness. It tells its story by refusing to change. That refusal creates a peculiar sense of presence. Mars feels watched rather than watching, remembered rather than living. It is a world that seems to bear witness to its own past, to the processes that shaped it, and by extension, to the fragility of worlds like ours. This witnessing quality gives Mars a quiet authority. The haunting quality of Mars is also tied to loss. Unlike worlds that were never habitable, Mars appears to have crossed a threshold and then retreated. The traces of water, the mineral signatures, the ancient river systems, all imply conditions that no longer exist. Mars is a planet defined by absence. It shows what happens when sustaining processes fail and do not return. Human imagination is particularly sensitive to lost worlds. Ruins fascinate more than empty spaces. Mars is not empty, it is ruined at a planetary scale. This framing resonates deeply. A ruined city suggests past life. A ruined planet suggests past possibility. Mars occupies that emotional register, whether or not life ever existed there. Even the failure to find life reinforces this haunting. The question of Martian life remains unresolved, not because evidence confirms it, but because evidence does not decisively exclude it. Mars keeps its secrets carefully. If life ever arose, it may have retreated underground, leaving no obvious traces. The silence is not a definitive answer. It is an invitation to keep asking. This unresolved status sustains fascination. A planet that clearly hosts life would redirect attention to biology. A planet that clearly never could would recede into geology. Mars sits between these states. It neither confirms nor denies humanity's hopes. It withholds closure. Mars also haunts us because it is the first truly otherworld humanity has come to know intimately. The Moon was familiar in its deadness. Venus was hostile beyond endurance. Mars occupies a middle ground that forces engagement rather than dismissal. It is the first planet that demanded sustained study rather than brief encounter. This sustained study has created a layered relationship. Mars has been imagined, misimagined, corrected, and reimagined again. Each phase leaves residue. Cultural memory does not reset when science advances. Older visions persist alongside newer ones. Mars carries all its past interpretations at once, becoming a palimpsest of human thought. There is also an ethical dimension to Mars' haunting presence. As discussions of human expansion beyond Earth grow more serious, Mars looms as both destination and warning. It represents humanity's desire to escape planetary limits, but also the reminder that planets can fail. To go to Mars is not simply to explore. It is to confront the consequences of planetary misfortune. Mars resists being reduced to a single meaning. It is not merely a target for colonization, nor merely a scientific object, nor merely a symbol. It is all of these at once, and more. This multiplicity prevents closure. Mars remains open-ended, refusing to settle into a stable role. The planet also occupies a unique place in time. It is close enough to study now, yet distant enough to represent the future. Mars feels like tomorrow's world, one humanity may visit, inhabit, or transform. At the same time, it feels like yesterday's world, a record of what once was. It exists simultaneously as future and past. This temporal duality deepens its haunting quality. Mars invites humanity to imagine itself both forward and backward in time. It asks what Earth might become and what it once was. Few worlds offer this mirror so clearly. Ultimately, Mars haunts us because it refuses to answer the most important questions definitively. Was it ever alive? Could it have remained habitable? What determines planetary fate? Each new mission sharpens these questions without resolving them fully. Mars yields knowledge but not closure. This refusal is not a failure of exploration. It is its success. Mars has taught humanity that understanding does not always bring comfort. Sometimes it brings responsibility, humility, and vigilance. The red planet stands as a reminder that worlds are not static, that habitability is earned and maintained, and that loss is possible even on planetary scales. Mars does not haunt us because it is mysterious alone. It haunts us because it is familiar enough to matter and different enough to warn. It is a neighbour that followed a path we did not, and in doing so, it illuminates the path we are on. The planet that refused to die in imagination continues to do so not because we misunderstand it, but because we understand it just enough to feel uneasy. Mars remains unresolved, and as long as it does, it will continue to haunt us. Landing on Mars transformed the planet from an object of speculation into a subject of direct study, but it also revealed a limitation that quickly became impossible to ignore. A stationary lander could tell a detailed story about one place, yet Mars was vast, varied, and unevenly written. The planet's history was not confined to a single patch of ground. To read it properly, exploration needed to move. Mobility was not a luxury, it was a necessity. The rise of mobile exploration marked a conceptual shift as much as a technical one. Instead of treating Mars as a set of isolated samples, scientists began to think of it as a landscape, one that could be traversed, compared, and contextualized. Movement allowed questions to change in scope. No longer was the goal simply to analyze a site, it was to understand relationships between sites, to follow patterns across terrain, and to reconstruct processes that unfolded over distance and time. This shift demanded a reimagining of the explorer itself. A rover is not merely a lander with wheels. It is an autonomous extension of human curiosity, designed to operate under constraints far removed from human reflexes and intuition. Every meter traveled is planned, debated, and justified. Each turn of a wheel is a commitment, because mobility introduces risk alongside opportunity. Mars is not a forgiving place for movement. Its surface is uneven, cluttered with rocks, slopes, and hidden hazards. Dust can obscure traction. Temperatures fluctuate dramatically. Communication delays prevent real-time control. A rover must navigate an alien environment with limited awareness, guided by instructions that arrive long after conditions have changed. Mobility on Mars is not exploration by stride. It is exploration by strategy. The early promise of roving exploration lay in its ability to connect observations into narratives. A stationary lander might identify minerals altered by water, but a rover could trace those minerals across layers, linking chemistry to stratigraphy. It could climb slopes, descend into depressions, and follow features that hinted at ancient flow. Mars began to reveal itself not as a collection of static facts, but as a story written across space. This narrative potential transformed scientific priorities. Landing sites were no longer chosen solely for safety or novelty. They were selected for context, places where movement could reveal transitions between environments. Ancient lakebeds, river deltas, and layered deposits became targets, not because they were singularly interesting, but because they promised continuity. Mobility made continuity legible. The act of driving across Mars also changed the tempo of exploration. Flybys delivered shock in moments. Landers delivered depth over months. Rovers delivered patience over years. Progress was incremental, sometimes frustratingly slow. A short drive could take days of planning. A single obstacle could halt movement entirely. Yet this slowness had value. It enforced deliberation. Each decision carried weight. Rovers introduced a new relationship between humans and machines. They were neither remote-controlled vehicles nor independent agents. Instead, they occupied an in-between space, executing human intent with limited autonomy. Scientists proposed targets and routes. Engineers assessed feasibility. The rover carried out commands with local judgment. Exploration became a dialogue across distance and time. This dialogue reshaped scientific interpretation. Because movement was costly, choices mattered. Selecting one path meant excluding others. Each drive encoded a hypothesis about what mattered most. Exploration became explicitly theory-driven. The rover did not wander aimlessly. It followed questions made concrete in terrain. Mobility also introduced serendipity. Despite careful planning, rovers encountered unexpected features. Rocks, unlike those anticipated, textures that defied classification, slopes that revealed new layers. These surprises often proved more informative than planned targets. Movement increased the chance of encountering the unpredicted, expanding the scope of discovery. The psychological impact of mobility should not be underestimated. Images from a fixed lander offer a single horizon. Images from a rover create progression. The landscape changes. Hills approach and recede. Tracks mark passage. Mars begins to feel traversed, rather than merely observed. This sense of journey deepened engagement, both scientific and public. For scientists, mobility enabled comparative reasoning. Differences between nearby outcrops could be analysed. Variations in texture and composition could be linked to environmental change. Mars stopped being a point and became a field. Hypotheses could be tested spatially, not just chemically. This spatial testing was essential for understanding water's role in shaping Mars. Water leaves signatures that are often distributed rather than localized. Channels, deltas, and sediment layers extend across terrain. A rover could follow these signatures, confirming whether they formed through sustained processes or isolated events. Mobility allowed the planet's hydrological memory to be traced rather than inferred. The rise of mobile exploration also required new standards of reliability. A rover's instruments had to withstand years of use under harsh conditions. Wheels endured abrasion. Sensors faced dust accumulation. Power systems operated under variable sunlight. Every component had to function long after launch, often beyond its expected lifespan. Durability became as important as precision. This durability paid dividends. Extended missions transformed rovers into long-term witnesses. They observed seasonal changes, dust storms, and temperature cycles. Mars was no longer sampled briefly, it was monitored. The planet's rhythms, subtle and slow, began to emerge. Mobility also altered the meaning of failure. A rover immobilized by terrain could still function as a stationary platform, continuing to gather data. This resilience changed risk calculus. Movement was encouraged not because it was safe, but because its potential rewards justified its dangers. Exploration became adaptive rather than brittle. The success of roving exploration reshaped expectations for future missions. Mobility was no longer experimental, it was foundational. The question shifted from whether to move to how far and how intelligently. Navigation algorithms improved. Autonomous hazard avoidance expanded. Rovers learned within limits to choose safer paths. Mars demanded competence, and rovers began to meet that demand. Philosophically, mobile exploration blurred distinctions between presence and absence. A rover moving across Mars embodied a form of persistence that flybys and landers could not. It stayed, adapted, and responded. It accumulated experience. Though not conscious, it enacted a continuity of engagement that felt closer to exploration in the traditional sense. This continuity reinforced Mars's status as a world worth sustained attention. Each kilometre travelled added context to previous findings. Each new layer exposed reframed earlier interpretations. Mars's story did not unfold linearly, it deepened. Mobility allowed understanding to mature rather than merely expand. There was also a symbolic dimension to movement. Tracks left in Martian soil carried emotional resonance. They marked the first sustained human-directed traversal of another planet. Though indirect, these tracks represented commitment. Humanity was no longer content to observe Mars from afar or sample it briefly. It was willing to follow the planet's clues wherever they led. Yet mobility did not resolve all challenges. Mars remained vast relative to a rover's reach. Each mission covered only a tiny fraction of the surface. The planet's diversity could not be exhausted by even the most ambitious traverse. Mobility expanded perspective, but it also underscored limitation. This limitation sharpened scientific discipline. Conclusions had to be framed cautiously. Local findings could not be generalized without support. Mobility did not eliminate uncertainty, it structured it. Mars was revealed as complex enough to resist simple narratives. In this resistance lay the true success of mobile exploration. Rovers did not simplify Mars. They complicated it in productive ways. They replaced singular interpretations with layered ones. Water was no longer a binary presence or absence. It became a spectrum of environments changing over time. The rise of mobile exploration marked the moment when Mars stopped being merely examined and began to be read. Its surface was treated as a text, with chapters separated by distance and layers. Movement provided syntax. Without it, the story would remain fragmented. This approach redefined planetary exploration more broadly. Other worlds, too, would require mobility to be understood fully. Static observation could identify features, movement could connect them. The rover became a model for how humanity might engage distant environments responsibly and intelligently. Mars, once imagined through sweeping fantasies, was now approached through measured steps. Each wheel rotation represented patience over impulse, inquiry over assertion. Mobility did not make exploration faster. It made it deeper. In rising from stationary platforms to travelling explorers, Mars exploration entered a new phase, one in which understanding emerged not from isolated facts, but from journeys. The planet's memory, written across its surface, could finally be followed. Once exploration on Mars became mobile, rocks ceased to be obstacles and became archives. Every boulder, outcrop, and layered exposure encountered by a rover represented more than a physical feature. It was a fragment of planetary memory. Unlike Earth, where geological processes constantly recycle the surface, Mars preserves its past with remarkable fidelity. Rocks on Mars are not merely materials, they are time capsules, storing information about environments that no longer exist. This realization transformed how scientists approached the Martian landscape. The goal was no longer simply to identify interesting features, but to decode histories encoded in stone. Each rock carried clues about the conditions under which it formed: temperature, pressure, chemistry, and the presence or absence of water. Together, these clues allowed reconstruction of ancient environments that could not be observed directly. On Earth, interpreting rocks relies heavily on context. Layers are correlated across regions. Fossils provide temporal anchors. Active processes allow direct observation of formation mechanisms. Mars offers none of these conveniences. Its rocks must be read without the benefit of living analogues or ongoing cycles. Interpretation depends on chemistry, texture, structure, and spatial relationships, subtle signatures preserved across immense spans of time. Rovers made this kind of reading possible by bringing instruments directly to the rocks. Cameras revealed grain size and layering. Spectrometers identified mineral composition. Drills exposed interiors untouched by surface alteration. These tools did not merely sample rocks, they interrogated them. Each measurement was a question posed to the past, answered through patterns of matter. The importance of layering cannot be overstated. Layered rocks are records of accumulation. Each layer represents a moment, a deposition event frozen in place. On Mars, these layers often stack in orderly sequences, sometimes hundreds of meters thick. Their regularity suggests sustained processes rather than catastrophic ones. The planet, at times, was stable enough to build sediment slowly, layer by layer. Such stability implies water. Many Martian sedimentary rocks bear mineral signatures that form only in the presence of liquid. Clays, for example, indicate prolonged interaction between rock and water under relatively mild conditions. These minerals do not arise from brief floods or transient melting, they require time. Their presence within layered deposits suggests environments that persisted long enough for chemistry to proceed deliberately rather than violently. Textures reinforce this interpretation. Fine-grained sediments imply calm deposition, often in standing water. Cross-bedding hints at currents shaping sand under consistent flow. Rounded grains suggest transport over distance, smoothed by movement. These features are not ambiguous. They echo terrestrial processes familiar from riverbeds, lake floors, and deltas. Mars rocks speak a language geology recognizes. Yet Mars also complicates this language. Some rocks show evidence of alteration without clear signs of sustained warmth. Minerals appear that could form in cold, acidic, or saline conditions. This diversity suggests that water on Mars was not uniform. It varied in chemistry, temperature, and duration. The planet's hydrological history was not a single chapter, but a series of changing regimes. Rocks also record transitions. A sequence might begin with sediments laid down in water, followed by layers shaped by wind. Such transitions mark environmental shifts, from wetter to drier conditions, from stability to erosion. These shifts are critical for understanding Mars' climate evolution. They reveal not just that conditions changed, but how and when they did so. The concept of rocks as time capsules extends beyond water. Volcanic rocks preserve information about Mars' internal heat and mantle composition. Their chemistry reflects the planet's early differentiation and thermal history. The size and distribution of volcanic features indicate how long Mars remained geologically active. Rocks tell the story of a planet cooling and quieting over time. Impact-related rocks add another dimension. Craters expose deeper layers, bringing ancient materials to the surface. Melted rock records the energy of collisions that shaped Mars early in its history. These impacts were not merely destructive, they were formative. They redistributed materials, altered climates, and perhaps even created temporary environments hospitable to water. Reading these records requires caution. Rocks do not narrate their history explicitly. Interpretation depends on analogy and inference. Yet the absence of biological overprinting on Mars simplifies some aspects of this task. Without plants, animals, or microbes constantly reworking the surface, geological signatures remain clearer. Mars' barrenness, paradoxically, preserves its memory. This preservation turns Mars into a planetary archive, unmatched in accessibility. The Moon preserves early solar system history, but lacks the chemical diversity associated with water. Earth preserves chemical diversity, but erases early records. Mars occupies a middle ground, preserving evidence of water-related processes across deep time. Its rocks are witnesses to environments Earth has forgotten. Rovers extended the concept of sampling from isolated measurements to contextual reading. A single rock can mislead. A sequence of rocks tells a story. Mobility allowed scientists to trace changes across layers and distances, linking chemistry to structure and structure to landscape. Rocks became sentences rather than words, paragraphs rather than letters. This narrative quality reshaped mission goals. Exploration prioritized stratified regions where time could be read vertically as well as horizontally. Cliffs, crater walls, and eroded mesas became prized targets. These natural exposures offered cross-sections through history, revealing sequences otherwise buried. Mars' erosion exposed its archive in ways Earth rarely does. Rocks also forced confrontation with uncertainty. Some features resist definitive interpretation. Minerals can form under multiple conditions. Textures can be ambiguous. Without direct dating methods comparable to those used on Earth, timelines remain approximate. Mars's rocks speak clearly, but not conclusively. They invite hypotheses rather than deliver verdicts. This ambiguity is productive. It encourages integration of multiple lines of evidence. Chemistry must align with texture. Structure must fit context. No single measurement suffices. Understanding emerges through convergence, not assertion. Rocks teach patience as much as they teach history. The emotional resonance of this process should not be overlooked. To read a rock on Mars is to engage with timescales that dwarf human experience. A layer deposited billions of years ago lies beneath a rover's instruments, unchanged since before Earth's continents stabilized. This intimacy with deep time fosters humility. Mars's rocks remind humanity of its brief presence within a much longer story. They also invite reflection on contingency. The conditions recorded in Martian rocks are not exotic anomalies. They resemble environments that once existed on Earth, and in some cases still do. The divergence between the two planets lies not in their origins, but in their trajectories. Rocks make this divergence tangible. In treating rocks as time capsules, Mars exploration moved beyond the search for singular discoveries. The goal was no longer to find one decisive feature, but to assemble a coherent history. Each rock contributed a fragment. Together they formed a mosaic of planetary evolution. This approach also reframed the question of life. Rocks that record long-lasting water environments are potential habitats, whether or not life arose there. Understanding these environments is a prerequisite for evaluating biological potential. The absence of fossils does not negate the importance of habitat reconstruction. Rocks define the stage, even if the actors are missing. Mars rocks thus occupy a dual role. They are records of physical processes and proxies for biological possibility. They allow scientists to ask not only what happened, but what could have happened. This distinction keeps the search for life grounded without extinguishing it. As rovers continued to explore, the archive expanded. New rock types challenged existing models. Unexpected mineral assemblages hinted at unanticipated conditions. Mars proved more complex than initial narratives allowed. Its rocks resisted simplification. This resistance is precisely what makes them valuable. Time capsules that tell only one story are propaganda. Mars's rocks tell many stories, some contradictory, some incomplete. They reflect a planet that changed repeatedly, responding to forces both internal and external. In learning to read these time capsules, humanity learned to listen to a world that speaks slowly. Mars does not reveal itself through dramatic events, but through accumulation. Its rocks whisper rather than shout. To understand them requires attention, patience, and humility. The rise of mobile exploration made this listening possible. Without movement, the archive would remain fragmented. With movement, it became legible. Rocks became guides rather than curiosities. In the next stage of exploration, these time capsules would be used to follow water's pathways across the planet, to read rivers that no longer flow and landscapes shaped by processes long ended. Among the most compelling revelations of Mars exploration is the unmistakable presence of ancient rivers etched into a world that no longer flows. These rivers are not speculative constructs or interpretive fantasies. They are written plainly into the landscape, preserved with a clarity that demands explanation. To read them is to confront a paradox. Mars is dead by present measures, yet its surface carries the unmistakable signatures of sustained, organized movement of water. The planet does not merely hint at a wetter past, it records it. Ancient river systems on Mars reveal themselves through form. Valleys branch and converge in patterns familiar from terrestrial hydrology. Channels widen downstream. Tributaries feed into larger networks. These structures are not random scars. They obey gravitational logic, responding to slope, drainage, and accumulation. Such coherence cannot be produced by wind, lava, or brief catastrophic floods alone. It speaks to water that flowed repeatedly, shaping terrain over time. Reading these rivers requires moving beyond the instinct to search for oceans. Rivers do not require seas to exist. They require gradients, sources, and persistence. On Mars, the sources appear to have been precipitation, snowmelt, or subsurface release. The gradients are carved into highlands and crater rims. The persistence is written in erosion, banks worn smooth, channels incised deeply, sediments transported far from their origin. Rovers brought this abstraction into focus. From orbit, valleys appear as lines and shadows. On the ground, they become layered walls, rounded pebbles, and cross-bedded sediments. These details matter. Rounded pebbles indicate transport by flowing water strong enough to tumble stone against stone. Cross-bedding reveals currents depositing material at angles that shift with flow direction. Fine laminations suggest settling in calm water after transport. Each feature is a letter in the grammar of rivers. The act of reading these features is not merely descriptive, it is reconstructive. Scientists infer flow rates, durations, and water volumes from geometry and sediment size. Narrow channels with steep walls suggest fast-moving water. Broad, shallow channels imply slower flow. Delta-like deposits indicate where rivers met standing bodies of water, spreading sediments as energy dissipated. Mars rivers, though silent now, carry quantitative information about their former vitality. One of the most striking aspects of Martian river systems is their scale. Some valleys stretch for hundreds of kilometers. Their networks span regions rather than isolated sites. This scale argues against brief, isolated events. While catastrophic floods can carve channels quickly, they tend to leave chaotic signatures, scoured landscapes, jumbled debris. Many Martian valleys instead show ordered development, consistent with long-term surface runoff. This runoff implies climate. Rivers do not persist without replenishment. For water to flow repeatedly, Mars must once have supported a hydrological cycle: precipitation, accumulation, and drainage. Whether this cycle resembled Earth's remains debated, but its existence challenges earlier assumptions that Mars was always cold and dry. The planet once occupied a different climatic regime. Yet these rivers end abruptly. They do not lead to modern seas. They terminate in basins that are now dry or in deposits buried by later processes. The endings matter as much as the beginnings. They suggest that water had destinations that no longer exist in the same form. Lakes evaporated, froze, or drained underground. Rivers became fossils of motion without present purpose. This fossilization is central to Mars's haunting character. On Earth, rivers are alive. They shift course, flood, retreat, and return. On Mars, they are arrested mid-gesture. The planet preserves them not as active systems, but as frozen movements. Reading them is like reading a score after the music has stopped. The stillness sharpens interpretation. Without vegetation to obscure channels or tectonics to erase them, Martian rivers remain legible for billions of years. Their clarity forces a confrontation with duration. These rivers did not carve themselves overnight. They required time measured not in seasons, but in geological epochs. The question then becomes why they stopped. The answer lies not in the rivers themselves, but in planetary change. As Mars lost atmosphere, surface pressure dropped. Liquid water became unstable. Temperatures fell. What once flowed became ice or vapor. The hydrological cycle broke. Rivers did not migrate elsewhere, they ceased to function. This cessation reframes Mars' death. It was not sudden. It was gradual, systemic, and irreversible. The rivers record a process of decline rather than catastrophe. They show a planet transitioning from active to inert, from dynamic to static. In this sense, Mars's rivers are elegies rather than monuments. Reading ancient rivers also complicates the search for life. Rivers are not merely conduits of water, they are organizers of environments. On Earth, rivers concentrate nutrients, create gradients, and sustain diverse habitats. If life ever emerged on Mars, rivers would have been among its most favorable settings. The absence of life today does not erase the possibility that rivers once hosted it. This possibility elevates the importance of river deposits. Sediments laid down by flowing water can trap and preserve chemical signatures. Fine-grained materials can protect organic molecules from radiation and oxidation. Deltas and floodplains, in particular, are natural archives of biological potential. Reading Martian rivers is therefore not only about reconstructing climate, but about identifying where life's traces might linger. However, reading does not guarantee finding. Mars's rivers may have flowed before life could take hold or after conditions became marginal. Life's absence, if confirmed, would not invalidate the river's significance. It would underscore the contingency of biology. Favorable environments do not guarantee emergence. Rivers create opportunity, not inevitability. There is also a methodological humility in reading ancient rivers. Interpretation relies on analogy to Earth, yet Mars is not Earth. Differences in gravity, atmosphere, and geology alter how water behaves. Channels that look familiar may not have functioned identically. Scientists must balance recognition with restraint, avoiding the temptation to over-translate. This balance reflects a maturation of planetary science. Early interpretations of Mars were too eager, too anthropocentric. Modern readings are cautious, layered, and probabilistic. Rivers are not assumed to mean oceans, nor life, nor permanence. They are treated as evidence of specific processes under specific conditions. Reading rivers on a dead planet also changes how death itself is understood. Mars is not dead in the sense of inertness. Its surface continues to change through dust movement, impacts, and seasonal processes. What has died is a mode of planetary functioning, the ability to sustain surface water. Rivers mark the boundary between these states. This boundary has ethical resonance. In an era of planetary-scale environmental change on Earth, Mars rivers serve as a reminder that loss can be permanent. Planetary systems can cross thresholds from which recovery is not straightforward. Mars shows that water, once lost from the surface, may not return. Yet Mars is not a prophecy. Earth is not Mars. The differences between the two worlds are as important as their similarities. Reading ancient rivers on Mars clarifies what Earth has that Mars lacks: active geology, a robust atmosphere, and ongoing cycles that renew surface conditions. Mars's rivers illuminate Earth's fortune by contrast. The act of reading these rivers also reshapes exploration itself. It encourages following flow paths, tracing deposits, and prioritizing stratigraphic context. Exploration becomes a kind of hydrological archaeology, reconstructing systems that once connected highlands to basins. Movement across terrain becomes movement through time. This temporal movement deepens engagement. Each channel crossed by a rover represents a moment when Mars was different. Each layer climbed represents a transition. The planet's surface becomes a sequence rather than a snapshot. Rivers provide narrative continuity in a world otherwise defined by stillness. In the end, reading ancient rivers on Mars is an exercise in disciplined imagination. The evidence is real, but the world it describes no longer exists. Scientists must envision conditions without projecting desires. They must reconstruct without romanticizing. The rivers invite empathy, but demand rigor. Mars does not hide its rivers. It displays them openly, etched across deserts that never knew vegetation. Their openness is unsettling. They show that Mars once had what it needed and lost it. The rivers are not mysteries because they are unclear. They are mysteries because their implications are profound. They tell of a planet that flowed, that organized itself around water, and then fell silent. They force humanity to confront planetary mortality not as abstraction, but as landscape. On Mars, the rivers are gone, but they are not erased. They remain, readable and unanswerable, flowing only in memory. As Mars' ancient rivers, lake beds, and altered minerals came into focus, a crucial distinction emerged, one that reshaped the entire search for life beyond Earth. Habitability is not the same as life. A planet can possess environments capable of supporting life without ever actually hosting it. Mars forced science to confront this difference with unusual clarity. For decades, the assumption had been simple: where there is water, there may be life. This assumption was not unreasonable. On Earth, water and life are inseparable. Wherever liquid water persists, oceans, rivers, lakes, deep crustal fractures, life finds a way. Water dissolves nutrients, facilitates chemistry, and stabilizes complex molecules. It is the medium through which biology operates. If Mars had water, the logic went, then Mars might have had life. But as evidence accumulated, the simplicity of this logic began to fray. Mars clearly had water, yet no clear evidence of life emerged. The absence was not definitive, but it was persistent. Each new discovery strengthened the case for past habitability while leaving the question of life unresolved. Mars became the first world where habitability could be studied independently of biology. This separation marked a conceptual turning point. Habitability refers to environmental potential, the presence of conditions that could support life. Life refers to historical outcome, the fact that biology did emerge and persist. Confusing the two risks, mistaking possibility for evidence. Mars made that mistake impossible to ignore. Habitability on Mars appears to have been real, and at times, extensive. The planet once supported liquid water at the surface. It possessed chemical energy sources. It had stable environments lasting long enough for complex processes to unfold. In purely physical and chemical terms, Mars checked many of the boxes associated with life-supporting worlds. Yet habitability does not guarantee genesis. Life is not a chemical inevitability. It is a process contingent on sequences of events, thresholds crossed, and perhaps rare conditions aligning in the right order. Mars teaches that a planet can do many things right and still remain lifeless. This realization carries profound implications. It suggests that the emergence of life may be less common than the emergence of habitable environments. The universe may be filled with planets that could host life but never did. Mars is not a failure. It is a data point clarifying how narrow the path from chemistry to biology may be. Understanding this distinction also reframes disappointment. The absence of life on Mars, if confirmed, does not negate its importance. Instead, it elevates it. Mars becomes a control case, a world that approached habitability but did not cross the threshold. Studying such worlds may be as informative as studying living ones. This reframing tempers expectations for exoplanet exploration as well. Discovering planets in habitable zones does not imply discovering life. It implies discovering opportunity. Mars reminds us that opportunity and outcome are not the same. The search for life must therefore be patient, probabilistic, and prepared for negative results. Mars also complicates the definition of habitability itself. Early concepts treated habitability as a binary condition. Either a planet could support life or it could not. Mars reveals habitability as a gradient. Conditions vary in intensity, duration, and stability. Some environments may be marginal, others transient. Habitability can flicker on and off over geological time. On Mars, water did not exist uniformly. It appeared in certain regions, during certain epochs, under specific conditions. Lakes formed and vanished. Rivers flowed and dried. Environments favorable for life may have existed briefly or intermittently. Such intermittency could limit biological potential even in the presence of water. This nuance underscores the importance of time. Life does not emerge instantly. It requires sustained conditions. A planet that oscillates between habitable and uninhabitable states may never allow life to gain a foothold. Mars's climatic instability may have undercut its biological potential, even as it carved rivers and deposited sediments. Mars also lacked certain stabilizing factors present on Earth. Its smaller size reduced internal heat. Its magnetic field weakened or vanished early, exposing the surface to radiation. Its atmosphere thinned, allowing water to escape. These factors do not preclude habitability outright, but they constrain it. Mars' environments may have been habitable in isolation, yet vulnerable in aggregate. This vulnerability highlights the difference between local habitability and planetary habitability. A lake can be habitable even if the planet as a whole is hostile. Life could exist in niches while remaining undetectable globally. Mars may have hosted such niches, brief, isolated, and easily erased. The absence of evidence does not prove absence of life, but it narrows plausible scenarios. At the same time, Mars resists special pleading. The longer exploration continues without clear biological signals, the more caution is warranted. Habitability alone cannot justify assumptions of life. Mars demands evidentiary discipline. Claims must rest on data, not desire. This discipline strengthens planetary science rather than weakening it. By separating habitability from life, scientists can study each on its own terms. Habitability becomes a measurable property. Temperature ranges, chemical gradients, energy availability. Life becomes an empirical question. Did biological processes leave detectable traces? Mars offers a rare opportunity to study the first question without the complication of the second. Its rocks record environments, not organisms. They allow reconstruction of conditions without biological overprinting. In this sense, Mars is a purer laboratory for habitability studies than Earth itself. This purity extends to philosophical reflection. Humanity often assumes that life emerges wherever it can. Mars challenges that assumption. It suggests that life may be fragile, contingent, and perhaps rare. This possibility does not diminish life's value, it amplifies it. If life is not inevitable, then its persistence on Earth is remarkable rather than ordinary. Mars thus shifts the emotional tone of exploration. Instead of seeking reassurance that life is common, it invites humility about life's precariousness. It encourages appreciation rather than entitlement. The universe may not be designed to produce life easily or often. This shift does not extinguish hope. It refines it. The search for life becomes more careful, more selective, and more profound. Each detection would carry greater weight. Mars prepares us for a universe where life, if found, is precious precisely because it is not guaranteed. The habitability versus life distinction also affects how future missions are designed. Instead of searching indiscriminately for biological signatures, exploration focuses on reconstructing environmental histories. Where were conditions most stable? Where did water persist longest? Where were chemical gradients richest? These questions precede biological claims. Mars' story suggests that life, if it arose, would most likely have done so early and retreated underground as surface conditions deteriorated. Habitability may have persisted below the surface long after it vanished above. This possibility shifts attention downward toward environments shielded from radiation and temperature extremes. Yet even subsurface habitability does not guarantee life. It extends opportunity, not certainty. Mars teaches that opportunity can be squandered by planetary evolution beyond any organism's control. Habitability can close faster than life can adapt. This sobering lesson resonates beyond Mars. It applies to exoplanets, icy moons, and even Earth's future. Habitability is dynamic. It can be gained, lost, and regained. Life must navigate these changes or perish. Mars shows what happens when it cannot. Importantly, Mars also cautions against equating life with value. A lifeless Mars is not a failure. It is a world with its own history, shaped by forces as legitimate as those that shaped Earth. Its significance does not depend on hosting biology. It matters because it reveals how planets behave, change, and sometimes fail. By disentangling habitability from life, Mars deepens humanity's understanding of both. It clarifies that life is not simply a chemical consequence, but a rare and contingent phenomenon. It reframes the search for life as an inquiry into possibility rather than promise. Mars does not answer whether life is common or rare. It reframes the question. It shows that the universe can create habitable worlds without creating life. It teaches that the presence of water is necessary but not sufficient. In doing so, Mars becomes one of the most important lessons in astrobiology, not because it confirms our hopes, but because it disciplines them. The red planet stands as a world that could have lived, may have lived, and yet does not speak. That silence is not empty. It is instructive. It tells us that habitability is an invitation, not a guarantee. As Mars's surface revealed itself to be cold, dry, and relentlessly exposed, attention began to turn downward. If the planet had once been habitable and later became hostile, where might conditions have lingered longest? The surface, battered by radiation and stripped of atmospheric protection, seemed an unlikely refuge. Beneath it, however, lay a realm less altered by Mars's decline. The question beneath the surface emerged not as a speculative detour, but as a logical extension of everything the planet had revealed so far. Mars's surface is deceptive in its clarity. Its openness makes it readable, but also unforgiving. Without a thick atmosphere or magnetic shield, the surface is exposed to radiation that degrades complex molecules. Temperatures fluctuate dramatically. Oxidizing chemistry breaks down organics. Even if life once existed on the surface, its traces would struggle to survive intact across billions of years. The surface, in other words, is a poor archivist of biology. The subsurface offers different conditions. A few meters of rock or soil can provide substantial shielding from radiation. Temperatures stabilize with depth. Ice can persist where liquid water cannot exist at the surface. Chemical gradients may be preserved longer. On Earth, life thrives beneath the surface in environments once thought sterile, within rocks, aquifers, and deep fractures. Mars invites comparison not because it mirrors Earth, but because it shares physical principles that make subsurface environments more stable than exposed ones. This stability is central to the subsurface question. If Mars lost its atmosphere gradually, surface conditions would have deteriorated long before the subsurface became inhospitable. Water could retreat downward, freezing or remaining liquid under pressure. Chemical energy sources could persist even as sunlight faded as a driver of surface processes. The planet's habitability may have contracted rather than vanished. Evidence supports this contraction. Ice is abundant beneath the Martian surface, particularly at higher latitudes, but not exclusively there. Radar data suggest buried glaciers and layered ice-rich deposits. In some regions, impacts have exposed bright ice just below the surface, implying shallow reservoirs protected by a thin layer of soil. Water did not simply escape Mars. Much of it went underground. The presence of subsurface water, even in frozen form, reframes the search for habitability. Ice is not inert. Under the right conditions, it can melt locally. Heat from radioactive decay, residual geothermal activity, or transient events like impacts could create pockets of liquid water beneath the surface. These environments would be isolated, intermittent, and difficult to detect, but not impossible. Such environments would differ fundamentally from surface rivers and lakes. They would not be driven by climate, but by internal or localized energy. They would be hidden rather than expansive. Their chemistry might be distinct, influenced by rock-water interactions rather than atmospheric processes. If life ever retreated underground on Mars, it would have done so into a world unlike the one imagined during the era of canals and seas. This retreat carries implications for detection. Subsurface life would not announce itself through visible structures or surface alteration. Its signatures would be subtle: chemical imbalances, trace gases, or altered minerals. Detecting such signatures requires precision and restraint. The subsurface question, therefore, demands a different mode of exploration, one less reliant on imagery and more on inference. It also demands caution. The desire to find life can lead to overinterpretation. Chemical anomalies may have non-biological explanations. Geological processes can mimic biological signatures. Mars, already a lesson in illusion, requires skepticism sharpened by humility. The subsurface may be promising, but promise is not proof. At the same time, Dismissing the subsurface prematurely would ignore a central lesson of planetary evolution. Environments change unevenly. What is lethal in one region may be tolerable in another. What is hostile at the surface may be benign below it. Mars's history suggests a planet that shut down from the outside inward, not all at once. This inward retreat resonates with broader astrobiological thinking. On icy moons, subsurface oceans are considered more promising than surfaces. On early Earth, life may have begun in protected environments shielded from harsh surface conditions. The subsurface is not a marginal refuge. It may be a primary theatre of biology across the universe. Mars, however, complicates this optimism. Its internal heat is limited. Its geological activity waned early. Any subsurface habitats would be constrained by declining energy availability. Life, if present, would have faced narrowing margins. Survival would depend on efficiency, adaptability, and perhaps dormancy. Mars's subsurface is not a sanctuary, it is a test. This test sharpens the philosophical stakes of exploration. If life cannot persist even underground on a planet that once had surface water, what does that imply about life's resilience? Does biology require sustained planetary-scale stability, or can it endure indefinitely in isolated pockets? Mars offers a natural experiment whose outcome remains unresolved. The subsurface question also intersects with ethics. Exploring beneath the surface risks contamination. Introducing terrestrial microbes could compromise environments that have remained isolated for eons. The very act of searching could erase what is sought. Mars forces exploration to balance curiosity with restraint, especially as attention shifts toward environments most likely to preserve life. This balance influences mission design. Instead of aggressive drilling, exploration often prioritizes shallow sampling and indirect measurement. The goal is to learn without overwhelming. Mars demands patience not only scientifically, but morally. The subsurface is a domain that cannot be rushed. The difficulty of access also shapes interpretation. Because subsurface environments are inferred rather than observed directly, uncertainty remains high. Models proliferate. Hypotheses compete. Mars resists closure. Each line of evidence opens new questions rather than resolving old ones. The subsurface remains a realm of disciplined speculation. This speculation is grounded, however, in physical reality. Mars's gravity, composition, and thermal history constrain what is possible. The planet cannot sustain Earth-like deep biospheres indefinitely. Any subsurface habitability would be limited in extent and duration. The question is not whether Mars hides vast underground ecosystems, but whether it could have sheltered small, persistent ones. The absence of clear answers does not diminish the importance of the question. On the contrary, it defines the frontier of Mars exploration. The surface has told much of its story. Beneath it lies the remaining uncertainty, compressed, shielded, and difficult to reach. This uncertainty also reshapes expectations. Finding life beneath Mars's surface would be extraordinary, but not finding it would also be informative. A sterile subsurface would suggest that life's requirements are narrower than habitability alone implies. Mars would then stand as a world that crossed many thresholds without completing the journey to biology. Such a result would not render Mars a failure. It would render it a boundary case, a planet that approached life closely enough to teach us where the line may lie. The subsurface question is therefore not merely about discovery, but about definition. It asks what life truly needs, and how forgiving planetary environments must be to sustain it. Mars does not answer this question directly. It invites it. The planet's silence beneath the surface is not a denial, but a challenge. It urges exploration that is careful, patient, and honest about uncertainty. In turning attention downward, Mars exploration acknowledges its own limits. The most important environments may be the hardest to access. The most meaningful answers may be the slowest to obtain. This recognition marks a maturation of planetary science, one that values depth over spectacle. The question beneath the surface remains open. It is not a question that can be answered quickly or conclusively. It is a question that demands new tools, new methods, and perhaps new ways of thinking about life itself. Mars, once imagined as a world of surface canals and open seas, now asks us to look inward. What remains beneath its silent plains may not be what we hope to find, but whatever it is, it will clarify what kind of universe we inhabit. The surface has spoken. The subsurface waits. Mars has become more than an object of study. Over decades of exploration, it has assumed a role that is both scientific and symbolic, a warning world. This role does not arise from analogy alone or from convenient moralizing. It emerges from evidence written across an entire planet. Mars shows what happens when the conditions that sustain habitability unravel, not suddenly, but inexorably. It is a world that crossed thresholds and did not recover. The warning embedded in Mars is not simple or deterministic. Earth is not destined to become Mars. The two planets differ in mass, internal dynamics, magnetic protection, and geological vitality. Yet Mars demonstrates that planetary environments are not fixed states. They are processes. They evolve, respond to internal and external forces, and sometimes fail. Mars is a case study in planetary vulnerability. At its core, Mars's warning lies in loss. The planet lost atmosphere. It lost surface water. It lost internal heat and magnetic shielding. Each loss compounded the next. As the atmosphere thinned, water became unstable. As water disappeared from the surface, chemical weathering slowed. As geological activity waned, recycling ceased. Mars did not collapse in a single catastrophe. It faded through interconnected declines. This interconnectedness is what makes Mars instructive. Planetary systems do not fail in isolation. Feedback loops amplify change. Small differences early in a planet's history can cascade into radically different outcomes. Mars and Earth likely began with similar materials and processes, yet diverged sharply. Mars shows that habitability is not simply bestowed by formation, it must be sustained. The planet also reveals how protective systems matter. Mars' early magnetic field likely shielded its atmosphere from solar stripping. When that field weakened or vanished, the atmosphere became vulnerable. Over time, the solar wind eroded it, thinning the blanket that once trapped heat and supported liquid water. Mars illustrates that invisible forces, fields, flows, and balances can determine planetary fate as much as visible features. This lesson resonates beyond geology. It reframes how habitability is evaluated elsewhere. A planet's position relative to its star matters, but so does its ability to retain atmosphere, recycle materials, and buffer change. Mars warns against simplistic definitions of Earth-like. Superficial similarity does not guarantee long-term stability. Mars also warns against assuming that habitability, once achieved, is permanent. The planet appears to have supported surface water for extended periods, perhaps hundreds of millions of years. Yet this was not enough to secure its future. Habitability can be temporary. Worlds can pass through habitable phases and then leave them behind. This possibility expands the search for life while also tempering optimism. In this sense, Mars shifts the focus from place to time. The question is not only where life might exist, but when. A planet may be habitable only briefly in cosmic terms. Life must emerge, adapt, and persist within those windows. Mars suggests that missing such a window or failing to endure its closure leads to planetary silence. The warning is sharpened by Mars's stillness. Earth's dynamic systems constantly mask vulnerability. Weather, oceans, and biology create an illusion of permanence. Mars lacks these distractions. Its surface is quiet, its changes slow and cumulative. This stillness allows its history to be read clearly. It is a warning preserved rather than erased. Mars also challenges the assumption that technological intervention can easily reverse planetary decline. Imagined futures often portray Mars as a terraforming candidate, a world that can be remade through engineering. Yet Mars's losses are deep-rooted. Rebuilding an atmosphere, restoring a magnetic field, or restarting internal heat are not trivial tasks. Mars suggests that planetary-scale change is not easily undone. This implication extends to Earth not as a prediction, but as a caution. Planetary systems operate on scales that dwarf human timescales and capacities. While humanity can influence climate and environments, restoring fundamental planetary processes is another matter entirely. Mars reminds us that some losses are effectively permanent. The planet also warns against complacency born of familiarity. Earth's stability can feel natural, even inevitable. Mars undermines that feeling. It shows that rocky planets can look promising and still fail. It invites humility about Earth's resilience and a renewed appreciation for the processes that sustain it. Mars's warning is not one of immediate doom, but of long-term consequence. The changes that rendered Mars barren unfolded over immense spans of time. This temporal distance can dull urgency, yet the lesson is precisely about accumulation. Small imbalances, if sustained, reshape worlds. Mars is a record of gradual drift crossing irreversible thresholds. This warning is particularly relevant in an era of planetary awareness. Humanity now understands that it influences Earth at global scale. Mars provides context for that understanding. It shows what a planet looks like after its sustaining cycles break down completely. It suggests that planetary health is not a metaphor, but a measurable condition. At the same time, Mars cautions against moralizing nature. Mars did not fail because of negligence or choice. It followed physical laws. Its fate was shaped by size, composition, and cosmic environment. The warning is not punitive, it is explanatory. It tells us what can happen, not what must. This distinction matters. Mars is not an indictment of Earth's future, but a reference point. It helps identify which processes are essential and which are fragile. It clarifies the difference between reversible and irreversible change. In doing so, it sharpens scientific understanding, rather than offering simplistic allegory. Mars also reframes the search for life beyond Earth. If many worlds pass through habitable phases and then lose them, life may be rare, not because conditions are uncommon, but because persistence is difficult. Mars stands as a reminder that the universe may produce many near misses, worlds that almost sustain life, or sustain it briefly, and then fall silent. This perspective deepens the meaning of any future discovery of life elsewhere. Finding life would not merely demonstrate abundance, it would demonstrate endurance. Mars, by contrast, demonstrates how easily endurance can be lost. Yet the warning is not purely negative. Mars also teaches resilience of a different kind. Its surface preserves history. Its rocks remember environments long gone. In losing activity, Mars gained legibility. Earth's dynamism obscures its early history. Mars' stillness reveals it. The warning world is also an archive world. This dual role, warning and record, gives Mars enduring value. It is not merely a cautionary endpoint, but a guide. By studying how Mars changed, scientists learn which processes matter most in sustaining habitability. Mars does not simply say this can happen, it says how it happens. In this sense, Mars is not a story of failure, but of consequence. It is a planet that followed the rules and arrived at a different outcome. Understanding that outcome enriches planetary science and sharpens humanity's awareness of its own world. Mars does not demand fear. It demands attention. It invites careful study, long-term thinking, and respect for planetary systems. It reminds us that worlds are not static backdrops for life, but dynamic participants in it. As exploration continues, Mars' role as a warning world will evolve. New data may soften or complicate the narrative. Subsurface discoveries may reveal resilience where surface readings suggest loss. The warning is not finished being written, but already Mars has earned its place as the solar system's most eloquent lesson in planetary fragility. It stands as a reminder that habitability is precious, contingent, and finite. Mars does not threaten Earth. It instructs it, and in that instruction lies its lasting power. For much of human history, the outer solar system existed as an abstraction. Beyond the orbit of Mars, the planets were visible only as distant points of light, brighter than stars, yet resolutely opaque. Their immense distances flattened them into symbols rather than places. Even as inner worlds gradually yielded to close inspection, the giants beyond remained concealed behind scale and darkness. The revelation of the outer solar system did not arrive through gradual refinement, but through sudden exposure. When spacecraft finally crossed the threshold, the familiar architecture of the solar system dissolved, replaced by something larger, stranger, and more dynamic than anyone had anticipated. Before these encounters, the gas giants were often treated as secondary actors, massive but simple, important mainly for their gravitational influence. They were assumed to be monotonous spheres of gas, lacking the geological and chemical complexity that made smaller worlds compelling. Their moons, by extension, were presumed to be inert, icy debris orbiting planets too far from the Sun to matter much in discussions of habitability or planetary evolution. That assumption did not survive first contact. When spacecraft approached the giant planets, they revealed systems unto themselves, miniature solar systems governed by gravity, energy exchange, and interaction on a staggering scale. Each giant planet was surrounded by a retinue of moons, rings, and magnetospheric structures that transformed the notion of what a planetary system could be. The solar system was no longer a simple hierarchy radiating outward from the Sun. It was a nested complexity, worlds within worlds. The gas giants themselves defied simplicity. Their atmospheres were not static envelopes, but turbulent, stratified systems driven by internal heat as much as solar energy. Bands of clouds wrapped around entire planets, shaped by rapid rotation and deep convection. Storms raged for decades or centuries, dwarfing anything on Earth. These planets were not passive recipients of sunlight. They were active engines, radiating energy left over from their formation. This internal heat proved crucial. It meant that the outer solar system was not as cold or inert as distance alone would suggest. Energy flowed through these worlds in ways that could not be explained by sunlight. The giants were not merely colder versions of inner planets. They operated under different rules. Their gravity reshaped space around them. Immense magnetospheres trapped charged particles, generating radiation environments powerful enough to alter the surfaces of nearby moons. Tidal forces flexed and stretched orbiting bodies, converting orbital energy into heat. The outer solar system emerged not as a frozen wasteland, but as a domain of interaction, mechanical, electromagnetic, and thermal. The true revelation, however, lay with the moons. As spacecraft began to resolve these satellites as worlds rather than points, expectations collapsed again. The moons of the giant planets were not uniform blocks of ice and rock. They were diverse, active, and in some cases startlingly complex. Some were scarred by ancient impacts. Others displayed surfaces renewed by processes still ongoing. A few exhibited evidence of internal oceans hidden beneath frozen shells. The idea that the search for habitable environments must focus on planets alone was abruptly outdated. This shift required a rethinking of scale. Habitability had long been associated with Earth-sized worlds, orbiting at just the right distance from their stars. The outer solar system challenged this framework. Here were environments far from the Sun, yet potentially warm inside. Here were worlds smaller than planets, yet geologically alive. Energy, it turned out, did not have a single source. The revelation of the outer solar system also forced a reassessment of formation history. The giant planets likely formed early, sweeping up vast amounts of gas and shaping the architecture of the solar system. Their moons formed within circumplanetary disks, analogous to miniature versions of the disk that produced the planets themselves. These disks produced families of worlds with shared origins yet divergent paths. This shared origin with divergence pattern echoed what had already been observed among the planets. Similar starting conditions did not guarantee similar outcomes. Small differences in composition, orbit, or timing could lead to radically different evolutions. The outer solar system thus reinforced a central lesson of planetary science. Outcomes are contingent, not predetermined. The scale of these systems also altered perception. Rings encircled planets in structures both delicate and massive, composed of countless particles interacting through gravity and collision. They served as laboratories for understanding disk dynamics, processes relevant not only to planetary rings, but to the formation of planets and stars themselves. The outer solar system did not merely add content to planetary science, it expanded its conceptual reach. Equally transformative was the realization that the outer solar system preserved conditions closer to those of the early solar system. Far from the Sun's heat, volatile compounds survived that were lost or altered closer in. Ices containing water, ammonia, methane, and more complex molecules remained intact. These materials offered clues to the raw ingredients available during planet formation. The outer solar system became a chemical archive as well as a dynamic environment. This archival role intersected with questions of life. If organic compounds were abundant beyond the snowline, then the building blocks of life were not confined to Earth's neighborhood. The ingredients for biology appeared to be widespread. What mattered was not merely their presence, but the environments in which they could be assembled, concentrated, and energized. The revelation of internal heating mechanisms within moons intensified this line of thought. Tidal heating could keep interiors warm long after radioactive heat diminished. Liquid water could exist beneath ice, protected from radiation and vacuum. In these hidden oceans, chemistry could proceed over immense timescales. Life, if it arose, would not need sunlight. The outer solar system suggested alternative pathways to habitability. This suggestion unsettled traditional hierarchies. The sun was no longer the sole arbiter of potential life. Planets were no longer the exclusive hosts of complexity. The definition of a world expanded to include bodies once dismissed as secondary. The outer solar system forced science to relinquish its inner world bias. There was also a psychological shift. The farther spacecraft travelled, the less the solar system resembled a familiar arrangement of rocks circling a star. It became something more alien, layered, and surprising. The outer regions felt less like an extension of the inner solar system and more like a different regime entirely, one governed by cold, distance, and internal energy rather than warmth and sunlight. This alien quality deepened fascination rather than diminishing it. The giant planets and their moons did not resemble Earth, yet they mattered profoundly. They demonstrated that planetary systems are not uniform. Diversity is not an exception. It is the rule. The solar system's most surprising worlds lay not near the sun, but beyond the region once considered relevant. The revelation also carried methodological consequences. Studying the outer solar system required long-duration missions, robust instruments, and patience. Signals travelled slowly. Light was weak. Conditions were harsh. Exploration here was not about quick returns. It was about endurance. The outer solar system demanded commitment commensurate with its scale. This commitment paid off in perspective. Seeing the solar system whole, from its rocky inner planets to its vast outer realms, clarified Earth's place within a broader context. Earth was neither central nor peripheral. It was one outcome among many. The solar system was not arranged for convenience or familiarity. It was shaped by physics, chance, and time. The outer solar system thus completed a transformation begun with Mars. Where Mars had taught lessons about planetary loss and fragility, the giant planets and their moons taught lessons about abundance and possibility. They showed that environments conducive to complexity could arise in unexpected places, driven by forces independent of stellar warmth. This abundance did not imply that life was common. It implied that the universe was inventive. Nature produced varied solutions to the problem of energy and chemistry. Some solutions led to barren landscapes, others to dynamic interiors hidden beneath ice. The outer solar system revealed that habitability could be concealed rather than obvious. Perhaps most importantly, these revelations dissolved any remaining notion that the solar system could be understood from Earth alone. The outer planets were not marginal, they were integral. They shaped the solar system's structure, preserved its history, and expanded its possibilities. To ignore them was to misunderstand the whole. The unveiling of the outer solar system did not answer the question of life beyond Earth. It reframed it. It shifted attention from planets to systems, from surfaces to interiors, from sunlight to energy. It suggested that the most promising environments might be those least visible. In revealing the giants and their moons, exploration expanded not only knowledge, but imagination, anchoring it more firmly to reality than ever before. The solar system grew larger, richer, and more complicated. And with that growth came a deeper appreciation for how little had been assumed correctly. The outer solar system was not empty. It was full of worlds, processes, and possibilities that had waited patiently to be seen. As the outer solar system came into focus, one of its most counterintuitive revelations was that some of its most dynamic worlds were hidden beneath frozen surfaces. Ice, long associated with sterility and stasis, turned out to be a mask rather than a verdict. Beneath shells of frozen water lay environments shaped by heat, motion, and chemistry, worlds sealed away from sunlight, yet potentially active for billions of years. The idea that ice could conceal complexity rather than extinguish it transformed how planetary science understood both habitability and life. At first glance, the icy moons of the outer solar system appear inhospitable beyond debate. Their surfaces are locked in perpetual cold. Temperatures plunge far below the freezing point of water. Sunlight is weak and distant, offering little energy to drive familiar processes. From a surface perspective, these moons resemble frozen relics, unchanging, inert, and hostile. Yet this surface view is misleading. Ice, unlike rock, is not rigid at planetary scales. Under sufficient pressure and over long spans of time, it flows. It fractures, convects, and reforms. More importantly, ice insulates. Beneath thick shells, heat can be retained far more effectively than on exposed rock. This insulation creates the possibility of liquid environments sealed away from the vacuum of space. The source of this heat is not sunlight, but gravity. As icy moons orbit massive planets, their paths are rarely perfect circles. Slight orbital eccentricities cause periodic stretching and compression as gravitational forces vary. This flexing generates friction within the moon's interior, converting orbital energy into heat. The process is relentless and predictable, operating as long as the orbit remains perturbed. This mechanism, tidal heating, redefined where scientists looked for activity. Worlds once dismissed as too cold to matter suddenly became candidates for internal oceans. The outer solar system revealed that distance from the sun does not determine thermal destiny. Energy can arise from motion as well as radiation. Evidence for subsurface oceans accumulated through multiple lines of observation. Surfaces fractured in patterns suggesting movement beneath. Regions showed signs of resurfacing, where old terrain had been erased and replaced. Magnetic measurements hinted at conductive layers below ice, most plausibly salty liquid water. Together, these clues pointed downward. The concept of a subsurface ocean challenges intuition. On Earth, oceans are exposed, interacting constantly with atmosphere and sunlight. On icy moons, oceans would be buried beneath kilometers of ice, isolated from direct contact with space. Yet isolation does not imply lifelessness. On Earth, deep oceans and subsurface environments host thriving ecosystems independent of sunlight. Energy flows from chemical gradients rather than photosynthesis. Life, it turns out, does not require light. It requires energy and stability. These hidden oceans may provide both. Shielded from radiation and surface volatility, subsurface environments could remain stable over immense timescales. Water-rock interactions at the ocean floor could generate chemical energy. Salts and minerals dissolved in water could facilitate complex chemistry. The ingredients for life, if present, would be protected rather than exposed. This possibility reframed the search for life beyond Earth. Habitability was no longer confined to surfaces bathed in starlight. It could exist in darkness, driven by forces invisible from afar. Worlds beneath ice expanded the definition of what it means to be alive-friendly. The implications extend beyond specific moons. If subsurface oceans can persist in the outer solar system, then similar environments may be common elsewhere. Icy bodies are abundant in planetary systems. Many orbit giant planets, others drift freely. If gravity and motion can generate heat, then hidden oceans may be widespread. Life's potential habitat expands dramatically under this framework. Yet these environments are not without challenges. Isolation limits nutrient exchange. Energy sources may be finite or diffuse. The chemistry of subsurface oceans could differ significantly from Earth's, favoring unfamiliar pathways. Life, if it arises, would not mirror terrestrial biology easily. Worlds beneath ice may host forms of complexity that challenge existing assumptions. The difficulty of access compounds these uncertainties. Subsurface oceans cannot be sampled directly without penetrating thick ice shells. Surface observations must suffice, interpreted cautiously. Indirect evidence must be weighed against alternative explanations. Worlds beneath ice resist easy confirmation, demanding patience and restraint. This resistance mirrors a broader theme in planetary exploration. The most promising environments may be the hardest to reach. The outer solar system teaches that habitability is often hidden, requiring inference rather than observation. Exploration becomes an exercise in humility as much as ingenuity. There is also a philosophical dimension to these worlds. They invert traditional hierarchies. Instead of open skies and visible oceans, they offer darkness and concealment. Instead of energy from above, they rely on energy from within. These inversions challenge anthropocentric expectations. Life elsewhere may thrive under conditions humans find alien or inaccessible. This realization tempers optimism without extinguishing it. Worlds beneath ice are not guarantees of life. They are opportunities framed by constraint. Their existence broadens the scope of inquiry while sharpening the need for evidence. They invite exploration while reminding us of its limits. The presence of ice itself becomes ambiguous. On Mars, ice marks loss, the freezing of once flowing water. In the outer solar system, ice may mark preservation, the sealing of oceans against hostile space. The same substance carries different meanings depending on context. Ice is not destiny, it is circumstance. These icy worlds also complicate narratives of planetary evolution. They suggest that internal processes can sustain activity long after surface conditions become inhospitable. A world may appear dead from the outside while remaining active within. This duality echoes Mars's subsurface question, but on a grander scale. The difference lies in persistence. Mars' internal heat waned early. Its subsurface habitats, if they existed, may have been transient. In contrast, tidal heating can operate indefinitely as long as orbital dynamics persist. Worlds beneath ice may enjoy stability measured not in millions but in billions of years. This longevity enhances their significance. The outer solar system thus challenges surface-centric thinking. It invites exploration to look beyond what is immediately visible. It suggests that the most enduring habitats may be those least obvious. The universe may conceal its complexity beneath layers that appear forbidding rather than inviting. There is also an emotional shift embedded in this realization. The idea of oceans hidden beneath ice evokes both wonder and unease. These are worlds we cannot easily imagine inhabiting, yet they may be more stable than Earth's surface in the long run. They suggest futures where life persists underground while surfaces change dramatically. They prompt reflection on resilience and adaptation. Worlds beneath ice also blur boundaries between planets and moons. Some moons with subsurface oceans rival small planets in complexity and volume of liquid water. Their classification as secondary bodies becomes arbitrary. What matters is not size or label, but environment. This blurring reinforces a broader lesson of the outer solar system. Significance is not dictated by familiarity. The most important worlds may not resemble Earth. They may not host continents, skies, or visible seas. They may exist in darkness, powered by tides and insulated by ice. In recognizing these worlds, planetary science expanded its moral and intellectual horizon. Life, if it exists elsewhere, may do so in forms and places that challenge human intuition. Worlds beneath ice remind us that nature is inventive, not constrained by our preferences. The outer solar system did not simply add new objects to study. It added new ways of thinking about life, energy, and environment. Ice, once a symbol of lifelessness, became a sign of possibility. These frozen shells are not endings. They are coverings. Beneath them, worlds may endure. If the discovery of worlds beneath ice overturned assumptions about cold and sterility, the recognition of volcanic moons shattered an equally persistent belief that geological activity requires a planet-sized body. In the outer solar system, some of the most geologically extreme environments are not planets at all, but moons. Small, tidally stressed, and locked in gravitational embraces with giant planets, these bodies demonstrate that size alone does not determine vitality. Heat can come from motion as well as mass, and where heat persists, worlds remain alive. The realization that moons could be volcanically active was among the most startling moments in planetary exploration. Prior to close encounters, volcanism was assumed to be the domain of large internally heated planets. Smaller bodies were expected to cool quickly, becoming rigid and inert. This expectation seemed reasonable, grounded in thermal physics. Yet the outer solar system refused to cooperate with reasoned simplicity. The key lies in tidal forces. When a moon follows an elliptical orbit around a massive planet, it experiences continuous flexing. As it moves closer and farther from its primary, gravitational stress rises and falls. This stress deforms the moon's interior, generating friction and heat. Unlike radioactive heating, which diminishes steadily over time, tidal heating can persist indefinitely as long as orbital conditions remain stable. This mechanism produces extremes. In some moons, tidal heating manifests as intense volcanism, reshaping surfaces faster than impacts can scar them. Lava flows erase craters, repainting the landscape repeatedly. Surface materials are recycled not over billions of years, but over decades or centuries. These moons are not merely active, they are restless. The existence of such volcanism has profound implications. It demonstrates that internal heat does not depend solely on primordial formation energy. Worlds can remain geologically alive long after their formation if gravitational interactions provide ongoing input. The outer solar system thus becomes a theatre of perpetual motion, where energy is redistributed through orbital relationships rather than solar proximity. Volcanic activity also signals internal differentiation. To sustain eruptions, a body must possess layered structure, sources of melt, pathways for ascent, and mechanisms for surface release. These features imply complexity beneath the surface. Volcanic moons are not homogeneous lumps of ice and rock. They are structured worlds with internal dynamics. Yet volcanism alone does not imply habitability. Lava is destructive as well as creative. Extreme temperatures sterilize surfaces. Constant resurfacing can erase any nascent biological signatures. Volcanic moons demonstrate energy abundance, but not necessarily biological friendliness. The true significance emerges when volcanism and ice coexist. In moons where tidal heating is strong enough to melt ice but not to dominate the surface entirely, a different regime appears. Heat concentrates beneath frozen shells, maintaining liquid layers while leaving the exterior cold. Volcanism may occur not as surface lava flows, but as cryovolcanism, eruptions of water, slush, or volatile mixtures rather than molten rock. In these worlds, geology operates through phases unfamiliar on Earth. Hidden oceans thrive in this regime. Beneath kilometers of ice, water remains liquid, warmed by tidal dissipation and insulated from space. These oceans may be global, enveloping the moon entirely, or regional, confined to pockets and layers. Either way, they represent vast volumes of liquid water, sometimes exceeding Earth's oceans in total mass. The presence of volcanism enhances the significance of these oceans. Where rock meets water, chemistry becomes energetic. Minerals dissolve. Redox gradients form. Heat drives circulation. These processes mirror environments on Earth, where life thrives without sunlight, such as deep-sea hydrothermal systems. Volcanic moons thus combine two critical ingredients: persistent energy and stable liquid water. This combination elevates them from curiosities to central figures in astrobiology. Unlike surface environments that depend on climate stability, subsurface oceans buffered by ice and driven by tides may remain habitable across immense spans of time. Their isolation protects them from radiation and surface volatility. Their energy sources are internal and renewable. However, these same qualities complicate detection. Life in hidden oceans would be sealed away, inaccessible to direct observation. Any evidence must travel upward through ice, perhaps emerging as chemical signatures in plumes, altered surface materials, or trace gases. Interpretation becomes indirect, probabilistic, and cautious. This indirectness echoes earlier lessons from Mars. Ambiguity demands restraint. Extraordinary environments do not justify extraordinary claims without commensurate evidence. Volcanic moons expand the realm of possibility, but they do not eliminate uncertainty. They also challenge intuition about scale and hierarchy. Some of these moons rival or exceed planets in complexity. Their oceans may be deeper than Earth's. Their energy fluxes may surpass those of larger bodies. Classification becomes secondary to function. The line between planet and moon blurs, replaced by a continuum of worlds shaped by interaction. This continuum reshapes the meaning of the outer solar system. It is not merely a cold periphery. It is a dynamic zone where gravity sculpts environments as actively as heat and chemistry. The Sun recedes in importance, replaced by planetary systems as drivers of change. Volcanic moons also complicate narratives of stability. Their environments are not tranquil. Tidal heating can fluctuate. Orbital resonances can shift. Activity levels may rise and fall. Habitability here is not static, it is dynamic, shaped by celestial mechanics. Life, if present, would need to adapt to variability rather than rely on equilibrium. This variability could be a strength rather than a weakness. Fluctuating conditions create gradients and cycles that drive complexity. Life on Earth thrives on change as much as stability. Volcanic moons may offer environments rich in challenge and opportunity, though their forms of life, if any, would likely differ profoundly from terrestrial analogues. The recognition of these worlds also reframes the concept of extreme. Volcanic moons are extreme by human standards, yet they may be biologically moderate in context. The absence of sunlight, the presence of ice, and the reliance on internal energy define a different baseline. What appears hostile from one perspective may be normal from another. This reframing encourages humility. Human intuition is shaped by Earth's surface conditions. The universe is not obligated to conform to them. Volcanic moons remind us that life's potential may be realized in places humans would never choose to inhabit. At the same time, these worlds are not utopias. They present challenges as severe as their promises. Chemical environments may be hostile. Energy may be unevenly distributed. Ice shells may limit exchange between ocean and surface, constraining nutrient cycles. Volcanic moons offer opportunity, not certainty. Their greatest contribution may lie in expanding imagination anchored to physics rather than fantasy. They demonstrate that habitability can arise from interaction rather than location, from motion rather than proximity to a star. They invite exploration that looks for processes rather than appearances. In doing so, volcanic moons and hidden oceans alter the search for life beyond Earth. The focus shifts from finding Earth's twin to understanding Earth's alternatives. Life may not require blue skies or continents. It may require only energy, chemistry, and time. The outer solar system teaches that these ingredients can coexist in unexpected ways. Volcanic moons stand as proof that small worlds can be powerful, that ice can conceal warmth, and that gravity can substitute for sunlight. They also underscore a final, sobering lesson. Worlds that appear static from afar may be the most dynamic beneath the surface. Without close exploration, their true nature would remain hidden. The universe does not advertise its complexity openly. It requires patience, proximity, and a willingness to abandon assumptions. Volcanic moons are not anomalies. They are revelations. They tell us that the solar system's most active worlds may be those we least expected, and that the line between dead and alive is often buried beneath ice. By the time the outer solar system's moons revealed their hidden oceans and volcanic engines, the concept of habitability could no longer remain what it once was. For generations, habitability had been a narrow idea shaped by a single example. Earth, with its surface oceans, temperate climate, and sunlight-driven ecosystems, had quietly set the rules. A habitable world was assumed to be Earth-like, orbiting at the right distance from a star, with liquid water on its surface and an atmosphere capable of sustaining it. The outer solar system did not merely challenge this definition, it dismantled it. The most profound shift was the decoupling of habitability from sunlight. For centuries, the sun had been treated as the primary source of energy for life. Photosynthesis dominated Earth's biosphere, reinforcing the belief that stellar radiation was essential. Yet worlds beneath ice demonstrated that energy could arise from gravity, motion, and internal heat. Life, if it existed in these environments, would not be fed by light from above, but by chemistry and heat from below. This realization forced a redefinition of what it means for a world to be alive-friendly. Habitability was no longer a surface condition dependent on climate alone. It became a broader concept encompassing internal processes, energy flows, and long-term stability. A world could be frozen at the surface and still host environments capable of sustaining complex chemistry beneath. The traditional habitable zone, defined by distance from a star, suddenly felt incomplete. The habitable zone had always been a useful simplification. It provided a first-order way to identify where liquid water might exist on a planet's surface. But it was never a guarantee of life, nor was it ever comprehensive. Mars had already demonstrated that being within or near such a zone did not ensure biological success. The outer solar system now showed that worlds far outside it could remain viable through entirely different mechanisms. This expansion of habitability introduced complexity rather than clarity. Instead of a single criterion, habitability became a spectrum. Worlds could be partially habitable, intermittently habitable, or habitable only in isolated regions. Some might support life briefly, others might do so for billions of years. Habitability ceased to be a box to be checked and became a set of interacting conditions to be weighed. Energy emerged as the unifying theme. Regardless of location or composition, habitable environments require a persistent energy source capable of driving chemistry away from equilibrium. On Earth, that energy is largely solar. In the outer solar system, it is tidal. Elsewhere, it might be radioactive or chemical. The form of energy matters less than its reliability and accessibility. Water remained central, but its role evolved. Liquid water was still considered essential, yet its location no longer needed to be visible or open. Water could exist beneath kilometers of ice, isolated from atmosphere and sunlight, and still function as a medium for chemistry. This reframing made water less of a surface feature and more of a structural one, a component of planetary interiors as much as exteriors. Stability also took on new meaning. Traditional habitability emphasized stable climates and long-lived surface conditions. Worlds beneath ice offered a different kind of stability. Shielded from radiation and surface volatility, subsurface oceans could remain liquid even as external conditions fluctuated wildly. A planet or moon might experience dramatic surface changes while its interior remained comparatively constant. This interior stability could, in theory, be more conducive to life than Earth's surface, which has undergone repeated mass extinctions and climatic upheavals. The outer solar system thus suggested that habitability might favour concealment over exposure. Life might endure longest where it is best protected. Redefining habitability also meant abandoning human-centred expectations. Concepts such as breathable air, open oceans, and temperate weather were revealed as parochial. They mattered to human explorers, not necessarily to life itself. Habitability became less about comfort and more about chemistry. This shift carried psychological weight. The search for life had long been driven by the hope of finding familiar worlds, places that could, in principle, be visited or even settled. Worlds beneath ice resisted such fantasies. They were not destinations, they were environments. They could be studied, inferred, and perhaps sampled indirectly, but not easily inhabited. In this sense, redefining habitability also redefined exploration's goals. The aim was no longer to find new Earths, but to understand how life might arise and persist under radically different conditions. The question changed from, where could we live, to where could life exist? This distinction mattered. It aligned planetary science more closely with biology and chemistry, and less with human aspiration. It encouraged exploration driven by curiosity rather than projection. The outer solar system demanded that life be understood on its own terms. At the same time, this broader definition increased uncertainty. As habitability expanded, so did the number of candidate environments. Not all could be explored directly. Prioritization became essential. Which environments were most likely to support life? Which were most stable? Which offered detectable signatures? Redefining habitability complicated decision-making, even as it enriched possibility. It also sharpened the need for precision. If habitability could exist in many forms, then claiming it required careful evidence. The term could no longer be used loosely. Worlds might be potentially habitable in some respects while hostile in others. Mars had already taught the danger of conflating possibility with outcome. The outer solar system reinforced that lesson at a grander scale. This redefinition also influenced how life itself was conceptualized. Life no longer needed to be imagined as surface-dwelling, photosynthetic, or even easily detectable. It could be sparse, slow-growing, and deeply buried. It might leave few traces and operate on timescales alien to human experience. Habitability became less about abundance and more about endurance. The idea of marginal habitability also gained prominence. Some environments might hover near the edge of viability, supporting life only under specific conditions or during limited periods. Such life, if it existed, would be fragile and rare. The universe might contain many such marginal worlds, each offering only a narrow window for biology. This perspective tempered expectations, without extinguishing wonder. The outer solar system did not promise that life was everywhere. It suggested instead that the universe was permissive rather than generous. It allowed life, but did not guarantee it. Redefining habitability also reshaped how Earth was perceived. Earth's surface conditions, once considered typical, now appeared exceptional. Earth combined surface water, sunlight, atmospheric protection, and internal recycling in a way that few other worlds seemed to match. Rather than being the baseline, Earth became an outlier, a particularly favourable arrangement among many less accommodating possibilities. This realisation deepened appreciation rather than diminishing it. Earth's habitability was not trivial or inevitable. It was the result of multiple conditions aligning and persisting. The outer solar system's diversity highlighted how easily those alignments could fail or take alternative forms. In practical terms, redefining habitability influenced mission planning and scientific priorities. Exploration began to emphasize processes rather than appearances. Scientists looked for energy gradients, chemical disequilibria, and signs of interaction rather than Earth-like landscapes. Instruments were designed to detect subtle signals rather than obvious ones. The concept of habitability thus matured. It became less about drawing boundaries and more about understanding systems. It acknowledged that life's requirements might be minimal, but its emergence might be rare. It separated the conditions for life from the certainty of life. The outer solar system did not provide a final definition of habitability. It made such a definition impossible. Instead, it offered a framework, one flexible enough to accommodate worlds that defy expectation, yet rigorous enough to demand evidence. In redefining habitability, planetary science accepted uncertainty as a feature rather than a flaw. The universe, it turned out, was not obliged to conform to tidy categories. Habitability was no longer a place. It was a process. As the outer solar system's moons came into sharper focus, another long-standing assumption quietly collapsed: the belief that moons were inherently secondary worlds, defined by their dependence on planets and limited by their smaller size. The evidence told a different story. Some moons possessed internal oceans deeper than Earth's, surfaces shaped by geology rather than impact alone, atmospheres that interacted dynamically with space, and energy budgets rivaling or exceeding those of terrestrial planets. In every meaningful scientific sense, these moons were not accessories to planets. They were planets in all but name. This realization did not arrive through a single discovery, but through accumulation. Each new dataset added weight to an emerging conclusion. Scale and classification had misled perception. The distinction between planet and moon was administrative, not physical. What mattered were mass, composition, energy flow, and history. When those factors aligned, a moon could develop into a world as complex and consequential as any planet. The outer solar system is uniquely suited to produce such worlds. Giant planets exert immense gravitational influence, capturing and shaping large satellites. Their moons often form from circumplanetary disks, rich in volatile materials, allowing them to grow to substantial sizes. In some cases, these moons approach or exceed the dimensions of the smallest recognized planets. Size alone, however, tells only part of the story. What truly elevates these moons is interaction. Orbiting close to massive primaries, they experience tidal forces far stronger than anything acting on isolated planets. These forces generate internal heat, drive geological activity, and sustain subsurface oceans long after radioactive decay would otherwise allow interiors to cool. Energy, not size, becomes the decisive factor. This energy reshapes internal structure. Large moons differentiate into layered bodies with rocky cores, liquid water layers, and icy shells. They host chemistry at interfaces where rock and water meet, conditions long considered critical for life. Some possess atmospheres thin but active, shaped by internal processes and external bombardment. These features collectively rival planetary complexity. The presence of such complexity undermines the idea that moons exist in a lesser category. From the standpoint of planetary science, they are independent laboratories of evolution. Their trajectories diverge from planets not because they are simpler, but because they are shaped by different constraints. Their dependence on a host planet introduces new dynamics rather than limiting development. This dependency can be an advantage. Orbital resonances among moons stabilize eccentricities that maintain tidal heating. Magnetic interactions with parent planets generate radiation environments that alter surface chemistry. Material exchange through impacts and plasma flows connects moons into system-wide networks. These relationships create environments impossible for solitary planets to replicate. In this way, moons that rival planets exemplify the importance of context. A world's character is not determined solely by its intrinsic properties, but by its relationships. The outer solar system demonstrates that interaction can be as generative as isolation. Worlds grow complex not only by internal processes, but by being embedded in dynamic systems. The recognition of planet-like moons also challenges historical narratives of exploration. Early planetary science treated moons as footnotes, targets of convenience rather than destinations of significance. That perspective inverted as data accumulated. The most promising environments for long-term habitability were not planets in the outer solar system, but their moons. This inversion carried conceptual consequences. It suggested that the search for life might succeed not by finding Earth analogues, but by recognizing Earth alternatives. Moons offered environments that did not resemble Earth's surface, yet may be more stable over geological time. Their oceans, sealed beneath ice, were insulated from cosmic hazards and planetary upheaval. Such stability contrasts sharply with planetary surfaces. Earth's biosphere thrives at the cost of exposure, vulnerable to radiation, climate shifts, and impact events. Planet-like moons trade exposure for concealment. If life exists there, it may persist quietly, protected from catastrophic change. The price of protection is isolation, but isolation may be survivable. These considerations blur the boundary between planetology and astrobiology. When moons rival planets, the unit of interest becomes the world itself rather than its classification. Exploration priorities shift accordingly. Questions of origin, energy, and chemistry take precedence over labels. This shift also reshapes thinking about planetary formation. If moons can rival planets in complexity, then planet formation is not the only pathway to rich worlds. Circumplanetary disks may produce environments as consequential as circumstellar ones. The universe may generate habitable niches at multiple hierarchical levels. The outer solar system thus emerges as a nested architecture of worlds. Planets host moons, moons host oceans, oceans host chemistry. Complexity arises through layering rather than singularity. This architecture complicates models that treat planetary systems as collections of isolated bodies. It also challenges cultural expectations. Popular imagination often equates planets with importance and moons with dependency. The science suggests otherwise. Some moons matter more, scientifically and potentially biologically, than the planets they orbit. Their stories are not subordinate. They are distinct. Recognizing moons as planet-like worlds also sharpens ethical considerations. If these environments are among the most promising for life, then they demand careful treatment. Exploration strategies must balance curiosity with preservation. The more a moon resembles a planet in complexity, the greater the responsibility to avoid contamination or irreversible alteration. This responsibility reinforces a broader lesson of exploration's maturity. As understanding deepens, restraint becomes as important as ambition. Worlds that rival planets deserve the same caution once reserved for planets alone. Classification should not dictate care. There is also a temporal dimension to this rivalry. Some moons may remain habitable longer than planets. Their internal heating mechanisms can persist as long as orbital configurations remain stable. Planets may lose atmospheres or cool internally, but moons embedded in resonant systems may continue generating energy long after isolated worlds fade. This longevity alters narratives of cosmic life. If life requires time more than space, then moons may be among its most likely refugees. They offer persistence rather than abundance, continuity rather than visibility. The universe may shelter life in places humans would not instinctively search. The recognition of moons that rival planets therefore expands both scientific scope and philosophical humility. It reveals that importance is not a function of size or status, but of process and potential. Worlds once dismissed as peripheral become central. The outer solar system teaches that planetary systems are not linear hierarchies, but ecosystems. Each component influences the others. Some moons emerge as keystone worlds, shaping scientific understanding and redefining expectations. In this light, the distinction between planet and moon begins to feel obsolete. What matters is whether a world has the capacity to change, to sustain energy flows, and to maintain environments where complexity can arise. By those criteria, several moons of the outer solar system stand among the most compelling worlds known. They are not merely companions to giants. They are giants in their own right. For most of human history, life and sunlight were inseparable ideas. The rising sun marked growth, warmth, and renewal. Plants turned light into substance. Animals fed on plants directly or indirectly. Even early scientific biology absorbed this logic, treating sunlight as the foundation of life's energy economy. The possibility that life could exist without sunlight, entirely independent of stellar radiation, seemed at best an exception. The outer solar system transformed that exception into a serious proposition. The first cracks in the sunlight paradigm appeared on Earth itself. Long before icy moons entered scientific discussion, researchers discovered ecosystems thriving in total darkness at the bottom of Earth's oceans. These communities did not rely on photosynthesis. Instead, they were powered by chemical energy released when seawater interacted with hot rock. Life, it turned out, could run on chemistry alone. This discovery altered biology, but its implications for planetary science were not immediately absorbed. Earth's deep ocean ecosystems were initially treated as curiosities, special cases that did not challenge the dominant solar model of life. Only when the outer solar system revealed environments where sunlight was irrelevant by necessity did the deeper implication become unavoidable. In the outer solar system, sunlight is weak, diffuse, and often blocked entirely. Any life that might exist there could not rely on photosynthesis in any meaningful sense. If life were present, it would have to exploit alternative energy pathways. The question was no longer hypothetical. The environments themselves demanded it. Chemical energy became the central focus. Wherever water interacts with rock, chemical gradients arise. Certain reactions release energy that organisms can harness. On Earth, these processes occur in deep-sea environments, underground aquifers, and subsurface ecosystems. They operate slowly, quietly, and persistently. They do not require light, only chemistry and time. The outer solar system provides abundant opportunities for such interactions. Subsurface oceans resting atop rocky interiors create vast interfaces where water and minerals meet. Heat from tidal flexing keeps these environments active. The chemistry does not need to be dramatic to be viable. Even low-energy systems can sustain life if they are stable. This stability is crucial. Sunlight-driven ecosystems can be highly productive but also volatile. Seasonal cycles, climate shifts, and atmospheric changes impose constant stress. Chemically powered ecosystems, by contrast, may be less energetic but more enduring. Shielded from surface upheaval, they operate in slow equilibrium. Life without sunlight may be less abundant, but more persistent. This persistence reframes what it means for life to thrive. Earth's biosphere is exuberant, expansive, and visible. Life in the outer solar system, if it exists, would likely be sparse, localized and hidden. Its success would not be measured in forests or oxygen-rich atmospheres, but in survival across geological time. The absence of sunlight also alters evolutionary pressures. Without light, there is no day-night cycle, no seasons, no photosynthetic base of the food web. Life must adapt to chemical gradients that may change slowly or unpredictably. Metabolisms would be tuned to scarcity rather than abundance. Growth rates would be slow. Adaptation would favor efficiency over speed. This challenges intuitive expectations of life's appearance and detectability. Such organisms would not reshape their environment dramatically. They would not produce obvious atmospheric signatures or surface changes. Their presence might be subtle to the point of invisibility. Detecting them would require sensitivity rather than spectacle. Life without sunlight therefore complicates exploration strategy. Traditional biosignatures, oxygen, vegetation, surface patterns, would be absent. Instead, scientists must look for chemical imbalances, unexpected concentrations, or isotopic anomalies. Even then, ambiguity remains. Chemistry alone can produce many of the same signals biology does. This ambiguity does not weaken the case for exploring such environments. It strengthens the need for caution. Life without sunlight forces science to distinguish carefully between living and non-living processes. It demands rigor rather than optimism. The philosophical implications are equally profound. Sunlight-based life places stars at the center of biological destiny. Chemically powered life decentralizes that role. It suggests that life's emergence may depend less on stellar generosity than on planetary mechanics and chemistry. Worlds do not need to bask in light to host complexity, they need energy gradients and stability. This decentralization expands the potential habitats for life dramatically. Regions once dismissed as too cold or too dark become viable. The universe's habitable real estate grows larger, but also more hidden. Life may be common in principle, yet rare in detection. At the same time, life without sunlight may be more limited in its capacity for complexity. Without abundant energy, ecosystems may remain simple. Intelligence, technology, or large multicellular organisms may be unlikely. Life may persist without ever transforming its world in obvious ways. This raises uncomfortable questions about what counts as success in the cosmic sense. Is life meaningful if it never becomes visible? The outer solar system does not answer this question, but it sharpens it. Worlds beneath ice may host life that is ancient, persistent, and utterly unknown beyond its own dark ocean. Such life would not broadcast its existence. It would endure quietly, indifferent to discovery. This possibility reframes the search for life as an act of humility. Humanity may not be the universe's primary audience. Life may not exist to be seen. It may exist simply because conditions allow it to continue. Life without sunlight also intersects with the concept of planetary longevity. Stars change over time. Their luminosity evolves. Planets within traditional habitable zones may drift out of them. Chemically powered life, by contrast, is insulated from stellar change. As long as internal energy persists, such ecosystems could outlast surface biospheres by billions of years. In this sense, life without sunlight may represent the universe's long-term strategy rather than its early flourish. Bright, surface-based life may be a transient phase. Hidden, subsurface life may be the enduring norm. This perspective unsettles human-centered narratives of progress and expansion. If life's most persistent forms are invisible and inaccessible, then exploration becomes less about conquest and more about understanding. The goal is not to find places to go, but to comprehend forms of existence that operate beyond human experience. The outer solar system thus becomes a proving ground for this broader vision. It forces science to abandon assumptions rooted in Earth's surface and embrace possibilities shaped by physics rather than familiarity. Life without sunlight is not an exotic fantasy. It is a plausible outcome of known processes. Yet plausibility is not confirmation. The outer solar system offers environments where life could exist, not evidence that it does. The distinction matters. Mars taught the danger of conflating habitability with life. Worlds beneath ice demand the same discipline. What they offer above all is perspective. They show that life's relationship with energy is flexible. They demonstrate that darkness does not imply death. They reveal that the universe may harbour forms of vitality that do not announce themselves in light. In acknowledging this, planetary science matures. It becomes less about finding reflections of Earth and more about understanding life as a physical phenomenon, one that adapts to available energy, chemistry, and time. Life without sunlight is not a contradiction. It is a reminder that life's story is larger than the one we know. Exploring a planetary system is not the same as visiting a planet. Early space exploration often treated worlds as isolated targets, single encounters designed to capture images, gather measurements, and move on. This approach yielded dramatic revelations, but it also imposed limits. A brief visit can show what a world looks like. It cannot easily reveal how that world behaves over time. The outer solar system, with its vast scales and interlocking dynamics, made those limits unmistakable. To understand such systems, exploration had to become long-term. The shift towards sustained observation marked a maturation of planetary science. Rather than snapshots, scientists sought narratives. They wanted to see storms evolve, rings shift, moons interact, and magnetic environments fluctuate. These phenomena unfold on timescales that exceed flybys. Only by remaining present could their rhythms be understood. Long-term exploration revealed that planetary systems are not static arrangements of objects, but living systems in the physical sense, networks of interaction governed by energy flow, feedback, and change. The giant planets and their environments behave less like collections of inert bodies and more like ecosystems, where altering one component influences many others. This realization emerged gradually. Early missions demonstrated the richness of individual worlds, but follow-up missions transformed isolated discoveries into connected understanding. Rings were no longer just beautiful structures. They became dynamic laboratories shaped by gravity and collision. Storms were no longer curiosities. They became expressions of deep atmospheric circulation. Moons were no longer accessories. They became active participants in system-wide processes. Time proved to be the missing dimension. Without it, many processes appear frozen or inexplicable. With it, patterns emerge. Long-term exploration allowed scientists to watch how energy moves through a system, how materials are exchanged, and how stability is maintained or lost. Planetary systems revealed themselves as processes rather than products. One of the most striking lessons of sustained observation is persistence. Some features endure far longer than expected. Massive storms can last decades or centuries. Ring structures can remain stable while constantly renewing themselves through collisions and resonances. Orbital relationships among moons can maintain energy flows across billions of years. These forms of persistence challenge assumptions about fragility and impermanence. At the same time, long-term exploration exposes variability. Planetary systems are not frozen in equilibrium. They fluctuate. Storms wax and wane. Seasonal changes alter atmospheres and surfaces. Magnetic environments respond to solar activity. Rings evolve subtly as particles migrate and collide. These variations matter. They reveal underlying mechanisms and test theoretical models. Understanding variability requires patience. Short missions risk misinterpreting transient states as norms. A single observation might catch a system during an unusual phase. Long-term monitoring smooths these anomalies, revealing baselines and cycles. In doing so, it transforms surprise into comprehension. This temporal perspective also deepens insight into causality. When changes are observed over time, relationships become clearer. A shift in a moon's orbit correlates with changes in geological activity. Variations in solar output influence magnetospheric behavior. Storm evolution reflects deeper atmospheric dynamics. Cause and effect become traceable rather than speculative. Long-term exploration thus bridges observation and theory. It allows models to be tested against reality not once but repeatedly. Discrepancies can be identified, refined, and resolved. The result is a more resilient science, one that acknowledges complexity rather than oversimplifying it. The need for duration is particularly acute in the outer solar system. Distances are vast. Signals are weak. Processes are slow. Many interactions operate on timescales far beyond human intuition. Only sustained presence can reveal them. The outer solar system resists haste. This resistance shapes mission design. Spacecraft must endure harsh environments for years or decades. Instruments must remain calibrated. Communication delays must be managed. Exploration becomes an exercise in longevity as much as discovery. Success depends on reliability rather than speed. The reward for this endurance is coherence. Long-term exploration reveals how disparate phenomena fit together. Rings influence moons. Moons influence rings. Magnetospheres interact with atmospheres. Atmospheres respond to internal heat and external radiation. Each component participates in a larger system. Understanding emerges not from isolated facts but from integration. This integration also changes how habitability is assessed. A single measurement of temperature or composition is insufficient. Habitability depends on stability, energy flow, and persistence, all of which require time to evaluate. Long-term exploration provides the temporal context necessary to distinguish fleeting conditions from enduring environments. In this sense, planetary systems resemble climates more than landscapes. They are defined by patterns over time rather than features in space. A climate cannot be understood from a single day's weather. Likewise, a planetary system cannot be understood from a single encounter. This analogy underscores another lesson. Systems can mask underlying vulnerability. A planet may appear stable during brief observation, yet be undergoing slow change. Long-term data can reveal trends invisible in snapshots. It can show whether systems are resilient or merely delayed in decline. Mars offered an example of this principle at planetary scale. Its surface records a long trajectory from habitability to barrenness. The outer solar system extends this lesson to entire systems. Stability must be demonstrated, not assumed. Long-term exploration also reshapes scientific humility. It reveals how often early interpretations must be revised. Initial models give way to refined ones as more data accumulate. Confidence becomes provisional rather than absolute. The universe proves more inventive than theory anticipates. This humility is productive. It encourages adaptability and openness. Long-term exploration is not about confirming expectations, but about letting systems reveal themselves. It values listening over projecting. There is also a philosophical dimension to sustained presence. Remaining with a system long enough to understand it fosters a different relationship to exploration. It shifts emphasis from conquest to companionship. The goal becomes comprehension rather than acquisition. This shift aligns with the ethical maturation of space science. Planetary systems, once understood as static backdrops, emerge as dynamic entities deserving respect. Long-term exploration acknowledges their complexity and autonomy. It recognizes that understanding cannot be rushed without distortion. This recognition influences future exploration beyond the solar system. As exoplanetary systems are discovered, the lesson of duration looms large. Characterizing such systems will require patience measured in decades. Patterns must be inferred across time, not assumed from single transits or spectra. The outer solar system thus serves as a training ground for this broader endeavor. It teaches how to study complexity without oversimplifying it. It demonstrates the value of commitment in scientific inquiry. Ultimately, long-term exploration transforms planetary science from a catalogue of worlds into a study of systems. It reveals that planets, moons, rings, and fields form interconnected wholes governed by flows of energy and matter. Understanding any part requires attention to the whole. This transformation mirrors the shift from descriptive to systems-based science more generally. The outer solar system is not merely a collection of objects. It is a network of interactions unfolding across time. Long-term exploration is the only way to witness that unfolding. In embracing duration, planetary science gained depth. It moved beyond the thrill of first sight to the discipline of sustained understanding. The outer solar system demanded nothing less. At first glance, planetary rings appear ornamental. Delicate halos encircling giant planets, visually striking but seemingly superficial. Early observers often treated them as curiosities, peripheral to the real planets they adorned. Long-term exploration overturned that view completely. Rings are not decorations. They are active, evolving systems that function as natural laboratories, offering insights into gravity, collision physics, disk dynamics, and the processes that shape planetary systems across the universe. What makes rings uniquely valuable is their scale combined with their accessibility. They are vast enough to display collective behavior, yet close enough to observe in extraordinary detail. Within them, countless particles interact through gravity, collision, and resonance, enacting processes that also occur in protoplanetary disks and galactic structures, only at scales and speeds that allow direct study. Rings compress cosmic evolution into an observable time frame. This compression is crucial. Many of the most important processes in astronomy unfold over millions or billions of years, far beyond direct observation. Rings, by contrast, change measurably over human timescales. Structures form, migrate, dissipate, and reform. Waves propagate. Gaps open and close. By watching these changes, scientists gain real-time insight into mechanisms that would otherwise remain theoretical. At the heart of ring dynamics lies gravity. Each particle in a ring follows its own orbit, yet collectively they behave as a fluid-like disk shaped by gravitational interactions. Tiny variations in orbital speed lead to collisions, redistributing energy and momentum. Over time, these countless interactions produce emergent structures, sharp edges, density waves, and finely sculpted patterns that betray the invisible hand of physics at work. Resonance plays a defining role. Moons orbiting near rings exert periodic gravitational tugs that organize particles into waves and gaps. These resonances amplify small forces into large-scale structure, demonstrating how order can arise from repetition. The same principle operates in protoplanetary disks, where young planets carve gaps and shape the distribution of material. Rings offer a scaled-down, accelerated version of this process. Because ring particles are relatively small and numerous, collisions are frequent. These collisions are not merely destructive, they are creative. They dissipate energy, flatten disks, and enforce coherence. In doing so, they reveal how systems evolve toward stability. Rings thus serve as testbeds for understanding how disks settle, thin, and persist. This persistence is itself instructive. Rings are neither fleeting nor eternal. Their lifetimes depend on a balance between replenishment and loss. Particles grind down, migrate inward, or are ejected. New material arrives through collisions or erosion of nearby bodies. Observing this balance illuminates how systems maintain themselves or fail to do so. The composition of rings adds another layer of insight. Ring particles range from icy grains to larger fragments, reflecting the materials available in their region of formation. Their reflectivity, structure, and distribution preserve clues about temperature, radiation, and chemical environment. In this way, rings function as archives of planetary history as well as dynamic systems. Long-term observation revealed that rings are far from uniform. Subtle variations in density, thickness, and composition create complex patterns. These patterns are not random. They encode information about forces acting within the system. Deciphering them requires patience, precision, and an appreciation for complexity. This complexity challenges simplistic models. Early theories struggled to explain how rings could remain thin and sharply defined. Extended observation showed that continuous interaction, collisions, resonances, and self-gravity maintains their structure. Rings are not static leftovers. They are active systems sustained by ongoing processes. Self-gravity is particularly revealing. In dense regions, particles can clump temporarily, forming transient aggregates that grow and disperse. These clumps demonstrate how gravity competes with shear and collision to shape matter. The same competition governs planet formation, only at vastly larger scales. Rings allow this interplay to be studied directly. Because rings respond sensitively to perturbations, they act as detectors of otherwise invisible influences. A passing moon, a shift in orbit, or a change in gravitational field leaves a signature in ring structure. By reading these signatures, scientists infer properties of objects too small or distant to observe directly. Rings become instruments as much as subjects. This instrumental role extends beyond planetary science. Disk dynamics operate throughout the universe, in star-forming regions, around black holes, and within galaxies. Rings provide a nearby analogue where fundamental physics can be tested. They bridge the gap between laboratory experiments and cosmic phenomena. Rings also reveal the importance of scale invariance. The same equations govern systems from microscopic grains to galactic disks. What changes are parameters, mass, distance, energy, not principles. Rings demonstrate this universality vividly. Watching a density wave propagate through a ring is, in essence, watching a universal process unfold in miniature. This universality deepens the philosophical significance of rings. They show that complexity does not require novelty. It emerges from simple rules applied repeatedly. The universe does not invent new laws for different scales. It recombines the same principles in diverse contexts. Rings make this recombination visible. The aesthetic appeal of rings should not obscure their analytical value. Their beauty arises from order imposed on chaos, from structure emerging out of countless interactions. Appreciating that beauty alongside its physical meaning enriches scientific understanding rather than detracting from it. Long-term exploration was essential to uncovering this meaning. Without sustained observation, rings might still be dismissed as static ornaments. Watching them change revealed their vitality. It also revealed how much information can be encoded in subtle motion. This lesson extends beyond rings. It reinforces the value of patience in science. Many systems reveal their nature only through time. Rings reward those willing to watch rather than merely glance. They also remind us that some of the universe's most instructive phenomena are not the largest or most energetic, but the most accessible. Rings occupy a sweet spot between scale and clarity. They are big enough to matter, small enough to study, and dynamic enough to teach. In treating rings as laboratories, planetary science embraced a broader methodological insight. Nature conducts experiments continuously. The task of science is not to replicate them artificially, but to observe them carefully. Rings are among nature's most generous experiments, offering insight into processes that shape worlds. They demonstrate that systems can be both fragile and enduring, chaotic and ordered. They show how complexity arises without design. They reveal that even seemingly decorative features can carry profound meaning. In encircling their planets, rings also encircle understanding. They draw attention to the interactions that define systems rather than the objects that anchor them. They invite exploration to focus on relationships rather than isolated entities. Rings, once marginal, became central, not because they changed, but because understanding did. Weather is the most immediate expression of a planet's physics. It is where energy, motion, and chemistry become visible, shaping skies and surfaces alike. On Earth, weather feels familiar and immediate. Clouds gather, storms form, seasons cycle predictably. For a long time, this familiarity constrained imagination. Other worlds were expected to have simpler, diminished versions of Earth's climate, scaled down by distance from the sun or atmospheric thinness. Long-term exploration of the outer solar system overturned that expectation decisively. These worlds did not merely have weather. They had alien weather, systems shaped by physics in regimes Earth never approaches. The defining feature of weather on the giant planets is scale. Their atmospheres are deep beyond terrestrial comparison, extending thousands of kilometers downward into increasing pressure and temperature. There is no solid surface to anchor storms or halt circulation. Instead, atmospheric motion is governed by rotation, internal heat, and stratification. The result is weather that is not confined to a region or season, but can persist for decades or centuries. Internal heat plays a central role. Unlike Earth, whose weather is driven primarily by sunlight, the giant planets radiate substantial energy from their interiors. This heat fuels convection from below, feeding storms independently of seasonal solar input. Weather on these worlds is therefore not merely reactive to external forcing, it is intrinsic. Storms can arise, evolve, and persist even in the absence of strong sunlight. Rapid rotation further shapes these atmospheres. The giant planets spin quickly, stretching atmospheric circulation into powerful jet streams that encircle entire worlds. These jets divide atmospheres into bands, constraining motion and creating long-lived structures. Instead of Earth's wandering storm tracks, these worlds exhibit ordered chaos, turbulence confined within persistent lanes. Long-term observation revealed that this order is dynamic rather than static. Jet streams shift subtly. Bands merge or split. Storms wax and wane. What appears frozen in a snapshot reveals complexity over time. The atmosphere behaves as a living system in the physical sense, responding to energy flows and internal feedback. Seasonality adds another layer of complexity. Although distant from the Sun, the outer planets still experience seasonal cycles due to axial tilt. These seasons unfold slowly, lasting years or decades. Their effects are subtle but cumulative, altering atmospheric chemistry, cloud formation, and circulation patterns over time. Weather becomes a long game, unfolding at a pace that challenges intuition. Some worlds experience extreme seasonal contrasts. Long winters plunge hemispheres into darkness for years, while summers bring prolonged exposure to weak but persistent sunlight. The atmosphere responds not with abrupt change, but with gradual reorganization. Clouds form and dissipate. Hazes thicken or thin. Chemical processes accelerate or stall. Weather becomes a memory of sunlight rather than an immediate response to it. These seasonal effects reveal how atmospheres store energy. On Earth, heat is redistributed rapidly by oceans and winds. On the giant planets, deep atmospheres and slow radiative cooling allow energy to accumulate and be released over long intervals. Storms may be delayed responses to past conditions rather than immediate triggers. Cause and effect separate in time. Alien weather also challenges assumptions about equilibrium. Earth's climate tends toward balance over long periods, moderated by feedback such as oceans and life. The giant planets lack such moderators. Their atmospheres can settle into patterns that persist far from equilibrium, sustained by continuous internal energy. Stability does not require balance, it requires consistency of input. This insight alters how atmospheric models are constructed. Simplified assumptions break down. Predictability becomes conditional rather than absolute. Weather on these worlds resists linear explanation. Small perturbations can grow into large-scale features, while major changes can be absorbed with little visible effect. The absence of a solid surface further complicates matters. On Earth, mountains, continents, and oceans shape weather profoundly. They anchor circulation, generate turbulence, and impose boundaries. On the giant planets, boundaries are fluid. Storms interact with each other rather than with terrain. Energy dissipates through internal friction rather than surface drag. The atmosphere becomes its own environment, largely self-contained. This self-containment allows storms to reach extraordinary longevity. Without land to disrupt them, vortices can persist as stable features, evolving slowly rather than dissipating quickly. Their endurance forces a re-evaluation of what constitutes weather versus climate. On these worlds, the distinction blurs. Weather becomes climate-like, climate becomes weather-like. Seasonal cycles on moons introduce yet another regime. Some moons possess tenuous atmospheres or transient exospheres that respond dramatically to seasonal changes. As sunlight varies, surface materials sublimate or condense, creating temporary atmospheres that wax and wane. Weather here is not about clouds and rain, but about the migration of molecules across surfaces and into space. These processes are delicate and easily missed without long-term observation. A single encounter might catch a moon during atmospheric expansion or collapse and misinterpret it as permanent. Only repeated observation reveals the rhythm. Seasonal worlds demand patience. Alien weather also intersects with chemistry. Atmospheric composition changes with season, altitude, and energy input. Molecules form, break apart, and recombine in cycles driven by radiation and temperature. Over time, these cycles alter the appearance and behavior of atmospheres. Color changes are not aesthetic accidents. They are chemical signatures of ongoing processes. Understanding these signatures requires disentangling overlapping influences. Internal heat, solar radiation, rotation, and composition all interact. No single factor dominates universally. Weather emerges from their interplay rather than from any one cause. This complexity underscores the value of long-term exploration. Without extended observation, atmospheric behavior would appear contradictory or chaotic. With time, patterns emerge. Variability becomes intelligible. What once seemed unpredictable resolves into structured dynamism. Alien weather also reframes how habitability is assessed. On Earth, stable weather patterns support surface life. In the outer solar system, surface weather may be irrelevant to habitability, which may reside beneath ice or within oceans, insulated from atmospheric extremes. Weather becomes a surface expression of deeper processes, rather than a determinant of biological potential. Yet weather still matters indirectly. It influences surface chemistry, energy exchange, and interactions with space. It shapes the environment that encloses subsurface worlds. Understanding alien weather is therefore essential, not because life exists in it, but because life may exist beneath it. This indirect role mirrors Earth's relationship between atmosphere and deep biosphere. Surface conditions influence, but do not wholly determine, subsurface environments. The outer solar system extends this principle to extremes, highlighting the layered nature of planetary systems. There is also an epistemological lesson embedded in alien weather. Familiar concepts can mislead. Terms like storm, season, and climate carry Earth-centric meanings that must be re-examined. Applying them uncritically risks misunderstanding. The outer solar system demands conceptual flexibility. This flexibility enriches planetary science. It forces the development of models capable of accommodating unfamiliar regimes. It broadens understanding of how atmospheres function under different constraints. In doing so, it prepares science for interpreting exoplanet atmospheres that may be even more alien. Alien weather also humbles expectation. Even with advanced instruments, prediction remains limited. The complexity of these systems resists full control. Observation remains essential. The universe does not yield its patterns easily. Yet within this resistance lies beauty. The vast storms, subtle seasonal shifts, and deep atmospheric currents of the outer solar system reveal physics in action at grand scale. They show how simple laws produce rich behavior. They demonstrate that weather is not a trivial detail, but a fundamental expression of planetary identity. By studying these seasonal worlds, science learns to see weather not as noise, but as signal. Each fluctuation encodes information about energy, motion, and composition. Each cycle reveals how worlds breathe, even when they lack surfaces or life. Alien weather thus becomes a bridge between the visible and the hidden. It connects atmospheric motion to internal processes, seasonal change to deep stability. It reminds us that planetary systems are coherent wholes, not collections of isolated phenomena. In the outer solar system, weather is not an afterthought. It is a language, spoken slowly, on a planetary scale, telling the story of energy in motion. Organic chemistry once carried an implicit assumption. It belonged to life, and by extension, to Earth. Carbon-based molecules were treated as biological artifacts, products of metabolism rather than outcomes of physics. This assumption eroded gradually, then collapsed entirely, as exploration pushed outward. The outer solar system revealed organic chemistry operating far from life, sunlight, and warmth, chemistry that arises naturally wherever energy, carbon, and time intersect. What had once been considered a biological signature became a planetary process. The shift began with detection rather than interpretation. Instruments designed to study atmospheres and surfaces encountered carbon-bearing molecules in environments thought too cold or inert to host complex chemistry. Methane, ethane, and heavier hydrocarbons appeared in abundance. Hazes formed from photochemical reactions. Organic compounds accumulated not as anomalies, but as stable features of planetary systems. The universe, it became clear, was chemically creative on its own. This creativity challenged a deep-seated bias. On Earth, organic molecules are constantly cycled through life. They are produced, consumed, and transformed by organisms at every scale. It was easy to mistake this ubiquity for exclusivity. The outer solar system demonstrated that organic chemistry does not require biology to begin. It requires only energy gradients and suitable raw materials. Energy is the key. In the outer solar system, energy arrives through multiple pathways. Ultraviolet radiation drives photochemistry in upper atmospheres. Charged particles from magnetospheres trigger reactions at surfaces. Tidal heating maintains warm interiors where water and rock interact. Each pathway opens routes for carbon to assemble into increasingly complex structures. The result is not random chaos, but structured chemistry. Molecules form families. Reaction networks stabilize. Complex organics persist long enough to accumulate. In some environments, these compounds precipitate, condense, or settle, becoming part of the geological record. Organic chemistry leaves traces not only in spectra, but in landscapes. This persistence matters. Transient molecules tell little. Persistent chemistry suggests ongoing processes and stability. The outer solar system's organic inventories are not fleeting. They are sustained by continuous input and recycling. Carbon chemistry here is not a dead end, it is an active domain. One of the most profound implications of this realization is decoupling. Organic chemistry can proceed independently of life, and life can emerge from organic chemistry without being identical to it. The two are related, but not synonymous. Confusing them risks misinterpretation. Mars taught this lesson through absence. The outer solar system reinforces it through abundance. Abundance, however, does not equate to inevitability. Organic chemistry can flourish without crossing the threshold into biology. The outer solar system presents environments rich in carbon compounds yet silent on life. This silence is instructive. It suggests that while organic chemistry is common, the leap to self-sustaining, evolving systems may be rare, yet rarity does not diminish significance. The widespread presence of organic molecules expands the universe's prebiotic potential. It means that the ingredients for life are not scarce. They are distributed widely, assembled repeatedly, and preserved under diverse conditions. The universe supplies the parts generously. Assembly into life remains the question. The outer solar system also complicates the notion of prebiotic chemistry itself. On Earth, prebiotic models are often constrained by assumptions about early surface conditions. In icy worlds, chemistry unfolds under different pressures, temperatures, and solvent environments. Water may be present, but it is not alone. Ammonia, methane, and other compounds alter chemical pathways. Prebiotic chemistry may follow routes unfamiliar to terrestrial laboratories. This unfamiliarity challenges experimental design and theoretical models. It demands broader thinking about what constitutes a viable pathway to life. The outer solar system suggests that chemistry can explore multiple solutions to complexity. Earth's solution may not be universal. Organic chemistry beyond Earth also reframes the role of time. In cold environments, reactions proceed slowly. Molecules persist longer. This persistence allows gradual accumulation of complexity, even with low energy input. Time compensates for intensity. What cannot happen quickly may happen eventually. This slow chemistry aligns with the broader character of the outer solar system. Processes unfold patiently. Change is subtle. Accumulation matters more than disruption. Organic chemistry here is not explosive. It is cumulative. Its products may be modest individually, yet significant in aggregate. There is also an architectural dimension. Organic molecules can assemble into structures, films, aerosols, sediments that influence physical environments. Hazes alter atmospheric temperature profiles. Surface deposits change reflectivity and energy absorption. Chemistry shapes physics as much as physics shapes chemistry. Organic compounds become actors rather than byproducts. This feedback blurs boundaries between disciplines. Chemistry becomes climatology. Geology becomes chemistry. Planetary science becomes systems science. Understanding organic chemistry beyond Earth requires integration rather than specialization. The integration deepens when considering subsurface environments. Organic molecules produced at surfaces or in atmospheres may migrate downward, accumulating in oceans or interfaces where water meets rock. There, chemistry enters new regimes. Heat and pressure unlock reactions inaccessible at the surface. Complexity can increase without sunlight or atmosphere. This possibility ties organic chemistry directly to habitability without asserting life. It suggests that some worlds may harbour rich prebiotic environments that never quite ignite biologically. Others may do so eventually, organic chemistry becomes a gradient rather than a gateway. Recognizing this gradient tempers interpretation. Detection of organic molecules is no longer cause for immediate excitement or disappointment. It is context. The question becomes not, are organics present, but what processes sustain them and where do they lead? The outer solar system also reveals that organic chemistry can be stable in unexpected places. Radiation, often seen as destructive, can drive synthesis. Cold, often seen as prohibitive, can preserve complexity. Environments once dismissed as hostile reveal nuanced roles. This nuance reshapes exploration priorities. Instead of searching solely for Earth-like conditions, science examines chemical networks. It asks how carbon moves, transforms, and persists. It looks for disequilibria that suggest active processes rather than static residues. Organic chemistry beyond Earth also carries philosophical weight. It challenges anthropocentric narratives about life's uniqueness. Carbon chemistry is not ours alone. It is a property of matter under the right conditions. Life, if it arises, is an expression of that property rather than an exception to it. This perspective does not diminish life's value. It situates it within a broader continuum. Life becomes a particular organization of chemistry, remarkable for its persistence and adaptability, not for its exclusivity. The outer solar system widens the stage on which this organization might occur. At the same time, the prevalence of organic chemistry without evident life raises sobering questions. If the universe produces the ingredients so readily, why does life appear elusive? Is the transition genuinely rare or simply hidden? The outer solar system offers no definitive answer, only sharper framing. This framing strengthens scientific discipline. It demands that claims about life be grounded in more than chemistry alone. It encourages careful separation of process and outcome. It reinforces the lesson learned repeatedly. Habitability, chemistry, and life are related but distinct. Organic chemistry beyond Earth is therefore not a promise. It is a context. It tells us what the universe is capable of producing spontaneously. It tells us where complexity begins. It does not tell us where complexity ends. The outer solar system shows that chemistry can do much on its own. It can assemble, persist, and interact across scales. It can shape environments and histories. It can prepare worlds without completing them. In this sense, organic chemistry beyond Earth is both encouraging and humbling. It suggests that life is possible, but not guaranteed. It reveals a universe rich in potential and sparing in outcome. Carbon does not wait for life to arrive. It is already at work. As evidence accumulated for subsurface oceans beneath icy shells, a unifying idea began to take shape. One that reframed not just individual discoveries, but the broader search for life itself. This idea became known as the ocean-moon hypothesis. It proposed that some of the most promising environments for life in the solar system are not planets with surface seas, but moons with hidden oceans, sustained by internal energy and insulated from cosmic hazards. The hypothesis did not emerge from speculation alone. It arose from converging lines of evidence, each reinforcing the plausibility of life in darkness. The core of the hypothesis is deceptively simple. Liquid water, energy, and chemical gradients are the essential requirements for life as it is understood. Surface conditions, sunlight, atmosphere, climate, are secondary if these essentials are met elsewhere. Ocean moons satisfy these requirements not at the surface, but beneath it. Their oceans may be global, persistent, and chemically active. They may endure for billions of years, outlasting surface oceans on planets more vulnerable to atmospheric loss or stellar change. This endurance is central. Time matters profoundly for biology. Life does not merely require suitable conditions. It requires them to persist long enough for complex processes to unfold. Ocean moons, shielded by thick ice, are buffered against many of the destabilizing forces that threaten surface environments. Radiation, impacts, and climate swings affect them indirectly, if at all. Their oceans exist in a controlled interior regime, governed by internal dynamics rather than external volatility. Energy sustains this regime. Tidal heating converts orbital motion into warmth, maintaining liquid water even far from the sun. In some cases, this heating may be uneven, creating temperature gradients that drive circulation within the ocean. Circulation in turn distributes nutrients and energy, preventing stagnation. The ocean becomes not a static reservoir, but a dynamic system. At the base of these oceans lies rock. Where water meets rock, chemistry accelerates. Minerals dissolve. Redox reactions occur. Energy becomes available in forms usable by life. On Earth, such environments support ecosystems independent of sunlight. The ocean-moon hypothesis draws directly from this terrestrial analogy, while acknowledging that conditions elsewhere may differ in detail. Those differences matter. Ocean moons operate under pressures and temperatures unfamiliar on Earth. Their oceans may be enriched with salts, ammonia, or other compounds that alter chemical pathways. Life, if present, would adapt to these conditions rather than replicate terrestrial forms. The hypothesis does not predict Earth-like life, it predicts life-compatible environments. One of the most compelling aspects of the ocean-moon hypothesis is its scope. If subsurface oceans are common among icy moons, then habitable environments may be widespread even in systems that appear inhospitable at the surface. The number of potential habitats multiplies dramatically. Instead of focusing on a narrow band around stars, the search for life expands to include countless hidden oceans orbiting giant planets. This expansion does not imply abundance of life, it implies abundance of opportunity. The hypothesis distinguishes clearly between environments that could host life and evidence that life exists. It is a framework for prioritizing exploration, not a declaration of discovery. Prioritization becomes necessary precisely because these environments are difficult to access. Thick ice shelves present formidable barriers. Direct sampling may require technologies not yet available. As a result, the hypothesis emphasizes indirect evidence, chemical signatures, plume activity, surface features linked to subsurface processes. Each line of evidence must be interpreted cautiously, aware of alternative explanations. The need for caution is a lesson learned repeatedly. Mars demonstrated how easily habitability can be mistaken for life. The ocean-moon hypothesis incorporates this lesson explicitly. It treats habitability as a necessary but insufficient condition. Life remains a question, not an assumption. Yet the hypothesis carries philosophical weight beyond its scientific content. It challenges the notion that life requires open skies and visible seas. It suggests that the universe's most stable habitats may be hidden, insulated, and inaccessible. Life may be common in principle and rare in appearance. The universe may be alive in ways that are difficult to witness. This possibility reframes humanity's place in the cosmos. If life thrives primarily in hidden oceans, then intelligence and technology may be exceptional rather than typical. Surface-based, sunlight-driven biospheres may represent a brief and fragile phase. The ocean-moon hypothesis invites reflection on whether Earth's surface life is an anomaly rather than a norm. At the same time, the hypothesis underscores the importance of systems thinking. Ocean moons do not exist in isolation. Their habitability depends on orbital relationships, gravitational interactions, and long-term stability of resonances. Disrupt those relationships, and the ocean may freeze or dissipate. Habitability here is a product of architecture rather than location. This architectural dependence has implications for planetary system evolution. It suggests that life-friendly environments may arise from interaction rather than simplicity. Complex systems may be more conducive to life than isolated worlds. The universe may favor networks over solitude. The ocean-moon hypothesis also influences how exploration is justified. Searching for life in hidden oceans is not about immediate payoff. It is about understanding where life could exist and how it might persist. The hypothesis values patience over spectacle. It aligns with long-term exploration strategies that prioritize sustained observation and careful inference. There is also an ethical dimension. If ocean moons are among the most promising habitats for life, then they warrant exceptional care. Contamination could irreversibly alter pristine environments. The hypothesis strengthens arguments for strict planetary protection. Worlds that might host life must be treated as subjects of study, not targets of exploitation. This ethical consideration reflects a broader maturation of exploration philosophy. As science identifies environments of potential biological significance, restraint becomes integral to responsibility. The ocean-moon hypothesis thus intersects with questions of stewardship as much as discovery. Critically, the hypothesis remains provisional. It does not claim certainty. It evolves with evidence. New data may refine, complicate, or even constrain its scope. Its strength lies in its adaptability rather than its finality. It is a working framework, responsive to observation. This responsiveness distinguishes it from earlier, more rigid models of habitability. Instead of defining narrow criteria, it embraces diversity of pathways. It recognizes that life may exploit opportunities humans have not anticipated. It prepares science to recognize unfamiliar forms of success. The ocean-moon hypothesis also bridges disciplines. It draws from planetary science, chemistry, biology, and physics. It requires collaboration across fields that once operated separately. Understanding these environments demands integrated thinking rather than specialized silos. This integration reflects the nature of the environments themselves. Ocean moons are not simply icy bodies, they are systems where geology, chemistry, and physics converge. Studying them requires similar convergence in scientific approach. Ultimately, the ocean-moon hypothesis reframes the search for life as an inquiry into endurance. It asks where conditions persist longest, where energy flows steadily, and where change is buffered rather than amplified. It suggests that the universe may favor life that is slow, hidden, and resilient over life that is exuberant and visible. Whether this suggestion proves correct remains unknown, but the hypothesis has already altered how exploration proceeds. It has redirected attention from surfaces to interiors, from brightness to depth, from immediacy to longevity. In doing so, it has expanded imagination without abandoning discipline. The ocean-moon hypothesis does not promise discovery. It promises perspective.